Welcome to our first video of our statistics series. This video is going to really introduce the idea of statistics and answer the question, what is statistics? And as we start studying statistics, there is some key vocabulary that we need to be very comfortable with in order to study statistics accurately and communicate our results accurately. So the first word we need to know in statistics is what we call the population. The population is basically everything, or everyone. We usually are talking about people, but not necessarily, being studied. Maybe we're investigating college students. The population would be all college students. Number two, the second word we need to know is what we call a parameter. And a parameter is some characteristic of the population. If we're talking about all college students, the parameter might be the average GPA. That'd be a parameter of the population. When we're talking about parameters, just as a note for now, we will usually use Greek letters to represent parameters. You'll see things like the Greek letter mu or the Greek letter sigma. Something in Greek generally means we're talking about a parameter of the entire population. This is different than if I was talking about a sample. A sample is a portion of the larger population. So if I went out and said we're studying college students and their average GPA, the sample might be I took a sample of 200 college students. That would be my sample. And then with a sample, we have these things called statistics. Hence the name of our course. A statistic is a characteristic of the sample. So this might be the average GPA of the 200 college students I interviewed. And to differentiate samples and populations, statistics, and parameters, with statistics we will use English letters. These English letters would be something like what we'll call X bar, or just the letter S. So as we're looking at statistics of samples, which hopefully will estimate the parameter of a population, we're also interested in what are called variables. And these are not the variables of algebra. A variable is any characteristic of interest gathered from each item in the sample. Another way to think about the variable is it's really, when I'm conducting a survey, it's really the question that is being asked. So for example, with our college students, we'd be asking them, what is your GPA? Our variable is the GPA. And then our last word for this part will be what we'll call the data, or the actual values of the variables. So a data for our example would be something like 2.38, a 3.47, a 4.0. That is the data. So let's see if we can use this key vocabulary in an example. See if we can identify the key vocabulary. You want to know the average cost of statistics textbooks. So you survey 25 textbooks. And we're going to find and identify these key terms, these same 6 key terms: the population, the parameter, the sample, the statistic, the variable, and the data. First, the population. The population is everything that we're possibly interested in. So we're talking about statistics textbooks. The population would be all statistics textbooks. And the parameter that we're interested in studying about those statistics textbook is the average cost. The average cost. But not just the average cost, but the average cost of all statistics textbooks. Notice how I tie it back to the population, because that's what the parameter describes. That can be contrasted with our sample, slightly different. Now, our sample is the smaller group, the subset we're looking at. This is the 25 textbooks. And then the statistic has to describe that sample. It's our characteristic of interest for the sample. It is the average cost of, and then tie it back to the sample, the 25 textbooks. Now the variable, that's the information I'm gathering. The variables, when I look at each textbook, what am I recording? Or the question, what am I asking with the variable? I'm asking the cost of a statistics textbook. And the data is the answer to that question, or the actual values of the variables. So it's the actual cost of the textbooks. An example might be you find an expensive one for $235. That is a piece of data to the variable, an answer to the question. All right, now that we have some vocabulary, let's move on to an example of actually summarizing data, which is what statistics is all about. With statistics, we're often interested in what is called the frequency of an event or thing. And the frequency is just how often a value occurs. And often we'll organize these frequencies in what we call a frequency table. And to set up a frequency table, we have a little bit more vocabulary. First is what we're going to call the relative frequency. And the relative frequency is just the proportion of times a value occurs. In other words, it's the decimal equivalent of the frequency divided by the total. And often with frequency, we're interested in what's called the cumulative relative frequency. And that is the sum of all previous entries. So with that vocabulary, the way we're going to set up the actual frequency table is frequency tables will generally have 4 columns. One column for the data value, a column for the frequency, which I'll denote with just f, a column for the relative frequency, which I can denote with rf, and then a column for the cumulative relative frequency, the CRF. And so then we'd fill in our data values, maybe 1, 2, and so on. Actually, let's just do 1 and 2. And then we'll do the frequency. Maybe the 1 appears 3 times and the 2 appears 7 times. So out of 10, the relative frequency is 3 out of 10, or 0.3. And for 2, the relative frequency is 7 out of 10, or 0.7. And the cumulative relative frequency will start to add all the previous values. So 0.3 plus 0.7 is 1.0 for the last column. Interesting to note is the last entry should sum to 1. Now maybe if you have a round off error, it might be 1.00001 or 0.9999999. That's okay. But generally speaking, we hope that cumulative relative frequency should sum to 1. That's all to show us how to set up the table. Let's actually make a frequency table. Let's do an example here. Let's say a baker keeps track of how many free donut holes his customers eat. "25 eat 1 donut hole. 15 eat 2 donut holes. 7 eat 3 donut holes. And 3 eat 4 donut holes." Let's make a frequency table. We have the values of 1, 2, 3, and 4 are the number of donut holes that were eaten. For the frequencies, we know 25 eat 1 donut hole, so that's our frequency. 15's the frequency for 2 donut holes, 7 for 3, and 3 eat 4. Now, if we want the relative frequency, what we have to do is divide the frequency by the total. So we need to know what the total is. And so if we add these up, we get a total of 50 customers. So when we divide 25 by 50, we get a relative frequency of 0.5. When we do 15 divided by 50, we get a relative frequency of 0.3. 7 divided by 50, we get a relative frequency of 0.14. And 3 divided by 50, we get a relative frequency of 0.06. And the fractions aren't needed so much as the actual decimal answers in our table. And then once we have our relative frequency, we can find the cumulative relative frequency by adding all the values before that. So for 1, we only have the 0.5. But then for 2, we're going to add 0.3. So we add 0.3 to get 0.8. And then we add the next value, add 0.14 to get 0.96. And then we add 0.06 to get 1.00. And that fills in our frequency table. Now that we have our frequency table, we can answer some questions about this baker. We could answer questions like, what percent ate between 2 and 3 donuts? 2 and 3 donuts have a relative frequency of 0.3 and 0.4. So when we add those together, 0.3 plus 0.14, the percent is 0.44, or as a percent, 44%. How about what percent ate more than 3? Well, I'll highlight in pink, more than 3 just means 4, so that must be this last entry of 0.06. And so we can say 0.06 or 6%. Finally, what percent ate at most 3? Well, I'll mark them in blue here. At most 3 is everybody else. I could add those all together, but what you might notice is that everybody else excludes the 6%. So it might be easier to say we've got 100% as everybody, exclude the 6% that are more than 3, and that leaves us with 94% ate at most 3 donut holes. So the big thing we're doing today is we are looking at statistics vocabulary and organizing data in frequency tables and interpreting that information. Take a look at the homework assignment that goes with this section, and in class we will investigate these frequency tables a little further. Statistics is all about the interpretation of data. So we're going to take a look today at the question, how is statistical data collected? And first, we have to really understand what we mean when we talk about data. Data can be measured on several different levels. So let's take a look at the levels of measurement. Levels of measurement start with the most simple type of data and grow to the most complex type of data. It's important we know what we're working with so we make sure we can do the correct mathematical operations of it and make sense of our conclusions. The most foundational level of measurement is what is called nominal, which basically just means we put things into categories. You might say there are no numbers. So for some examples of nominal categories, you could look at color, or maybe a yes-no survey. Do you support this political issue? Or maybe some type of label, or gender. Those are nominal categories. Now, slightly more involved than a nominal category is something that we can actually put in order and say this one is more than that one, which is more than that one. We call this ordinal data. And that's data that can be put in order. However, with that order, there is no clear space between the data values. In other words, we can say A comes before B, but we don't really care how much before B. The space between A and B might be different than the space between B and C. An example of ordinal data might be finishing place in a race. There's a clear first, second, and third, but the space between first, second, and third is not necessarily well defined. That's ordinal. Or we might say the top 5 cooks in America. Cook 1, 2, 3, 4, and 5. That's ordinal. We can put them in order, but we don't necessarily know how much better each one is than the other. Now, when we do clearly define the space between values, we have what we call interval data. Interval data has a space between the numbers with meaning. The space has meaning. However, there still is no 0 point. The space between the two numbers is well defined, like in the example of temperature. "30 degrees is 10 more than 20 degrees, just like 90 degrees is 10 more than 80 degrees. That space has meaning. And while temperature does have a 0, 0 degrees doesn't mean the absence of temperature or no temperature. It's just a point along the number line that has the same spacing as all the other temperatures. Now, if we want to have a clearly defined 0, that's when we have ratio data. And that's where we have an absolute 0 that means literally nothing or none. An example of ratio data might be the length of a phone call or a test score or the number of children. If we said we got a 0 on a test or we have 0 children, that actually means nothing, the lowest amount possible. Now, these different levels of measurement can show up in different types of data. Let's scroll up. It's very important we understand the two different types of data, and the second one can actually be broken up into two subgroups. The first type of data is what is called qualitative. Qualitative data, which really focuses, again, on categories. No numbers. We're describing the qualities of something. So, for example, we might be talking about the type of car, or maybe some type of ethnic group. Those are the qualities of the data. That's qualitative data. The second type's the one we work with the most in statistics, and that is what is called quantitative data. And quantitative data is when we're looking at quantities. Quantitative data is either measured or counted. Really, what we're talking about is numbers. How many, how much, how far, how long. Some examples of these might be the number of students, or the distance to school. Quantitative data can even be divided up further. Quantitative data can be either discrete or, leave a space, continuous. Discrete data is data that is countable. 1, 2, 3, 4, 5. When we count things, we say we have discrete data. Generally, we don't get decimals with discrete data. Examples might include the number of shoes a person owns. You're not going to end up with decimal shoes. You're not going to have 1.4 shoes. Discrete data is countable. You count the number of shoes there are. That's contrasted with continuous data, which is measured, which means every decimal and every decimal in between those decimals is possible. Measured data, example, might be the length of a phone call. Or maybe somebody's height. That's continuous data. It's measured. Always we can have decimals. You can have half an inch. You can have half of an inch or a quarter. You can have an eighth of an inch. You can do all the decimals in between. That is continuous data. So that's the different levels of measurement we can do with different types of data. But we haven't answered the question of how do we collect our data, which is what we said we wanted to do at the beginning. So let's take a look at actual sampling of data. How do we collect it? When we collect data in a sample, we want it to be representative of the entire population. In order for it to be representative of the entire population, we need the data to be random to avoid any bias. In other words, we want all options to be equally likely to be included in our sample. So if random is best, let's take a look at a few random sampling methods. The first random sampling method is what we call simple random sampling. Simple random sampling is random selection methods such as random numbers, or drawing out of a hat. This is the idea of I assign everybody a number, and I pick a bunch of random numbers, and those people are included in my survey. An example is if I want to pick students, we could assign students a number. And pick random numbers to be included in the study. A second type of random sampling is what is called stratified random sampling. And this is when we divide the population into groups. Each group is called a strata. And then select a proportionate number of each group. Polling is often done this way. The idea is if we randomly survey 100 people or 200 people, we don't want those 200 people to be all of the same political party. Otherwise, we would get a biased sample. So we guarantee it by saying if my state is 40% Democrat, 35% Republican, and 25% independent, then using a random method, we will select, I said we wanted 200 people, so maybe we double the percentages. Maybe we'd select 80 Democrats, 70 Republicans, and 50 independents to be included in my sample. I have a proportionate representative of each group that matches the proportions of the state, and so my sample still is random, but I don't get the bias of only interviewing one party. Another type of random sampling also involves groups, but it's called cluster random sampling. Again, we're going to divide into groups. But this time, instead of selecting a proportionate number of each group, we are going to randomly select entire groups. So everybody in some groups are included, and everybody in other groups are excluded. An example of doing this might be a football stadium. And it has different sections in the football stadium. So instead of interviewing everybody in the stadium or random people through the stadium, it's easier just to hit one section at a time. So in the football stadium, sections E and G are randomly selected. And all fans from those sections are included. Cluster takes all people in each randomly chosen section, while stratified takes a proportionate group out of each group. The last random method we're going to use is called systematic random sampling. The idea behind systematic random sampling is we start with a random item or person, and choose every nth person after this. That means like every 5th person, or every 12th person, or every 30th person. An example of this might be if I pick a random phone number, a random number in the phone book, and then I choose every 50th person after this until I circle back to the beginning. And go all the way through and back to the beginning and back to where I was, taking every 50th person. Those are our 4 random sampling methods that you should be able to identify for this course. There is a non-random method that is used quite a bit, and so we should at least acknowledge the non-random method called convenience sampling. Which basically says use the results that are readily available. As an example, let's say I need to collect 50 data values for a survey, so I'm just going to interview people nearby me. Or maybe people within driving distance. Maybe the friends on my Facebook friend list. Something convenient and easy to get a hold of. It's not really random. And the problem with not being random is there are several drawbacks to not being random. I could have biased results. If I'm interviewing phone preference outside of the Apple Store, I'm going to get more iPhones. That convenience sampling is going to work against me. It may not be representative. Of the population. If I only interview outside of a school because it's convenient near my house, I'm going to get a lot more parents of young children than I will the general population. And then the drawback of that is the results may not be useful outside of the sample. I could conclude that such a percent of people prefer a certain type of music, but when I'm with a different sample or a different population, those results may not be useful. So those are some drawbacks to convenience sampling. We got to watch out for convenience sampling, though it is used more often than it should be. Take a look at the homework assignment that practices with random sampling and also some of these different levels of measurement and types of data. In class, we're going to do more work with random sampling, get really comfortable with the different types, and I'll look forward to seeing you then. Now that we know the basic vocabulary of statistics and know how to collect data, we're actually ready to start displaying some data. Our question for today is, how do we display data visually? And we're going to look at 2 main ways to display data. The first way is going to be with what's called a histogram. A histogram shows us frequencies over intervals. And a histogram can really give us an idea of the shape of our data. Let's do a quick example here. It's going to be easier to talk about a histogram with an example of a histogram. So here's a scale, 1, 2, 3, 4. Up the vertical axis, the y-axis is always labeled frequency. And then the x-axis is going to be some type of label of what we're actually looking at. Maybe we're looking at the number of TVs in a home. And I'm going to actually start at negative 0.5. I'm going to come over here to 1.5, 3.5, 5.5, 7.5, 9.5, and we'll end at 11.5. First box we're going to make 1 tall. The next one we're going to go up to 3. The next one we're going to start at 2. The next bar will start at 1. Then we'll skip a space and put a bar at 1. I'm also going to give this a title. Let's title this the number of TVs. And this picture is an example of what you would expect a histogram to look like. A couple things that I want to note. The bars on a histogram touch. They come down on the interval numbers. Not in between, but right on those numbers I labeled. And they show frequency in a range. In other words, if I color this second bar green here, what that second bar means is that there are 3 values, or 3 people who reported having between 1.5 and 3.5 TVs. Between 1.5 and 3.5 are the numbers 2 and 3. So the numbers 2 and 3 all went into that bar. Now, it's impossible to have 1.5 or 3.5 TVs. And that's what brings up the second point here, point B, if possible, and it's usually easiest with discrete data, never have a bar come down on a value. In other words, if I'm talking about the number of TVs, I don't want this to come down on 4 TVs. If a bar came down on 4 TVs, I wouldn't know if that 4 goes in the left bar or the right bar. So instead, I make sure my bars come down staggered from actual data values, in this case, by 0.5. And you also notice I took care to give a title to my graph and labels for the x and y axes. Title and labels are important. So now that we kind of know what a histogram is and what it looks like, showing frequencies over a range, let's look at how to make a histogram. First, we need to decide on the number of bars. Once we decide the number of bars, we'll use this nice little formula where we take the high number minus the low number, and then divide by the number of bars. And then whatever that number is, we will round up. And that will give us the bar width, how wide each bar should be. Now, it's important to note we always round up. If it's 3.1, we'll still round up and the bars will be 4. In fact, if it's 3.0, we would still round up to have 4 bars of width 4. We always round up to the next number after this division. Next, we need to decide on the starting value. What I usually recommend we do to decide on the starting value is do 0.5 before the lowest number. In my TV's example, 0 is the lowest number of TVs, so I went 0.5 before that, so I'm staggered, and the bars won't come down on that. Then it's helpful to make a frequency table like we saw in section 1 with ranges. With the ranges that we found in parts A and B here. And we can use that frequency table then to build the histogram. So if that's the method, let's see if we can go ahead and actually do that with an example. The number of miles (20 students) commute to work is below. We are going to make a histogram with 5 bars to represent the data. And our data here is going to be 4, 6, 6, 7, 11, 13, 18, 18, 18, 21, 24, 26, 27, 35, 36, 36, 42, 43, 45, and 49. So for our bar width, we need to take the high minus the low divided by the number of bars. So the high is 49 and the low is 4. 49 minus 4 divided by the 5 bars is 9. Now it's exactly 9, so I have to round that up to 10 is my width. Always round up to the next whole number. Otherwise, your last values won't be included in the last bar. Now we can decide on our start values, or our ranges. So for our x values, to start with our graph, we're going to start half a unit before the low value of 4. So half before 4 is 3.5, and we're going to go up 10 to 13.5. The next range is going to start at that 13.5 and go up 10 to 23.5. Then we have 23.5 to 33.5. And I'm running out of space, so I'm going to scroll up a bit. 33.5 to 43.5, and 43.5 to 53.5. Those are our ranges. Now we just need to find the frequency inside each range. 3.5 to 13.5. There's 1, 2, 3, 4, 5, 6 numbers. 13.5 to 23.5. We only have 4 numbers. Then you see 23.5 to 33.5. There's 3 numbers. 33.5 to 43.5. There's 5 numbers. And 43.5 to 53.5, we see 2 numbers. Now that we have that frequency table, we're ready to build our histogram. Starting at 3.5, my next tick mark is 10 later at 13.5, then 23.5, 33.5, 43.5, and 53.5. Our frequencies go up to 6. 1, 2, 3, 4, 5, 6. The first bar is 6 tall. The second bar, touching it, is 4 tall. The next bar, touching it, is 3 tall. The next bar, touching it, is 5 tall. And the next bar, touching it, is 2 tall. And now my bars show the frequency within each of those ranges. Now I still need a title. We're talking about miles driven to work. It's a good title. Our x-axis is in miles. And then the y-axis, going from 1 to 6, always shows my frequency. And there's my histogram. Now with histograms, it's important not just to be able to draw the histogram, but we also need to be able to describe the shape of the histogram that we end up with. So a couple notes here on some vocabulary you can use to describe the shape of a histogram. And now with real-world data, it's never perfect. Histograms are never perfectly any of these shapes, but they tend to be close to one of these shapes. Not always, but generally, a common shape we'll see is what's called the uniform shape, where the bars are about the same. So just a quick sketch here. You might see bars that they're not quite exactly the same, but they're pretty darn close. We would say that histogram is uniform. They're all about the same height on all the ranges. Another word we should know is what's called a normal shape. The normal shape is taller in the middle and shorter on the edges. What a normal shape looks like is it generally starts short and gets taller until the middle, and then after the middle it starts getting shorter again. It's also called the bell-shaped curve, where it goes up and then back down. The opposite of the normal shape is what we would call the V-shape, and that is shorter in the middle and then taller on the edges. So that's when we have a tall edge that gets shorter, and then it comes back up and gets taller on the outside. And you can almost see that V shape right on top of those bars. In addition to the shape, we can talk about its symmetry. We say a graph is symmetrical if it's basically the same on both sides. So if we go tall and then shorter, it's going to be the same thing on both sides. You notice that's the same as the V shape. It's also symmetrical, the same on both sides. And we can combine these different descriptive words together to come up with a detailed description of a histogram. Then we have this idea of skewedness. Skewed means it's not symmetrical. And we describe the unsymmetrical part where the extra stuff is. Skewed right means it's not symmetrical because we have extra stuff, for lack of a better term, on the right. So that's where we're trying to be symmetrical, right? But then on the right side, there's all this extra stuff, and it kind of goes down a lot slower. That extra stuff means it's skewed right. And you might expect the last term then is skewed left, where the extra stuff is on the left. And that's where we've got all these extra little short bars on the left before it starts growing and giving us our what would be symmetrical shape. So that's histograms. We can draw them to show the shape of the data. We can describe them as uniform, normal, V-shaped, skewed, symmetrical. Really can help us visualize what our data set looks like. A second thing we can do, though, to describe our data visually is to draw what's called a box plot. And a box plot shows the spread of data with what is called the 5-number summary. Five-number summary is made up of 5 pieces: A, B, C, D, and E. The 2 easiest to find are the minimum and maximum. And then right in the middle of them is what is called, we'll put it on C, the median, or the middle when the data is in order. So the median cuts the middle of the data, and then we've got the top half and the bottom half. In the bottom half, we're going to find what's called Q1, or the first quartile. Which is the middle of the lower half. And similarly, Q3 is called the third quartile, which is the middle of the upper half. So the quartiles and the median really divide it into quarters. Now there's a little caveat with the quartiles and the median. We said they're the middle values, but if there are 2 middle values, what we'll do is we will add them together and divide by 2, giving us the middle of the middle. Once we find that 5-number summary, we'll usually represent it visually with what's called the box plot. The box plot splits the data into quarters. And to do that, we put Q1 and Q3 as the edge of the box. And then we draw whiskers out to the min and max values. And finally, we use a dotted line for the median. And so what we end up with is there's some number line down the bottom, and then floating above that number line is the box showing where the quartiles are, Q1 and Q3. Whiskers out to the minimum and maximum values. and then a dotted line for the median. And each part of the box represents a quarter, or 25% of the data values. The box then is the middle 50%, the whiskers are the outside 50%, and we can make some visual conclusions about how our data is spread out. Let's see if we can make a box plot. Going back to our example with the commute time, that list of numbers again for us was 4, 6, 6, 7, 11, 13, 18, 18, 18, 21, 24, 26, 27, 35, 36, 36, 42, 43, 45, and 49. Now, if this data was not in order, it would be essential as a first step to put the data in order. Fortunately, ours already is in order. We know there are 20 data values. So 20 cut in half is 10. We're going to have 10 below and 10 above. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cutting in half, 10 below and 10 above sticks us right between 21 and 24. Because it's right in the middle, we add those numbers together and divide by 2 to get our median value, which is 22.5. Then we can go after our quartiles. Our quartiles are in the middle of the bottom half and the top half. Well, the bottom half has 10 values, so we're going to split 5 and 5, which sticks us right between 11 and 13. Again, because there's not one value in the middle, we'll add those together and divide by 2. 11 plus 13 divided by 2 gives us our Q1 equal to 12. For the upper quartile, again, we're going to have 5 data values on each side. Sticks us right between 36 and 36. When we add those together and divide by 2, the third quartile is 36. Also include our minimum value of 4 and our maximum value of 49. And we're ready to make our box plot showing the spread of our data. We should make every attempt to make this box plot to scale. So if I count by 6s, starting at 3, we'll have 3, 9, 15, 21, 27, 33, 39, 45, and 51. Notice those are about the same size apart from each other. My box is made from the quartiles at 12 and 36. So we connect our box. The median's a dotted line at 22.5. The whiskers go to the minimum of 4 and the maximum of 49. And we have our box plot. Of course, any graph needs a title, so we can title this commute time. And label the x-axis, maybe time in minutes. And we have our box plot. Now, normally the box plot would all be one color, but I did color coding to show where all the pieces came from in this example. And just like we can describe the shape of our histograms, we can also describe the shape of our box plots. And there's basically 3 ideas here. One is the idea of being spread out, where we have a wide range of values. This would be a big box plot. covers a large range of values. That means the data is not really close to each other, not close to the median, not really close to anything. It's all spread out. The opposite of being spread out is to be clustered together, where we have a small range of values. And this is going to give us a really tiny box plot. Everything's really close to each other. And often it's beneficial to split our description into the entire shape and the middle 50%, or the box. For example, I could have a box plot that looks like this. And we could say overall, the data is spread out, but the middle 50% is clustered together, because the box is small compared to the rest of the data. So that's what we're looking at today: histograms and box plots. Practice making them, practice interpreting them, describing them. Take a look at some of them on the homework. We'll work with these a little bit more in class, and we will see you then. In our previous section, we took a look at how we could summarize data visually. But quite often, it's going to be useful to summarize data with numbers. So that's going to be our question. How do we summarize data numerically? And there's two things that we'll try and summarize numerically. The first one we're going to plant on for a minute here are the measures of center. Where is the middle of the data? And depending on our context, the measure of center will either be the mean, the median, or the mode. Let's start with the mean, or what people typically call the average. Now, if we're talking about a population mean, we will always use a Greek letter, and that's going to be the Greek letter mu. But if we're talking about a sample mean, we will use an English letter, which we will notate with x bar. And the formula for calculating the mean, I'm going to use x bar, but it works also for mu, is equal to this symbol, which we call sigma, x over n. And that symbol, that funny looking thing, means the sum. What this means is sum up all the x's, or sum up all the values, and divide by n, which is the sample size, or population size if we're in the population context. So for example, if I had the numbers 1, 3, 3, 4, 4, 4, 5, 5, and I wanted to find the mean of this sample, the numerator says sum up all the x values, or do 1 plus 3 plus 3 plus 4 plus 4 plus 4 plus 5 plus 5, and divide by the sample size. And if I count here, I see we've got a sample size of 8. So adding those all up, we get 29 over 8, which gives us a mean of 3.625, or the average is 3.625. Most students are familiar with that mean formula, but one tweak we can do to it, and we quite often have in statistics, it's not 2, let's call this C because we're still under mean, is if we have frequencies. So we've already seen one formula for the mean, the sum of the x's divided by the n. But if we have frequencies given to us where we know how often each number is used, the formula is going to tweak slightly. X bar is going to be equal to the sum of the x's times the frequency divided by the sample size. So if we have frequencies, we should know this formula. Let's do the exact same example we just did, but this time we're going to summarize those numbers by their frequencies. So first, I'll list out the numbers. The numbers that showed up were 1, 3, 4, and 5. But then I'm going to have another column that shows the frequency. I had a single 1. There were 2 3s, 3 4s, and 2 5s. What the sum says we need to do is first multiply the x's times the frequencies. So when we multiply, 1 times 1 is 1, 3 times 2 is 6, 4 times 3 is 12, and 5 times 2 is 10. And then what we want to do is sum this x times frequency table. So 1 plus 6 plus 12 plus 10 is 29. That represents the sum of the x's times the frequencies. And then we just have to divide by the sample size. Well, the frequencies tell us how many things there are. So my sample size is 1 plus 2 plus 3 plus 2 is equal to 8. So for my mean, again, we're doing 29 divided by 8 to get the exact same number of 3.625. But sometimes it's a lot quicker and easier if we have those frequencies given to us. That's the first measure of center. The measure of center of the average says if everybody was split up equally, they'd have this many in common. But quite often, the problem with the mean is one large value or one small value can throw off the mean significantly, which is why we might be interested more in the median or the middle number when they're first put in order. This way, one large or one small number won't have a dramatic impact on this measure of center. So for example, using our same data, the 1, 3, 3, 4, 4, 4, 5, 5, the median is going to be the value right in the middle. Well, if there's 8 values, the middle puts you between the 4 and the 4. And we know from our previous section when we made box plots, we would add those and divide by 2 to get our median value, which turns out here to be 4. And the big advantage of the median is that one extreme value does not impact the median as significantly as the mean. It's a little more stable. Now the third measure of center, and this is often used in categories or nominal data, is what is called the mode. The mode is the value that occurs the most often. And again, it's usually best for categories. If we're talking about the color of cars in the parking lot, we're not going to have an average of a blue point green car. That doesn't make any sense. But what we can do is say the most common frequent color car is blue or gray or whatever that most frequent one is. We can still look at mode in terms of numbers. We seem to be using this example data of 1, 3, 3, 4, 4, 4, 5. So let's keep using it. And what we see is the number 4 appears 3 times. It is the one that occurs the most often. So we will say that the mode is equal to 4. Those are our measures of center, the mean, median, and mode. But the problem with just measuring the center is it only tells us where the middle value is. It doesn't tell us kind of how all the rest of the data is behaving around the center. Is the data really spread out? Is it clustered close to the center? What's happening with the rest of the data? And that's why we also need some type of measure of spread. It tells us more than just the middle. It tells us how spread out the other values are. Not just where the middle is, but how's everybody else behaving around the middle. And the reason this is important is we can look at data such as these 3 data sets I'm going to put up here. And all of them, all of the following, have the same mean and median. The first data set's going to be 1, 1, 1, 5, 9, 9, 9. Both of that data set has a mean of 5. It also has a median of 5. But if I do another data set of 1, 2, 4, 5, 6, 8, 9, that data set has a mean of 5 and a median of 5. And if I do a data set of 5, 5, 5, 5, 5, 5, 5, that data set has a mean of 5 and a median of 5. There's no difference between these 3 data sets if I just look at the center. But the numbers are spread out quite differently. The first data set, the blue one, are spread out very far. The green one's kind of spread out evenly, and the red one has absolutely no spread in it at all. This is why we need a measure of spread. And the most basic measure of spread is what we call the range. The range tells us how much space there is between the largest and the smallest number. We take the large number and subtract the small number to see how far apart those extreme values are. So for example, with our data we've been playing with today of 1, 3, 3, 4, 4, 4, 5, 5, the range would be the big minus the small. 5 minus 1 equals 4. And so there is a space of 4 between all of these values. Now there's a problem with the range, though. The problem with the range is one extreme value could greatly impact For example, if there was also a 27 on this data set, 27 minus 1 would sound like 26. There's a large range between the numbers, when most of them are actually clustered quite closely together. So this is why we need a different, better measure of center. And one measure of center that might be better is what we call the interquartile range. It's often abbreviated as IQR for interquartile range. And the interquartile range you could think about as the range of the middle 50%. What we'll do is we'll take the Q3 and subtract the Q1 value. subtract the quartiles, and we see the range of the middle 50%, or how spread out the middle 50% is. And then we're no longer going to be impacted by an extreme outlier that's way too big or way too small for the rest of the data. So for example, with our data of 1, 3, 3, 4, 4, 4, 5, 5, we already said the median was between 4 and 4. The first quartile then, Q1, is between 3 and 3, which is just 3. And the third quartile, Q3, is between 4 and 5, which is 4.5. This means our interquartile range is 4.5 minus 3, or 1.5. And that might be a little bit of a better measure of the spread because it's only looking at the middle 50%. The extreme outliers are not going to impact the interquartile range. However, we still have a problem. And that problem is this interquartile range formula only considers two values, the Q1 and the Q3. It would be nice if we had some measure of spread that considered all the values and how spread out those are. And this gives rise to the most important measure of spread, the one we'll use a lot in this class, called the standard deviation. And the standard deviation attempts to measure what we call the average distance a point is from the mean. How spread out is the data considering all the data values? On average, how far are they from the mean? Now, with a population, we will use a Greek letter for the standard deviation, and that's the Greek letter sigma. And with a sample, we will use the English letter S to represent the sample. The formula for the standard deviation kind of builds on this idea that we want the average distance from the mean. So if I took any point and subtracted the mean, that would give me the distance it is from the mean. The problem is some of these will be positive and some of these will be negative. So if I add them up, it actually adds up to 0. So to avoid the positive-negative problem, what we'll do is we'll square each of the values before we take the sum and add them all up. Then we'll divide by the sample size, which turns out with standard deviation, and when we derive the formula, it's not exactly the sample size we divide by, but we'll divide by n minus 1. And the reasons for the minus 1 are beyond the scope of this course, so you'll just have to trust me to take an average distance from the mean with the standard deviation. We're going to divide by n minus 1. The problem that we still have, though, is we squared everything, so it's not really a true average. So to undo the square, we'll take the square root at the end of our formula. And we will say S is equal to that square root. And that is going to be an important formula for us in this course. Now, I do have one little caveat. Turns out that the formula for a population standard deviation is slightly different than S. The formula is. We're not going to worry too much about that different formula for the population because generally we always have a sample. We're always going to be taking sample standard deviations, which is this formula we've looked at here. So let's do an example. And let's start with a smaller example, and then we'll move to the bigger example that we've been seeing throughout this video. We'll start with the example 11, 13, 14, and 14. And I'll give you a hint. If you go through and calculate the mean of these values, the mean is going to be equal to 13. So what we'll do to get started is we'll list our values, 11, 13, 14, 14. And then we're going to have a column for every step along the way in this formula. The first step says take those x values and subtract the mean. Subtract 13. So 11 minus 13, I can even put a little 13 here. We're subtracting 13. 11 minus 13 is negative 2. 13 minus 13 is 0. 14 minus 13 is 1. And 14 minus 13 is 1. Then the formula says to square our values. So the x minus x bar, each of those values needs to be squared. Negative 2 squared is 4. 0 squared is 1. 1 squared is 1. And 1 squared is 1. Finally, the formula says to take the sum. So the sum of x minus x bar squared is equal to 4 plus 1, which is 6. Now I'll jump to the standard deviation formula, which says the square root of the sum, which is 6, divided by 1 less than the sample size, which is 3. 6 divided by 3 is 2, and the square root is 1.41. Now, similar to our formula with means, if the data is given to us with frequencies rather than individual data numbers, we need to do a slight adjustment to our formula. So if we have frequencies, the formula will slightly adjust to s equals the square root of the sum of x minus x bar squared. But before we take the sum, we have to multiply by the frequency and then divide by n minus 1. So let's take a look at an example where we do it with frequencies. And let's use that data set that we've been using where we know the x values were 1, 3, 4, and 5. And the frequencies of that were 1, 2, the number 4 appeared 3 times, and the number 5 appeared twice. Now, we already know that x bar, the mean, is 3.625. We would have had to find that first if we didn't know that. But since we do, now we'll make another column for x minus x bar. Taking the x, the number 1 minus 3.625 is negative 2.625. 3 minus 3.625 is negative 0.625. 4 minus 3.625 is 0.375. And 5 minus 3.625 is 1.375. Next, the formula says we need to square that x minus x bar. We're going to square each of these numbers. So 2.625 squared, and I'm going to round to 2 decimal places, is 6.89. 0.625 squared is 0.39. 0.375 squared is 0.14. And 1.375 squared is 1.89. Now, if we didn't have frequencies, we would just add this column up. But because we have frequencies, we need to take this column, the x minus x bar squared, and multiply by those frequencies. So the 6.89 needs to be multiplied by 1 to get 6.89. The 0.39 needs to be multiplied by its frequency of 2 to get 0.78. 0.14 times 3 is 0.42. And 1.89 times 2 is 3.78. And that's what we want to sum. We want to get the sum of x minus x bar squared times the frequency. And when we add up that column, you should end up with 11.87. Now we plug into our formula for s. S is the square root of that sum we just found is 11.87. Divided by 1 less than the sample size. You could add the frequencies together to find out that the sample size is 8. Or you might remember that because we've been working with this for quite a while. 1 less than the sample size is 7. So the square root of 11.87 divided by 7 is 1.30. So on average, these points are about 1.30 units away from the mean of 3.625. Gives us an idea of the middle and how spread out the data actually is. Now, the standard deviation is actually quite nice because it gives us a way to compare data based on how many standard deviations we are from the mean. Standard deviations measure distance from the mean. And in statistics, we will use a very important variable to represent the number of standard deviations we are from the mean. That variable is always going to be z. Z is the number of standard deviations from the mean. And we actually have two formulas that use z. They're both really the same formula. The idea is z is the number of standard deviations from the mean. So we'll take the value we're working with. We want to know how many standard deviations x is from the mean. Well, first we need to know the distance to the mean. So we'll subtract the mean, or x bar, and then we'll divide by s, or the number of standard deviations that is. That's our main formula for z. Now, sometimes we have the opposite information, and we want to know what is 3 standard deviations from the mean. We know z. We want to be 3 standard deviations from the mean. What value is that? And so we can solve this equation for x. And when we do, we get x is equal to the mean plus the number of standard deviations times the standard deviation. And so this formula, it's really the same formula, it's just been solved for x, will tell us the number of standard deviations is what value. Let's do some examples. Let's say for our data, 1, 3, 3, 4, 4, 4, 5, 5, we want to know how many standard deviations from the mean is the median. Well, we've already found all these important values. We found the median is equal to 4. Also, earlier, we found the mean was equal to 3.625. And also, earlier, we found the standard deviation is equal to 1.3. So if we want to find out how many standard deviations the median is from the mean, the medians are x, the mean's the x bar, and the standard deviation is s. So z, the number of standard deviations, 4 is, we subtract the mean of 3.625 and divide by the standard deviation of 1.3, and we find the median is 0.288 standard deviations from the mean. Or we could ask a similar question for the same data. What value is 2 standard deviations below the mean? We already know the number of standard deviations. So 2, that's actually going to be our z, the number of standard deviations below the mean. And because we want to be below the mean, we will use a negative number to make it below the mean. So we're looking for the x this time. What is that value of interest? So x is equal to the mean, x bar of 3.625, minus 2, because we have a negative 2 standard deviations below the mean, times the standard deviation of 1.3, and that gives us 1.025. Now, it turns out that we can say 95% of our data generally falls within 2 standard deviations of the mean. If it's more than 2 standard deviations from the mean, we say those values are unusual or extreme values. We call those extreme values outliers. And these outliers are values far removed from the rest of the data. For example, if I have the numbers 1, 3, 3, 5, 87, 87 is far removed from the rest of those values. It's an outlier. And the outlier can either be large or small. And we actually have 2 methods for calculating outliers, and they generate very similar results. So neither one is necessarily better than the other, but I want to show you both of them. The first one is called the interquartile range method. And the idea behind this is we cannot be more than 150% or 1.5 times the IQR from the edge of the box in the box and whisker plot. The idea is anything below the first quartile minus 1.5 times the IQR, or anything above the third quartile plus 1.5 times the IQR. Anything that's above or below those numbers becomes an outlier. So for example, let's say we've got the numbers 2, 3, 5, 6, 7, and 14. Now, the median's right in the middle. But what we're interested in with the interquartile range is the middle below the median. The first quartile is 3. and the third quartile is 7. So the interquartile range is 7 minus 3, or 4. This means an outlier is anything below the first quartile, 3, minus 1.5 times the interquartile range of 4. That gives us 3 minus 6, or negative 3. Anything below negative 3 would be an outlier, which there's nothing in this data set below negative 3. But also anything above the third quartile, 7, plus 1.5 times the interquartile range. 7 plus 6 is 13. Anything above 13 becomes an outlier. And you notice 14 is right on the edge there. And so we will say, based on that, 14 is an outlier. It lies outside of the majority of our data. Now that's the interquartile range method. I said there's a second method. It's based on the standard deviation. The standard deviation method says that anything that is more than 2 standard deviations from the mean is an outlier. Which brings us back to that example that led into this discussion. So, actually, let's first define this clearly. Let's do anything below x bar the mean minus 2 standard deviations, or anything above x bar the mean plus 2 standard deviations is considered an outlier. So for example, we had our data of 1, 3, 3, 4, 4, 4, 5, 5. And we found out already that the mean of this data is 3.625. And we also found out the standard deviation of this data is 1.3. So an outlier would be anything below the mean, 3.625, minus 2 standard deviations. (3.625) minus 2 times 1.3 is 1.025. And we'll recognize there that we do have a value below 1.125, or 1.025. It's just a little below, but it is below. Here, 1 is an outlier. We also have to check above. So we'll do the 3.625 plus 2 standard deviations, or 2 times 1.3, which gives us 6.225. Nothing above 6.225, so the only outlier we have here is the number 1. So we've covered quite a bit in this video. We talked about measures of center, the mean, median, and mode to estimate where the middle of the data is. We talked about measures of spread to see how spread out we are around the mean or the center, using the range, the interquartile range, and the most important ones, the standard deviation. And then we also looked at some uses of the standard deviation to see its distance from the mean, finding outliers or identifying outliers. So lots to take a look at on the assignment. Take a look and practice a few. We will discuss them more in class. We'll look forward to seeing you then. All Our second unit is going to focus on probability and how to calculate various probabilities in different contexts. So we're going to start out with basic probabilities. And so that question we're going to answer is, how do we calculate basic probabilities? And as always, we need to start off with some vocabulary to make sure we understand what we're talking about. The first vocabulary word we need to know for probabilities is what is called the sample space. The sample space is a list of all possible outcomes. So for example, if I was to flip a coin, the sample space would be all possible outcomes. I could get a heads or I could get a tails. Which begs the question, what is an outcome? So let's define an outcome really well. An outcome is just the result of an experiment. So an experiment might be flipping a coin. An outcome would be just maybe heads or just tails. And hence the sample space is all of the outcomes, heads and tails. When we're looking at the number of outcomes that occur in a sample space, what we're really interested in finding is some type of probability, or the chance that an event will occur. And what we really end up with is a scale from 0 to 1, where 0 means the event certainly will not happen. Not going to happen. And then the number 1, the maximum probability, is it is certain to happen. And then you could get any decimal in between. So if I ended up with like 0.5, that would be right in the middle, so it's equally likely to happen or not happen. So if the probability is 0.001, it's probably not going to happen, but it could happen. If the probability is 0.95, it probably will happen because it's closer to 1, but it might not happen. The scale from 0 to 1 is our probability. And there's two types of probabilities that we're going to be looking at. The first is called the theoretical probability. Which basically says what we expect to happen or what should happen. And the way we calculate a theoretical probability is we say that the probability of some event E is equal to the number of outcomes that we are looking for divided by the entire sample space, or how many things could occur. That's our basic probability formula. So for example, if I flip a coin and I want heads, we would say the probability I get a heads is the number of outcomes. There's only one outcome on a coin. Out of the sample space, there are 2 possible outcomes on a coin, heads or tails, and then I would convert that to a decimal. In this course, we'll always use decimals for probabilities to get a probability of 0.05 of getting a heads. That's theoretical probability, what we expect to happen. The other type of probability is called empirical probability. And that is the chance of something happening based on our observations of some experiment. What happened in an experiment? So this is the example of maybe I flip a coin 500 times and I end up getting 257 heads. Because in actual practice, the probabilities aren't perfect. I'm going to get a few more heads or a few more tails. It's not going to be exactly even. And so in this case, the probability of a heads as an empirical probability or an observed probability is 257 out of 500, which is 0.514. There's usually going to be a slight difference between the empirical probability and the theoretical probability. But that difference can be made smaller using what's called the law of large numbers, which basically says that the more trials I do, the more trials done, the closer the empirical probability is to the theoretical probability. If I were to do 1,000 trials, this would be closer to 50%. If I would do 1,000,000 trials, flipping a coin would get closer to 50%. More trials, the closer they're going to be. Now that's really basic probability, but we do have some specific probability formulas to help us calculate some more involved situations. And these 3 formulas we're going to look at are very closely related. They really come as a group. There's no one you should learn before the other because they're all so closely related. So we'll do our best to define them one at a time when really they all come as a group. And the first is what we're going to call the conditional probability. In a conditional probability, we write it as the probability of B given A, or with a vertical line between B and A. And what that means is that is the probability of B given A has already occurred. That's a conditional probability where we have some information and that's going to change the probability of B. The formula for a conditional probability is the probability of B given A is equal to the probability that both occur, A and B, divided by the probability of the given information. In this case, the probability of A. That conditional probability formula will be very important to us. We'll do an example here in a minute. Let's go on to the second type of probability we need to know, and that is the AND probability. The probability of A and B is the probability that both occur at the same time or together. And the formula for the probability of A and B comes from the conditional probability. If we multiply both sides of the conditional probability formula by the denominator, the probability of A, we end up with the probability of A times the probability of B given A has already occurred. And that is the that is the AND probability formula. The third formula we need to know is the OR formula, the probability of A or B occurring. And that is the probability of A occurring, or B occurring, or both occurring, one or the other or both. And the formula for an OR, the probability of A or B, is we're going to add the probabilities together. The probability of A plus the probability of B. The problem is this counts the AND or the overlap twice. It counts it in the probability of A and it counts it in the probability of B. So we have to subtract off the overlap or subtract off the probability of A and B. So it's not double counted, it's only counted once. And that gives us our formula for the OR. Those are our three probability formulas. The conditional probability is the probability of both divided by the given information. The AND probability, with AND we multiply the probabilities together, given the first one's already occurred. And with an OR probabilities, we add them together, subtracting off the overlap. So let's do an example, number 4. Let's say we have 3 blue cards numbered 1, 2, and 3. And we also have, let's write 3 out as a number since it's starting a sentence. 3 blue cards numbered 1, 2, and 3, and I have 2 yellow cards numbered 1, 2. A, we're going to find the probability actually, let's just write as a probability statement. We're going to find the probability that I get a blue card given the card is even. With a conditional probability, since I know the card is even, we're not dealing with all 5 cards anymore. We're just dealing with the even cards. So we find the probability of both blue and even. From the blue cards, there is one that is blue and even. So there's one of them out of the 5 cards, divided by the probability of the given information. The given information is that it's even. There are 2 even numbers out of 5. Now what's nice is generally those denominators will divide out, and we're just left with 1/2, or 0.5. So that means if I know I've got an even card, the probability is 50% that it's going to be even. That's conditional probabilities. Let's find the probability that I get a blue card and an even card. Now this is looking for the probability that both occurred at the same time, blue and even. Of the blue cards, only one of them is blue and even. Out of the total cards, now we're looking at the total sample space, of 5. And so the probability that it's blue and even is 0.2. There's only a 20% probability that it's both blue and even. What about the probability that it's blue or even? For blue or even, now we're looking for how many are blue. The first option, there are 3 blue cards out of 5, plus how many are even. There are 2 even cards out of 5. But then we need to subtract off the overlap, the ones that are blue and even. Blue and even, we know there's only 1 out of 5 that's both blue and even. So 3 plus 2 minus 1 is 4/5, which means we have a probability of 0.8 that it is blue or even. I want to do one more example that kind of illustrates the AND formula maybe a little bit better. And that is finding the probability that if I draw 2 cards with replacement, actually maybe I should write this out. Probability I draw 2 blue cards without replacement. What I'm really saying is, what's the probability the first one is blue? And what's the probability the second one is blue? Well, for the first one to be blue, the probability of the first event, there are 3 out of 5 that are blue. Then we multiply by the second event. The probability that I get a blue, given the first one was already blue. So now one of the blues is gone. Maybe the 2 is gone. Now there's only 2 blues left. There's only 4 cards left. And when I multiply that across, we end up with 0.3 is the probability we get 2 blues without replacement. 30%. So that's what we're looking for with that AND formula. The second part, the AND, we adjust the probability to assume the first one already occurred. Those are our basic probability formulas, but there are 2 vocabulary concepts that are related to those that I want to make sure we are familiar with. So the first one of those 2 is what are called independent events. When 2 events are independent, what that means is one occurring does not change the probability of the other occurring. The opposite of this would be dependent events. And if we think about the blue cards that we drew without replacement, the second probability was 2/4. That second probability had changed from the first probability because one occurring changes the other one's chance of occurring. Because there's fewer cards left. There's fewer blues. Now, the way we show things are independent, we can show this in one of 3 ways. And it doesn't matter which one of these ways we use, so we'll just pick the one that's most convenient for our context. The first is we can show that the probability of A, given that B has occurred, if B is not going to affect its probability, it should still be the same as just A occurring by itself, because B has no impact on it. The opposite is also true. We could say the probability of B given A is going to be just equal to the probability of B, because A occurring has no impact on it. Or the third method we can look at is the probability of A and B. The probability of both of them occurring is equal to just the product of the individual probabilities, because the given part doesn't change. So for example, let's say in a class, 20% of students are left-handed. Five percent of students are earning an A in the class. Good job to those 5%. But only 1% of students are left-handed and earning an A. Are these events independent? Is there a relationship between left-handedness and earning an A? Well, we'd have to look. What's the probability that they're left-handed? We're told the probability they're left-handed is 0.20 or 20%. The probability that they're earning an A, of all students, 5% are earning an A, so the probability of earning an A is 0.05. We're also told the probability of the students who are left-handed and earning an A, both of them together, is 0.01. Well, we can use either one of the three formulas for showing things are independent. It's probably going to be easiest in this context to use the third, because we have all of those pieces. So the probability of A and B, the probability of left and receiving an A, should be equal to the probability of being left-handed times the probability of receiving an A, if they are in fact independent. Well, the probability of A and L is 0.01. The probability of left-handed is 0.2. The probability of an A is 0.05. And sure enough, we get those are equal to each other. Because they're equal, we'll say, therefore, they are independent events. If it wasn't equal, we would say the opposite, or that they're dependent events. So that's the first concept, the idea of independent versus dependent. The second concept that I want to wrap up with today is the idea of mutually exclusive. Two events are mutually exclusive. That means both cannot occur at the same time. Essentially, what we're saying is the probability of A and B is equal to 0. An example of this would be if I were to roll a die, a standard 6-sided die, and we're going to let O, actually I'm going to use the letter D because O is a bad letter for math. D is going to represent an odd less than 4. B is going to represent a number bigger than 3. So what you see is D, the odds less than 4 are the numbers 1 and 3. That's kind of the sample space of D. And B, the event B, is everything bigger than 3, which is 4, 5, and 6. These two have nothing in common. You can't both be an odd less than 4 and a number bigger than 3. Because we can't have both together, we say they are mutually exclusive. In other words, the probability that we have an odd less than 4 and a number bigger than 3 is equal to 0. That never happens. So a little vocabulary as we wrap up with mutually exclusive. Both can't occur at the same time. Independent, one occurring does not affect the other occurring. But the big thing that we're looking at today are these probability formulas, conditionals, ands, and ors. Take a look at the homework assignment to practice a few of these. We will try a few more in class and answer any questions you might have then. Now that we're comfortable working with basic probabilities, we're going to look at different ways we can organize our probabilities and information. In today's video, we're going to look at the question, how do we organize probability information in a table? Specifically, we're going to be in the context of what is called a contingency table, which is basically just a table that lists results in relation to two variables. These tables and this information will make calculating probabilities easier. And what makes it easier is quite often we will add a column and row for totals. So for example, let's say we've done a survey and we're comparing whether or not people have speeding tickets in the last year or no speeding tickets in the last year. And we're going to break this up into 3 groups. The first group are going to be our younger drivers, the under 21 drivers. And then we're going to also look at the 21 to 25-year-old drivers. And then we'll also look at the over 25 drivers. And the survey's conducted, and there's 82 under 21s with a ticket, 17 without a ticket in the past year. For the 21 to 25s, there were 39 with a speeding ticket and 27 without. And for the over 25, there's 18 with a speeding ticket and 61 without. Now, with this contingency table, it's going to be helpful that we're going to add an extra row and an extra column if it's not there already. That's going to give us the totals. And these totals are going to make calculating individual probability questions much more efficient. So if we total the under 21, we see we have 99 surveyed. The 21 to 25, total that, we get 66 surveyed. Total the over 25, we get 79 surveyed. Working across the rows, 82 plus 39 plus 18, there's 139 people surveyed who got a speeding ticket in the last year. The no tickets, 17 plus 27 plus 61 is 105. And for the totals, 99 plus 66 plus 79 gives us 244 people total in the survey. And a good way to check that that total's correct is if we add the other combination, 139 plus 105, that should also equal the 244, which it does. And so that, what we have there as that example, is a contingency table. Now we're ready to find some probabilities off this contingency table. For example, if I want to know the probability that someone is 21 to 25, I can see very quickly on my contingency table that there are 66 people in the 21 to 25 range out of a total of 244 people. And so when I divide 66 by 244, we can quickly get our probability of 0.2705. We could also do maybe the probability that someone has no tickets. Very similar, I'd say, well, no tickets, the total there is 105. Out of the grand total, which is 244. And when we divide 105 by 244, we get 0.4305 for our probability. We can also do ands, and we can do ors. We can find, let's combine these together, the probability that someone's 21 through 25 and has no tickets. Well, the 21 to 25 and have no tickets are when both of those occur together at the same time. That's where they overlap. Here in the middle, we have 27 people who are of no tickets, and they're 21 to 25. Out of the total of the whole group is still 244. And so when I divide 27 by 244, we get 0.1107. And we can change that to an or. We can find the probability that someone's 21 to 25 or has no tickets. And if you remember, the or formula says we have to add the individual pieces and then subtract where they overlap. So 21 to 25, there's 66 of them. Plus the no tickets, there's 105 of them. But we have to subtract where they overlap because these 27 where they overlap have been counted twice in both the column and the row. So when we subtract off the 27 out of the 244, when we do that math on our calculator, we get 0.5902, about a 59% probability they're one of those two. We can even do given probabilities. Let's do the probability that we're in that 21 to 25 range. Let's get rid of these circles we don't need. Given we know the person has no tickets. Well, with a given probability, we are looking for both of them, or the overlap, divided by the given information. So where they overlap, 21 to 25 and no tickets, they overlap with 27, but we're going to divide by the given information. This time it's not the 244 because we've shrunk our sample size. Now we're just interested in those that have no tickets. We're only interested in that 105. And so with the given information shrinking the sample size, now the probability is 0.2571. We can switch that and see how that probability compares. The probability they have no tickets, given they're between 21 and 25 years old. You might pause the video and see if you can figure this one out on your own. With a given probability, we need to find where they overlap, divided by the probability of the given information. They overlap, again, no tickets in 21 to 25 with these 27 individuals. However, now our sample space, the given information is just the 21 to 25 years old. and that's the 66. So we'll do 27 divided by the 66 to get our probability of 0.4091. And you can see how we move through each of these probabilities at a much greater accelerated pace when we have the contingency table to organize our data for us. That's the nice thing about the contingency table. One more thing I want to look at, though, is we have this vocabulary word from our previous video of independence. So I want to know, are being 21 to 25 and having no tickets independent? Does that mean being 21 to 25 has no impact on whether or not you had a ticket in the past year? Well, we talked about there being 3 different formulas we could use in order to show this. One of those 3 formulas says that a given probability should not change the probability if they are in fact independent. In other words, the probability there being 21 to 25, given they have no tickets, should be the same as the probability of just being 21 to 25 if they're independent, because the tickets shouldn't impact that at all. Well, we just found both of these pieces. The probability of being 21 to 25 given we have no tickets is actually here in number 5. That was 0.2571. And the probability of being 21 to 25 we found in part 1, that's 0.2705. And we see that these guys are different. Therefore, the probability is changed once we have given information and shrunk down the sample size. That means these 2 variables are actually dependent on each other. So all we're looking at today is organizing our probability information in a contingency table and taking a look at how that helps facilitate calculating the actual individual probabilities. It also gives us an opportunity to practice more with and, or, and the given probabilities. So take a look at these on the homework assignment. Come to class ready to discuss them and work with these contingency tables a little bit more. Today we're going to continue our work with representing probabilities visually using what are called tree diagrams, and we'll also take a look at Bayes' theorem. The question, though, that we're attempting to answer is how do we visually organize conditional probabilities? How do we visually organize conditional probabilities? And really the best way to organize a conditional probability is using what is called a tree diagram. And a tree diagram basically has a branch for each outcome. And then each branch produces a conditional outcome from that outcome, from that outcome. And then to find final probabilities, we can multiply down the branches for final probabilities. For example, let's say we have an urn with 5 blue and 3 green marbles. And you will draw out 2 marbles without replacement. We are being asked to make a tree diagram to model the possible outcomes and probabilities. So what we need to do is we're going to draw a branch on this tree for every decision point. So the first decision point is the very first draw. So this represents the first draw. And off that first draw, we could end up with a blue marble, or we could end up with a green marble. Now you can see there's a total of 8 marbles, 5 plus 3. So the probability of getting a blue marble on the first draw is 5 out of 8. And the probability of getting a green marble on the first draw is 3 out of 8. But we're not done there because we're still going to draw another marble. And that marble could be either blue or green. And it doesn't matter which color we got first, we're going to have the same possible outcomes. It could be either blue or green on this second draw. And so you can kind of see that if you follow a draw down, if we want a green first and a blue second, we'd go down the green line and the blue line, and that represents green first and blue second. Or if I wanted a blue then a green, we would go down the blue line first and then the green line second, and we'd end up with the blue-green combination. But first, let's fill in the individual probabilities, because on the second draw, things have changed. If we go down the left side, where the blue was drawn first, and if we want a blue on the second draw, there's no longer 5 blues left to pick from. There are only 4 blues left to pick from, and there are only 7 marbles left. So we only have a 4 in 7 chance of getting a blue marble on the second draw, given the first draw was blue. Similarly with the green option, if we want blue then green, tracking that down, there are still 3 green marbles left, but now the total is only 7 marbles because 1 has been drawn out. A blue one has been drawn out. Similarly, on the right side of the tree diagram, if green is drawn first and then I want a blue on the next draw, there are 5 blues to pick from out of the 7 marbles that are left. But with the green, there are only 2 marbles that are green left out of the 7 marbles that are left. Now, to get my final probabilities for each of these possible outcomes, we just have to multiply down the chain. So if I want a blue-blue outcome, what I'll do is I'll multiply the 5/8 times the 4/7. And when I multiply 5/8 times 4/7, we get a probability of 0.3571. Now, if I want blue then green, we multiply down those probabilities to get the blue-green possibility. 5/8 times 3/7 is 0.2679. Going down the next path, we go green, then blue. So if we want a green marble, then a blue marble, that probability is 3/8 times 5/7, which turns out to also be 0.2679. I think the other one was 2679 also. I wrote it down wrong. The last track is going down the green and then the green. So if we want 2 green marbles, green then green, we'll multiply the 3/8 times the 2/7 to get the 0.1071. And now we see all the different possible probabilities for drawing 2 marbles out of this urn without replacement. And we can use that table to find things like the probability that both are the same color. Well, both the same color would be a blue-blue or a green-green. And then we subtract the overlap, but there's certainly no overlap with blue-blue and green-green. So we'll just add those together. And actually I should do this in red. 0.3571 plus 0.1071 will give me the probability that I get 2 are the same color of 0.4642. One more example. What's the probability that I get at least 1 blue? Now, I could do this a couple ways. One way is I could say these first 3 options each have at least 1 blue. But that's a lot more work than saying, let's look at the complement and let's subtract off the only one that's left from the absolute probability of 1. We know all the probabilities are 1, so we subtract out the probability that doesn't satisfy what we want. If we subtract off the 0.071, we'll end up with our probability of at least 1 blue of 0.8929. And that's how using a table can greatly facilitate our conditional probabilities and their various calculations. But one very important application of using these tables is to facilitate what is called Bayes' theorem. And Bayes' theorem is a way to find a conditional probability, like the probability of B given A, using known values of the probability of the probability of A given B. In other words, the given values are backwards from the given values that we want. Now, Bayes' theorem officially says that the probability of B given A is equal to the probability of both, the probability of A and B, divided by the probability of the given information, or the probability of A. But we might not know the exact probability of A, but we do know the probability of A given B, and we can add to that the probability of A given it's not B. In other words, we combine all the A probabilities together to build that denominator. And that last part, that not B, it may be several options. So we might need to add 3, 4, 5, 6 things that are the not B's. But we have to basically add all the combinations of the probabilities of A given the other stuff. This formula is not worth memorizing because it is always easier to do this on a tree. The tree makes this easy. And I'm going to show you what I mean with a couple examples. Let's say a marketing company predicts 90% of new products are profitable. However, the marketing firm isn't perfect. Only 70% of those products predicted to be profitable actually are. In addition, those predicted to be not profitable (20%) actually are profitable. So let's say we've got some product and it turns out that it was profitable. That's given to us. Given a product was profitable, what is the probability? It was predicted to be profitable. So it was profitable. What's the probability it actually was profitable? Let's make a tree to model this. First, the marketing firm looks at it and they say, yes, it will be profitable or not. We are told the company predicts 90% of their products will be profitable. Therefore, the complement, 10%, must not be profitable. And that's actually not just profitable, but that's a prediction of profitable and a prediction of not being profitable. Because then the next branch we're going to look at, it actually is profitable or it's not profitable. Were they right or wrong? It actually is profitable or it's not profitable. We are told 70% of those that are predicted to be profitable actually are. So if I go down that they're predicted to be profitable, they actually are, 70% are, and the rest, 30%, are not. Of those that were predicted to be not profitable, going down the not line, 20% actually are. So 20% is on the right side, and the rest, 80%, are not. Going down the lines, multiplying 0.9 times 0.7, the first branch is a 0.63% probability. 0.9 times 0.3, there's a 0.27% probability. Next branch, 0.1 times 0.2 is 0.02. And 0.1 times 0.8 is 0.08. So for my actual probability statement, it's asking, what is the probability it was predicted to be profitable? The probability that we predicted it was profitable, given it actually was profitable, given it actually is profitable. Well, we know conditional probabilities are the probability of both divided by the probability of the given information. So the probability of both, where it's predicted to be profitable and it actually is this far left branch here. That's 0.63. That is going to be our numerator, the 0.63. The denominator then is going to be the probability of the given information. The given information is that it is profitable. The is occurs in two locations. The is the left side of both branches. The is profitable. Both of those together make up my sample space. So I take the given information and I add those pieces together, 0.63 plus 0.02, and that gives me 0.63 out of 0.65, which gives me a probability that it was predicted to be profitable, given it actually was, of 0.9692. And that is how Bayes' theorem helps us reverse the given probabilities in our table. Let's do one more of these Bayes' theorems with a little bit more detail in it. Let's say Bob drives to work %40 of the time. He takes the bus 50% of the time. He walks 10% of the time. So that's 100% of the time how he gets to work. The probability he will be on time is 90% if he drives, 60% if he takes the bus, and 30% if he walks. If Bob arrives late, that's our given information. Bob has arrived late. What is the probability he took the bus? Well, let's make our tree diagram to summarize what happens. He actually has three things that can happen initially. He can drive, he can take the bus, or he can walk. In fact, we're given probabilities that he drives 40% of the time, takes the bus 50% of the time, and walks 10% of the time. Once he does that, he will be either late or on time. Doesn't matter which method he takes, he will be either late or on time. He will be either late or on time. We're told about the on-time half. If he walks, if he drives, going down the drive, he will be on time 90% of the time, or 0.9, which means he's late the rest of the time, 10%. The bus, we're told, he is on time with the bus 60% of the time, which means he's late the rest of the time, 40%. But if he walks, he's on time 30% of the time, and he's late the rest, or 70% of the time. Multiplying down the chain then, driving in late is 0.04. Driving in on time is 0.36. Busing late is 0.20. Busing on time is 0.30. Walking in late is 0.07. Walking in on time is 0.03. We are asked to find the probability that he took the bus given he arrived late. I like to start off by marking all of the given information. So given he arrived late. Late was our left branch. Late, late, late. What we're looking for is the probability that he took the bus and was late. So what we're looking for is the 0.20. Now we're ready to build our probability. The probability of both, bus and late, is that 0.20. But divided by the probability of the given information. The given information is that he was late. We marked that as a 0.04 plus a 0.20 plus a 0.07. So we have 0.20 out of 0.31, which when we divide those, you get 0.6452, almost a 65% chance that Bob took the bus, given he's arriving late. That's Bayes' theorem, and that's how we can use tree diagrams to help us with conditional probabilities. So take a look at a few of these on the homework. We will discuss these more in class, and I'll look forward to working with you then. Now that we're comfortable working with and finding probabilities, we're ready to talk about discrete probability distributions, and then later we'll talk about continuous probability distributions. First, I want to make sure we know what question we're trying to answer. The question for today is, what are discrete probability distributions? And to set this up, we're going to be working with this idea of finding what's called the probability distribution function. Often this is just abbreviated as PDF, the probability distribution function. And these probability distribution functions have two key characteristics. The first is, for this PDF, each individual probability is between 0 and 1. In addition, if we took all the probabilities and added them together, they would sum to 1. Now, often we'll organize these probability distribution functions by what we call random variables. And a random variable just describes the outcomes of an experiment. Now, a discrete probability distribution is used with countable or discrete outcomes. For example, if we let the random variable x represent the number of movies watched last week, that's a discrete random variable because you only can watch a certain number of movies. We can't do decimals. You either watched it or you didn't. So because this is a countable result, it's a discrete result, and we can collect discrete data. A survey is conducted, and it is found that 40% of the respondents watched 2 movies last week. 50% watched 1 movie. And the rest watched no movies. We can summarize the PDF, or the probability distribution function, in a table. And in this table, all we have to do is list the possible results. I spelled countable wrong. Forgot the T in countable. Sorry about that. All we have to do is list the possible results and their associated probabilities. So x is the random variable. People watched either 0, 1, or 2 videos. And then we'll make a column representing the probability that x occurred. We're told that 40% watched 2 movies, so the probability is 0.4. 50% watched 1 movie. The probability is 0.5. We're not told what percent watched no movies, but if we add what we have together, we see we've covered 90% of the respondents. So there's only 10% left to make it equal 100%, and that must be the 0. And this becomes our probability distribution table. Now, what's nice about being able to organize all the countable possibilities is it allows us to consider the expected value, which is also called the mean, and the standard deviation of the probability distribution function, or of the PDF. And the formulas for finding these expected values and standard deviations are very similar to the formulas we had for means and standard deviations from chapter 1, but using the probabilities instead of the frequencies. First, the expected value. The expected value is the long-term average, or mean, of the PDF. In other words, if you ran lots and lots of experiments and took the average of the results, what would that expected value or that average result be? And the formula for the expected value, or the mean, is equal to the sum of all the x's times their individual probabilities. This is a good formula to know. So for our example, where we had our number of movies being 0, 1, and 2, and their individual probabilities being 0.1, 0.5, and 0.4, we can find the average number of movies watched in this survey by making an extra column for x times p of x, multiplying the x value times its probability. 0 times 0.1 is 0. 1 times 0.5 is 0.5. And 2 times 0.4 is 0.8. And if I add those together, that will give me the sum of the x's times the p of x's, which is 1.3. This tells me that the average student, or survey respondent, watched 1.3 videos last week. The expected value. If I took a whole bunch of students over and over again, I would expect the average to be 1.3. And again, similar to how we found the standard deviation with frequencies, we can find the standard deviation, or the spread of our random variables. using the formula that sigma, the standard deviation, is equal to the square root of the sum of the difference between the mean and the value squared times the probability of the values. Again, this would be a good formula to know how to use. And basically, like we did before with finding standard deviation, we're going to make an extended table. So again, our values for the movies were 0, 1, and 2. Their individual probabilities were 0.1, 0.5, and 0.4. And we're going to start to build this formula by adding columns. The first part of the formula wants the difference between the mean and the value. So our mean, remember, we just found out that the mean was equal to 1.3. We did that in a previous section. So 1.0 minus 1.3 is negative 1.3. 1 minus 1.3 is negative 0.3. And 2 minus 1.3 is positive 0.7. But then our formula says we take that difference and we square it, make them all positive. 1.3 squared is 1.69. 0.3 squared is 0.09. And 0.7 squared is 0.49. But then the formula says we need to take that square of the difference and multiply it by the individual probabilities. So we'll take that green column times the second black column. 1.69 times 0.1 is 0.169. 0.5 times 0.09 is 0.045. And 0.4 times 0.49 is 0.196. And our formula says, let's find that sum. Our formula wants the sum of the difference squared times the probability, which is equal to 0.169 plus 0.045 plus 0.196 is 0.41. And we're told the standard deviation is the square root of that value, the square root of 0.41, which is equal to 0.6403. So now we know our probability distribution function. That table that we made has an average expected value of 1.3 and a standard deviation of 0.6403. So that's what we're looking at today, is we're taking a look at how to work with these probability distribution functions, specifically the discrete ones. And then in our next few videos, we'll look at some specific types of discrete probability distributions. But for now, take a look at practicing a few of these on the homework. We'll discuss them further in class. Good luck. This video is going to take a look at a special type of discrete distribution called the binomial distribution. And the binomial distribution helps us calculate what is the probability of x successes out of n trials. In other words, I'm going to conduct a survey, and maybe I want to see how many people support a particular political candidate. I want to know what's the probability that 100 out of 200 of them, or 50%, support my candidate. That is what we call a binomial distribution. And a binomial distribution has the following characteristics. First, there is always a fixed number of trials. I'm going to interview a certain number of people, or I'm going to run a test a certain number of times. And when I run that experiment or that survey, there are really only two options. The two options are success, and we usually use x to represent the number of successes, or failure. And it's important to note, as we define success and failure in our experiment, there is no moral or good-bad judgment to the word success. And quite often, success is a bad thing. If I'm in quality control, I might say a success is a defective part, and we're looking at how many successes there are. In that case, success is a bad thing. So there's no moral or ethical standard for success. Success is just what we are looking for. So try to avoid pinning positive and negative emotions to that word. With those two options of success and failure, we'll often talk about P, which is equal to the probability of a success. And if x is the number of successes, and we'll use n for the number of trials, x divided by n would be the probability of that success. Then we also have this letter Q, which is the probability of failure, the opposite. And since there's only two options, success and failure, we can quickly calculate Q to be equal to 1 minus the probability of a success. It's the complement. So the distribution itself the distribution for the binomial is, we're going to say that x tilde, or the little squiggly line, b for binomial, and then in parentheses we'll do n, the number of trials, and p, the probability of success. And we'll use this notation to represent how the x is distributed. It's distributed as a binomial with n trials and a p probability of success. And if we are in the context of the binomial, we have some shortcuts to help us calculate things like the expected value. The expected value, or the mean of the distribution, is simply going to be the number of trials times the probability of success. And that seems to make sense. If I have 30 trials and a 10% chance of success, I would expect to be successful 10% of 30, or 3 times. We can also use a shortcut formula for the standard deviation of the binomial. And the standard deviation, or sigma, is equal to the square root of NPQ. Now, we could go through the formulas for mean and standard deviation like we did with just the generic discrete probability distributions. It just gives us the same answer, so we might as well use this nice little shortcut. And actually, before we move on, let's go ahead and highlight these 3 pieces, because these 3 pieces are foundational to doing our binomial distribution. Let's look at using the binomial distribution. And you notice I never gave the formula for how we actually calculate binomial probabilities. That's because we're going to cheat and we're going to use the calculator to do all the work for us. In the calculator, the steps that you're going to push on the TI-83 or 84 calculator is you'll hit the second button, and then you're going to hit the what's called the distribution button, which is above the button that actually says vars. So when you hit the second, it gives you the command above the button. the distribution function is what we want to use. And we're going to use the binomial distribution. So then we will scroll down, and there's two options for the binomial. The first option is called the binomial PDF, and it opens a parentheses. That one gives us the probability of exactly x successes. The one below it we'll also use is called the binomial CDF. And the C in there stands for a cumulative distribution function. That tells us the probability of up to and including x successes. In other words, with the CDF, if I'm interested in the number 3, if I want 3 successes, the PDF will tell me exactly 3 successes. The CDF will tell me what's the total probability of 3, 2, 1, or 0 successes. All the probabilities up to and including that number. Now, after the parentheses, we do have to enter in the key information. Some calculators have some software that it'll prompt you for the information. But if it doesn't prompt you, you just need to know that the format for both of these is exactly the same. We will use the binomial, and I'm going to do a star because it could be the PDF or the CDF. Both of them are the same. Then the first number you enter will be the number of trials, comma, the next will be the probability as a decimal, comma, then you'll do x, or the number of successes, and close the parentheses. And that's how we can use the binomial distribution on the calculator, and it's probably easiest to see with an example. And according to the website citydata.com, in Moses Lake, 7.9% of workers carpool to work. You're going to go out and you're going to conduct a sample of 41 workers. First thing we want to do is identify what is the distribution. For this situation. The distribution of our x, or our random variable, is going to be randomly distributed as a binomial, so we'll do a b, because we're looking at the number of successes out of these 41 trials. The first number is the number of trials, 41 trials. The second number is the probability of success, which is 0.079. We do need to change that percentage into a decimal. So of our 41 workers, how many would you expect to carpool to work? Well, when we're looking at how many would we expect, we're talking about the expected value, or the mean. The mean, we said, is equal to the number times the probability, or the 41 people you surveyed times the probability of 0.079. That gives us an expected value of 3.239 workers. So maybe you'd round that down to 3 workers. You'd expect about 3, maybe 4 out of your 41 workers to carpool to work. Let's scroll up. We'll come back to the calculator strokes in a minute. What is the standard deviation? Of our population? Well, we have our formula for the standard deviation. It's the square root of NPQ. So we'll take the square root of n, the number of trials is 41. P, the probability is 0.079, times Q. Well, Q is the probability of a failure, or the probability of someone not carpooling to work. Well, if 7.9% carpool to work, we can do 1 minus 0.079 to get Q is equal to 0.921. So Q is 0.921. And when we multiply and take the square root, we'll get a standard deviation of 1.727. But we still haven't calculated any probabilities. So let's do 2 or 3 of these. Let's say, what is the probability exactly 3 of 41 carpool to work? In other words, what's the probability that our x, our number of successes, is exactly equal to 3? Well, because I'm looking for a specific exact number, that is going to be the PDF on our calculator. So on our calculator, we're going to do the binomial PDF, and then we do the number of trials, the probability of 0.079, comma, the number of successes we want, which is 3. Let's go to the calculator and do that. On my calculator, we said the way we got the binomial PDF is we hit the second button, and then above vars, you see the word distribution. Now, the binomial PDF is near the bottom, so you can scroll down a bunch, or if you scroll up once, it'll take you to the bottom. And you see options A and B are the binomial PDF and the binomial CDF. I'll hit enter on the PDF. Now mine gives me the prompts, so I just have to enter in the number of trials, 41, P, the probability of 0.079, the x value, the number of successes I want, which is 3, and then I can select paste. And what that'll do is it'll automatically type in the 41, 0.079, 3 for me. If you don't have those prompts, you can just type those numbers in with commas in between them. The comma's right above the number 7. And when I hit enter, it's going to give me the probability that I get exactly 3 successes. The probability is 0.2304. And we will always round probabilities to 4 decimal places, 0.2304. What is the probability that in my survey less than the expected value carpool to work? In other words, we want the probability that x is less than the expected value, which we found in part B was 3.293. Well, this is a discrete distribution. You can't have 0.293 people saying, yes, they commute to work. So what we're really saying is the probability that x is less than or equal to the number 3. And it's important to identify what it's equal to, less than or equal to, not just less than. Because in the CDF, when we do the cumulative distribution, we need to know what number to start at. So now we're going to do the binomial CDF, cumulative distribution, which is going to add from 0 all the way up to 3. Starting with 41 is the sample size, 0.079 is the probability, and we're going all the way up to 3. We'll hit second distribution to the bottom, but this time selecting the binomial CDF. I have 41 trials, 0.079 is my probability, and my x value is 3. And when I hit paste, it's going to put those numbers in for me. Again, if you don't have the prompts, just put those numbers in separated by a comma. And when I hit enter, it's going to tell me the sum total of all the probabilities of 0, 1, 2, or 3. There is a 59.17, or a 0.5917 probability that if I ask 41 people, I will get 3 or fewer carpoolers as they commute to work. Let's do one last example as we wrap this video up. We want to know, what is the probability more than 4 carpool? So now I'm asking for the probability that x is greater than 4. The problem is the CDF counts down. So this would be a lot of work to do to find them individually. The probability of 5 plus the probability of 6 plus the probability of 7 all the way up to the probability of 41. That is a lot of work. Instead, what we're going to do is we're going to use the complement. We're going to find out the probability that we're not talking about and subtract that probability from 1. 1 minus the probability that x is now less than or equal to, and we have to decide what number we're less than or equal to count everything that's not included with the greater than 4. The blue greater than 4 does not include the number 4, so in the complement we do want to include the number 4. If our probability statement had equality, if it said or equal to 4, then we would have to do the complement, which is the opposite, and to not include 4, and so we'd start at 3. So you really have to be careful to decide what you're going to include. So now on my calculator, we're going to do 1 minus. We want less than or equal to 4. That's the binomial CDF, cumulative distribution function, so it goes up to. With the 41, 0.079 probability, we're going to go up to and include the number 4. 1 minus second distribution up to the binomial CDF. We still have 41 trials. We still have 0.079, but now we want the x value to be 4. Paste. And when I hit enter, 1 minus the binomial CDF gives me a probability of 0.2205. So there's a 22% chance that we would have more than 4 out of 41 workers carpooling to work. That's the binomial distribution. The calculations we'll have the calculator do for us, but we do need to know how to set them up, how to find the mean and the standard deviation, and interpret what pieces are talking about what parts of the binomial. So take a look at a few on your assignment, come to class ready to discuss it further, and we'll continue to investigate the binomial distribution. A second type of distribution that we can work with is called the Poisson distribution. It's named after a mathematician named Poisson. But the question that the Poisson distribution attempts to ask is very similar to the binomial. The binomial wanted to know the probability of x successes in n trials. Poisson also wants to know what is the probability of x successes. But instead of in a certain number of trials, it wants to know in a certain amount of time. In other words, we'll say some event happens on average 3 times an hour. What's the probability this hour it's going to happen 5 times? And to answer that question, we use the Poisson distribution. And some characteristics of the Poisson distribution is that we are interested in some number of successes in a fixed interval. Usually those intervals are a certain amount of time, a day, a week, a month, a year, but it can be any fixed interval, like an editor might be interested in the number of errors an author makes per page. And so a page is the fixed interval that functions as the time interval. But usually we're talking in the context of time. And we also need to know, or we will have, the average number of successes in that interval. So the editor knows that an author makes on average 3 errors per page. The distribution itself, we will notate the distribution very similarly to how we did the binomial. We'll use the x to say that's our random variable, the tilde to tell us it's distributed, but this time, because it's a Poisson distribution, we'll use p to represent Poisson. And the only variable we need for the Poisson distribution is the mean, or the average number of successes in the interval. As you might expect, the expected value is the mean that's given to us. That's no surprise. But the standard deviation turns out to just be the square root of that average. And so these formulas can help us shortcut that process as we attempt to actually use the Poisson distribution. And just like we did with the binomial distribution, when we're using the Poisson distribution, we will actually have the calculator find the probabilities for us. We just need to know how to use the calculator to get the information we want. Very similar to the binomial, we'll hit the second button. And then you're going to hit the vars button, because above the vars, we remember it says distribution. And then we need to select the correct distribution, as there are several in the calculator. Again, near the bottom are going to be the 2 we'll use. One is called Poisson PDF. And just like the binomial, that gives us the probability of exactly x successes. And then the other one is the Poisson CDF, opening a parentheses. That's the one that gives us the probability of up to and including x successes. And again, similar to the binomial, the format we will use, if you don't have the prompts on your calculator, will be the Poisson, either C or P, they both work the same, DF. And then the first number you'll enter in is actually the average, or the mean. over that time interval. The second number is the x value that you're interested in finding. So let's see if we can use the Poisson distribution in an example. Let's say a certain hospital baby unit has an average of 4 births per week. And we're going to randomly choose a week. A week is randomly chosen. First things first, let's describe the distribution. The distribution is a Poisson because we're talking about a time period, an interval, a span of time, 1 week. And in that 1 week, there is an average of 4 births in that week. That is the distribution. Now we can find the expected value and standard deviation of the number of births the hospital has per week. Well, the expected value, that's just mu, or the average, which is given to us. The expected value is 4. The standard deviation, or sigma, is the square root of the average, and the square root of 4 is 2. So average of 4 births with a standard deviation of 2 births is what we would expect to happen on any given week in the baby unit of the hospital. So let's find some probabilities and see how likely various things are to occur. I'm always interested in how often the average occurs. So what is the probability exactly 4 babies are born this week? What we're asking is, what is the probability that our random variable x is exactly equal to 4? Now, because I want my probability to be exactly equal to 4, what I'm interested in finding is the PDF for the Poisson exactly equal to 4 in that time interval. So we will do the Poisson PDF, probability distribution function. The first number is the average of 4. The second number says we want exactly 4 to occur. So let's see what the calculator says when we pull it up. Very similar to the binomial, we'll hit second and distributions. Scroll down to the bottom, and below the binomial, you'll see the Poisson distributions. The Poisson's PDF. And the calculator, if it gives you props, will ask for lambda. That's the Greek letter lambda is the average. So for lambda, the average we say is 4. The x value we're interested in is 4. And when we paste, you'll see it puts it in the calculator for me. If you don't have the prompts, again, you can just type in 4, 4 and close the parentheses. The comma's above the 7. And we see the probability that we get exactly 4. Even though that's the average, the probability that actually occurs is only about 19.5%, 0.1954 when we round. So that might beg the question, what is the probability of fewer than 4 births this week? the average of 4 only has a less than 20% probability. What's the probability that x is fewer or smaller than 4? Well, the calculator can only do exactly equal to a number and down. So first, let's identify that we're really looking for the probability that x is less than or equal to, not 4, because 4 is not included, but less than or equal to 3. Because we want to be less than or equal to 3, counting all the possibilities up to 3, 0 plus 1 plus 2 plus 3, that's going to be our CDF, or our cumulative distribution that adds up all the values up to that point. The Poisson CDF, which has an average of 4, but we want to know up to the number 3. So we go to our calculator and hit second distribution. Down to the bottom, you see Poisson CDF. The mean is 4. We want to go up to 3. And when we paste, types the numbers in, or you can type them in manually if you don't have the prompts. The probability that we get less than 4 is 0.4335. So there's a 43% chance we're actually less than the average number of births. Let's say the hospital can only handle about 1 baby a day, 1 birth a day. It's a small hospital, a small baby unit. So we want to know what is the probability seven or more births occur this week. What is the probability that x is greater than or equal to, because it includes 7, it said 7 or more, births this week? Now, the thing about the Poisson distribution is there's not actually any maximum. In theory, there could be 1,000 births this week at this hospital. It could go up that high. Now, if the average is 4, the probability is basically 0, but it could potentially happen. So when we're doing greater than 7, this is actually impossible to calculate straightforward, because we'd have to do 7 plus 8 plus 9 plus 10 plus 11, and we'd have to go all the way to infinity. We can't do that. So just like we did with the binomial, when we want greater than, we're going to actually work with the complement. We're going to do 1 minus the probability that x is less than or equal to the opposite set of numbers. Now, if we're going from 7 up, this time it includes the number 7. So when we count down, we don't want to include 7. So we're going to start at 6 counting down. So in the calculator, we'll type in 1 minus the Poisson CDF, cumulative. It's going to add those all up. The average is 4. And we want to go up to 6. And then we'll subtract all of that off of 1 to get the complement. So we'll type in 1 minus second distribution up to Poisson CDF. The average is still 4, but this time we're going up to 6. And when I paste it in, and we do 1 minus that value, we get a probability of 0.1107. 0.1107. And so if they're not ready for 7 or more births this week, that's going to happen 11% of the time. They might need to expand their baby unit in the hospital. So that's the Poisson distribution. Very, very similar to the binomial. The difference is now we're talking about the number of successes in a fixed interval, usually a time interval. So take a look at the homework assignment to practice a few of these, and then when you come to class, we'll continue working with Poisson and that distribution. We've spent several days discussing how to find probabilities of discrete distributions where the results are countable. But probabilities with continuous distributions become a little bit more interesting. That's going to be the question we look at, is how do we find probabilities of continuous distributions? Because if it's continuous, we've got to consider every possibility. Between 1 and 2, there are an infinite number of decimals, and we can't add the individual probabilities. So instead, we're going to steal a concept from calculus that says that the probability is simply the same thing as the area under a curve. A really simple example of what I mean by this to help us visualize is probability distribution functions or density functions can be expressed as an equation. Maybe f of x equals 1/2 of x. That is a probability distribution function. Probability with results that are possible from 0 to 2. Here's what I mean by that. If we were to graph f of x equals 1/2 of x, we would know that has a y-intercept of 0 and a slope of rise 1, run 2. And so this line going from 0 to 2 represents the probability distribution function, or the density function. And the probabilities are just going to be the area underneath that line. Remember that if we take the probability of all of our possibilities, they have to add up to 1. Well, if I were to calculate the area of this triangle, as it turns out to be, we know areas for triangle is 1/2 times the base times the height. Well, the base is 2 wide, and the height is 1 high. So 1/2 times 2 times 1 equals 1.00. The total area of this triangle is 1.0, just like the total probability of all the possible outcomes is 1.00. So now we could find the probability that maybe our random variable x is less than 1. What we're really looking for is 1's here in the middle. If I were to shade the area less than 1 on this triangle, we end up with this smaller triangle on the left side here. Well, the probability that it's less than 1 is the area under the curve that is less than 1, which is still a triangle. So the probability is the triangle area, 1/2 times the base. Well, the base is 1 long. Times the height. And if I were to draw this to scale, you'd see the height was exactly 0.05. And so 1/2 times 1 times 0.05, we'd end up with an area of 0.25, meaning there's a 25% probability that I'm between 0 and 1 on this triangle. Now, this f of x equals 1/2 x probability density function, I made it up. It's fake. It doesn't model anything. But it does show us kind of how this idea works, that probability is the area under the curve. The curve can be any shape, as long as the total area under it is 1. because that's the total probability that is equal to 1. So rather than dealing with a fake triangle, let's deal with a real probability density function. One that we do use is called the uniform distribution. And the uniform distribution is a distribution where all outcomes are equally likely. I could get any number with basically equal probability. The distribution itself has a special notation, just like the Poisson and the binomial did. When we have a uniform distribution, we will say x tilde, or x is uniformly distributed, u, between a and b, where a is the low number and b is the high number. So if we're going anywhere from 5 to 10 with equal probability, the numbers a and b would be 5 and 10. Now, the curve that we want to be underneath for the uniform is f of x equals the reciprocal of the difference, or 1 over b minus a. And when we do that, what we'll end up with is a rectangle that goes from a to b, where they're all equally likely to occur. And that height on that line is how likely it's to occur, that 1 over b minus a. If I were to find the area of this rectangle, because it's a rectangle, area is base times height. So the area is the base. The distance between the two, we have to subtract them, is b minus a. And the height, that's the green height that we just calculated, is 1 over b minus a. And those b minus a's divide out. So the total area is 1.0. So the curve, the height of the rectangle for a uniform distribution, is the reciprocal of the difference, 1 over b minus a. Now, just like the discrete distributions, we can find the mean, or the expected value. And the formula for that with the uniform is just a plus b divided by 2, or the average of the extremes. That's going to stick us right in the middle to find the mean. Turns out the standard deviation is equal to the square root of b minus a squared divided by 12. And it's always divided by 12, regardless of the numbers. It just works out that way. So let's try an example of this and see if we can see this uniform distribution work out. So for example, a plumber estimates that service calls are uniformly distributed between half an hour, or 0.5 hours, and 8 hours. First, let's describe the distribution. We said our random variable x was going to be distributed uniformly. The smallest number possible is 0.5. The largest number possible is 8. So our distribution is x tilde u 0.5, 8. We can easily then calculate the mean, or expected value, and standard deviation using the formulas from the uniform distribution. The mean is the average, 0.5 plus 8 divided by 2, which is 8.5 divided by 2, which is 4.25 hours. So this plumber's average service call is about 4¼ hours, 4 hours, 15 minutes. The standard deviation on those service calls is the square root of b minus a, 8 minus 0.5, squared, divided by 12. When we put that into our calculator, we should end up with a standard deviation of 2.165 hours. So now that we know his average call or service call and standard deviation, let's actually calculate some probabilities. And what you'll find with calculating probabilities on continuous distributions, it's always easier to draw a picture of the situation. So if we want to find the probability a call takes less than 3 hours, we're going to draw a picture of the probability. It's a uniform distribution, so we know it's a rectangle from a low of 0.5 all the way up to 8. The height is that f of x equals 1 over b minus a, or 1 over 8 minus 0.5, 1 over 7.5. And we can leave that decimal in there. That's OK. Now, it's asking for us to find the probability that we're actually less than 3. Remember, probability is area. So if I mark on my graph approximately where 3 is, and we want to be less than 3, it's going to be the area of this rectangle off to the left. So the probability that x is less than 3 is the area of the rectangle, base times height. The base is the distance from 3 to 0.5, or 3 minus 0.5. And the height is what we just found out, the f of x, the 1 over 7.5. And when I put this into my calculator, 3 minus 0.5 in parentheses times 1 over 7.5, we end up with 0.3333. Or about a 1/3 probability that the service call takes less than 3 hours. Let's try another example. Let's find the probability a call takes between 2 and 4 hours. Again, probabilities are always easier if you draw a picture. So here's our uniform probability. It doesn't have to be to scale, but it does show the lowest 0.5, the highest 0.8. The height is still 1 over 7.5. But now I want to be between 2 and 4 hours. So between 2 and 4 hours, we're going to shade that area in between. We're looking for the probability that 2 is less than x, which is less than 4, which is just this rectangle. The rectangle is base times height. The base is the space from 2 to 4, or 4 minus 2, times the height, which is 1 over 7.5. Putting that in my calculator, 4 minus 2 is 2 divided by 7.5. We get an area of 0.2667 when we round. So there's about a 26 2/3% probability that a call will take between 2 and 4 hours. We can even find conditional probabilities in much the same way. Let's find the probability a call takes more than 5 hours given it was less than 7 hours. Again, we're going to draw a picture going from 0.5 to 8 with a height of 1 over 7.5. But now I want to be more than 5 given it was less than 7. So we don't really care about this right side. We just want to be less than 7. And we want to know what's the probability that I'm more than 5 given that I'm less than 7. The probability that x is more than 5 given x is less than 7. Well, with a given probability, we know we look at the probability of both divided by the probability of the given information. So the probability of both would be between 5 and 7. So between 5 and 7 has a base of 7 minus 5 times a height of 1 over 7.5. That's the both, and then we divide by the probability of the given information. The given information is that we're less than 7. So that probability's got a base going all the way down of 7 minus 0.5 times a height of 1 over 7.5. Which is kind of nice, as often occurs with given probabilities. Part of it will divide out. And so we're left with 7 minus 5 is 2 over 7 minus 0.5 is 6.5. And 2 divided by 6.5 is 0.3077. So there's just over a 30% probability the call took more than 5 hours, given we knew it was less than 7 hours. Another concept that we haven't spent much time with is the idea of what's called a percentile. A percentile is the value where a certain percent is below the value. You often see this with standardized test scores. If you took a test and you scored in the 80th percentile, that means your score was better than 80% of the participants. So we could find, for our example, let's find the 80th percentile, or what value has 80% below it. Let's draw a picture. Same picture. It's a uniform distribution, so it's just a big rectangle. The height is still 1 over 7.5, and we're going from 0.5 to 8. But we want to know what value, let's call it k for now, will give us an area that's 0.80, below it. 80% is below it. What value gives us that? Well, to get there, we're going to use our area formula. The fact that we know that area of a rectangle is base times height. The difference is this time, we know the area. We know the area is 0.80. The base is the distance from k down to 0.5. So we'll have k minus 0.5 is the base. And the height we know is 1 over 7.5. All we really need to do now is solve this equation for k, and that solution will be our 80th percentile, the value that has 80% of service calls below it. First, we can get rid of the fraction by multiplying both sides of the equation by 7.5. That's going to give us 6 equals k minus 0.5. Add 0.5 to both sides, and k is equal to 6.5. This means that 80% of service calls are less than 6.5 hours. That's what it means to be the 80th percentile. Now, as we wrap up, there's one more example I want to show you. It's kind of a special case, and it seems counterintuitive. We want to find what is the probability a call takes exactly 5 hours. And the key word here is exactly, because that means something very specific in probability. It doesn't mean between 5 hours and 5 hours, 0 minutes, and 1 second. It means at the exact moment of 5 hours. Let's draw a picture to represent the exact moment of 5 hours. Going from 0.5 to 8, and a height of 1 over 7.5, the exact moment of 5 hours occurs somewhere in the middle. Well, the probability that x equals exactly 5 is going to be whatever the base is times the height. The problem is the base of that rectangle, since it's just a line right at 5 hours with no width, the base goes from 5 to 5 with the height of 1 over 7.5. But 5 minus 5 is 0. And anything times 0 is 0. The probability that anything happens at exactly a specific moment in a continuous distribution is always equal to 0. Nothing ever happens at an exact moment. That always happens over a span of time. It could be between 5 hours and 5 hours and 1 second. But that's a span of time. At exactly a specific number, that will never occur in a continuous distribution. Seems like a paradox, but it's the way it works out. We're focusing, though, today on finding probabilities off the uniform distribution, and this idea with continuous distributions that probability is area under the curve. So take a look at the assignment to practice a few of these, and we will see you in class to continue working with the uniform distribution. Now that we've gotten familiar with continuous probability distributions, we're going to move on to take a look at the most important continuous distribution in all of statistics, and that is the normal distribution. So the question today is simply, what is the normal distribution? The normal distribution is a probability density function that's got this beautiful equation of 1 over the standard deviation times the square root of 2 pi times e to the exponent of negative 1/2 times x minus the mean divided by the standard deviation squared. Now, what's nice about the normal distribution is you do not need to know that formula. Instead, we're going to cheat and use a table to help us actually calculate what that formula is going to be equal to at various points. But what you should know about the normal distribution is the shape of the normal distribution. Just like the uniform distribution has a clear shape of the rectangle, the normal distribution has a clear bell shape to the curve. The normal distribution, if this is my x-axis, is a bell-shaped curve where the mean of the distribution falls right in the middle. And we describe the distribution as x tilde n for normal. And then we'll just state the mean and the standard deviation for the two arguments of the function. Now, the normal distribution has slightly different shapes based on the standard deviation. The smaller the standard deviation, the taller and skinnier it is. The larger the standard deviation, the shorter and fatter it is. But there's one special distribution, which we call the standard normal distribution. And for when we're dealing with the standard normal, we won't use x, we'll use z. So we know we're talking about the standard normal distribution, which always has a mean of 0 and a standard deviation of 1. And what's nice about the standard normal distribution, it has a table to help us find areas. This is what the table looks like. The table gives us values for z. Going down the first column, you see the first 2 digits, maybe 1.2. And then if I wanted 1.23, I'd go to the 3 on the next, and where those two overlapped, at the point 3907, I can get my area under the curve based on those z values. And we'll look more at using the table here in just a minute. But what we need to know for now is there's a table to help us find areas. And what we need to do quite often is we change between a regular normal curve, which uses x values, and the standard normal curve, which uses z values, so that we can use the table in order to find the areas. The way we make that change is we use one of two equations. We either use z equals the x value minus the mean divided by the standard deviation. Or if we solve for x in that same equation, we end up with the mean plus the z value times the standard deviation. And with these two definitions, or these two formulas, it's important that we keep track of what's an x and what's a z. X has meaning in context. X might be the height of the average person. And so x, we're looking at a 64-inch person. Z does not have context or meaning. Z is simply the number of standard deviations we are from the mean. And once we have a z-value, then we're able to go to the standard normal to find areas off the table. The table gives the area between a z-value and the mean. And of course, the mean is 0. In other words, if I've got this standard normal curve here, the mean is always in the middle of 0. Off to the side, we've got a z-value. The table gives the area between that z-value and the mean of 0. So if we want to find probabilities, let's scroll up a bit and give us a little bit more room. If we want to find probabilities off this table, we'll have to decide what pieces we're interested in. First thing that we'll use is the fact that the curve is symmetric. In other words, the z-table does not have any negative values on it. Fortunately, the negative values behave like the positive values because the curve is symmetric. Each half, the left and right side, has an area of 0.5. And we use this one less often, but the total area is 1.0 because it's a probability. So let's see if we can figure out how to use this information and use our table in order to calculate probabilities under the standard normal curve. Let's do some examples. For this example, if you look up, according to Google, the average ACT score is 20.8. with a standard deviation of 4.8. Let's do some examples off of this information. First, let's describe the distribution. For the distribution, our variable x is normally distributed. The mean is 20.8, and the standard deviation is 4.8. Let's find out the probability a student scores higher than 30. Now, with all of these probability problems, it will always be easier to draw a picture first. So we'll draw a picture of our normal curve, our little bell-shaped curve. We'll put the mean right in the middle. The mean is an x value right now. So I'm going to label my first row, we're going to put x values on it. And then in the second row, we'll label what those equivalent z values are when we change them from x's to z's. That way we don't get them mixed up. So the mean for our x value is 20.8. We want a student to score higher than 30. 30 is off to the right. And we want the area that's higher than 30, because the area is the probability. Well, let's change those x values into z's. We know the mean changes to 0. But the 30, we need to use our formula for z. Z says take the x value, subtract the mean, and divide by the standard deviation. We have an x value of 30 minus 20.8 divided by the standard deviation of 4.8. We end up with a z value of 1.92. So 30 changes into a z value of 1.92. We will always round our z values to 2 decimal digits because that's going to match our standard normal table. So on our table, we need to find 1.92. Let's scroll down a bit to help us see it a little better. 1.9 going down the column, and then we want 1.92. And so when we combine those, we end up with them overlapping at 0.4726. That 0.4726 is the area between my z value and the mean. It's the white area, kind of in the center. We don't want the white area in the center. We want the tail off to the right of it. And this is where we use what we know about the normal distribution. We know the entire right side is 0.5. So the probability that some student scores higher than 30 is going to be equal to the 0.5 minus that white area that's been cut out of 0.4726, which leaves us with 0.0274. There's just shy of a 3% chance that a random student will have scored higher than 30. Let's try a few more of these so we can get really good at finding probabilities on this important normal distribution. We're on number 3. Let's find the probability a student scores less than 25. Again, we'll draw a picture. The mean right in the middle of 20.8, that's an x value. We want to be less than 25, which is somewhere over here to the right. And we want to be less than, so we want the smaller part, or the left side, all of that area. In order to do that, we need to calculate our z values. We already know the mean will have a z value of 0. What we don't know is the z value of the 25. So we'll subtract the mean of 20.8. We'll divide by the standard deviation of 4.8. And we get 0.88. So now we have a z value of 0.88 that corresponds with the x value of 25. 0.88 is what we're going to look up in our table. In the table, we're looking for 0.88. So 0.88. When we go down and across, we find out the probability there is 0.3106. 0.3106. And that, again, is the area, 0.3106, the area between the mean and that z value of 0.88. But this time, we also want not just that little bit, but the whole area to the side. That left side we know is 0.5. So when we want the probability that x is less than 25, this time we need an extra 0.5 added to the 0.3106 that we just found to get 0.8106. Or just over 81% of students score less than a 25 on the ACT. So you can see how the picture helps in the difference between example 2 and example 3. Example 2, we had to subtract from 0.5 to get the area that we wanted. Example 3, we had to add to 0.5 to get the area we wanted. Let's try another example to keep working on how the picture is going to help us calculate our probability. Let's find the probability a student scores between 15 and 23 on their ACT. So we draw a picture. The mean in the middle has an x value of 20.8. We want to be between 15 and 23. 15 is off to the left, and 23 is off to the right. We want the area between these two numbers. So now when we convert to a z-value, we don't have to just change the mean to 0 and one other value. We have two other values that we need to convert to z-values. So let's do that. For the 15, we take 15 minus the mean of 20.8 divided by the standard deviation of 4.8. That's going to give us a negative number, negative 1.21. But that's OK because it's to the left of 0. It makes sense that a number to the left of 0 on the number line is negative. That's what a negative z-value is. It just means we're to the left or smaller than the mean. When we do the 23, we should get a positive number. 23 divided by 0.8 divided by 4.8. And it's going to be positive because it's bigger than the mean. This turns out to be 0.46, a z-value of 0.46. We're going to look up both of these values in the normal table. First, looking up the 1.21. It's negative, but that's OK because the curve is symmetrical. So we'll just look up the positive version, and it's going to have the same area on the other side, 1.21. 1.21. So when we do that, we end up with this center area of 0.3869. 0.3869 is the area between the mean and that z-value, 0.3869. We still need to look up the z-value of 0.46. So I'll do it in blue here, 0.46. When I go across, we end up with an area of 0.1772. So the area there is 0.1772. We want the area between those two numbers, which includes both halves. So when I want to find the probability that 15 is less than our score, which is less than 23, we need to combine both those pieces together. 0.3869 plus 0.1772 will give us a total area of 0.5641. There's just over a 56% chance that a student will score between 15 and 23. So sometimes you see we have to add pieces together. But that's not always the case either. Let's look at this example. Let's find the probability a student, just one student, scores between 18 and 20 Now if we draw this picture with our mean in the center of 20.8, that's an x value. But now you notice 18 and 20 are both smaller than our mean. And we want the area between them. Of course, to get that area, we have to change them to a z-value. The mean has a z-value of 0, but we have to work to get the other 2 points. So first for the 18 minus the mean of 20.8 divided by the standard deviation of 4.8. That's going to be equal to negative 0.58. So the z-value there is negative 0.58. For the second one, the 20, z is equal to 20 minus 20.8 divided by 4.8 is equal to negative 0.17. Negative 0.17. And we want the area between those. Going to our normal distribution, our first value was negative 0.58. 0.58. So we'll go over and down, and we find our first area is 0.2190. 0.2190. So this first one, 0.2190. Now it's important to note that's not just the shaded region. That goes all the way to the mean. It doesn't stop at the 20. The 2190 goes all the way to the mean. Does not stop at the 20. We still need to find the other piece, which is the negative 0.17. Doing this one in blue, the negative 0.17. Going down and across, we find an area of 0.675. So that's area of 0.6750. 675. Sorry, forgot the 0. 0.0675. And now we're ready to answer the question, what is the probability that 18 is less than our score, which is less than 20? Well, the 20.90 goes all the way to the mean, but we don't want the white space, the 0.675, that goes on the right side of the mean. So if we're going to cut out that white space, we just need to subtract. We have 0.2190 minus 0.0675. That's going to be 0.1515. Just over a 15% probability a student will score between 18 and 20. Let's do one last example, but let's make this one a little different. This time, we're going to find the third quartile of ACT scores. Remember, the third quartile, that's the value that's over 75%. What we're really asking to find is the 75th percentile. This is different than we were doing before. We're not saying what's the probability of this number. We have the probability. We have the probability. 0.75. We're looking for the x and the z values that give us 0.75. So let's draw our picture. We've got our mean of 20.8. That's an x. When it's a z, the mean is 0. And we're looking for some value out here. We'll call it k. Some value out there where the area below is a total of 75%. Well, the table's only going to give us the space between k and the mean. And actually, let's label k down below. We're going to make k a z-value. We'll use that k to find the x-value. We know the left side of the curve is 50%, or 0.5, so the right side of the curve must be the remaining 0.25 of an area. But we know the area of 0.25. When we're given the area, do not go down the z-values. Z's are not areas. Z's are a scale of the number of standard deviations we are from the mean. We need to look inside the body of the table for the area that we're given. We want 0.25. And if we kind of scan through our numbers, you'll see 0.25, an area of 0.25 is right in between these two numbers, between 2486 and 2517. Now, if it was closer to 1, I'd go with the one that's closer, but it's really right in the middle. So we'll call right in the middle 0.6, right in between 7, 8. So we're going to call that 0.675. 0.675. So that k value is 0.675. How do we find the x value then? Well, we have that other formula we haven't used yet that says x is equal to the mean plus the number of standard deviations times the standard deviation. And that z is that z-value we just found of 0.675. So if we plug in what we know, the score x, that's the 75th percentile or the third quartile, is the mean of 20.8 plus 0.675 times the standard deviation of 4.8. The mean is 24. I'm sorry, not the mean, but the x value, 24.04. The third quartile of ACT scores is about 24. That means a score of 24 is better than about 75% of all of the scores on the ACT. The normal distribution is truly the most important distribution you know how to use in all of probability. You need to know how to use the table, how to find the left side, the right side, what's in the tail, what's in the middle, how do you find percentiles, how do you use the table backwards. You need to be very comfortable and familiar with the normal distribution and how it works as we move forward in our study of probability. So take a look at the homework assignment, practice a few of these important problems. In class, we're going to keep working with the normal distribution, and I will look forward to seeing you then. Now that we've gotten really comfortable at working with the normal distribution and finding probabilities, we're ready to actually get into working with samples. Now, the heart of statistics is collecting a sample to make an estimate or a conclusion about a population. So first we need to know, how do we find probabilities? With sample means. The big difference here is in the previous chapter, in chapter 2, we were finding the probability for one individual value. Now we're going to take several values, find the mean, and look at the probability of the mean of several values. And this is what gives rise to what is called the central limit theorem. And the central limit theorem basically in words says that the mean of a sample should be close to the mean of a population. And not only that, it should have a smaller standard deviation. The idea is that if we have several values averaged together, the extreme values are going to be averaged out and pulled back in towards the center, which makes the standard deviation smaller. In fact, we can go one step further and say that the larger the sample, the closer to the mean we become, and the smaller the standard deviation is. And that makes sense. If I interview nearly everybody, I will be probably pretty close to the actual mean. I'm not going to be off by much, which is why the standard deviation is going to be so small. And as we're working with samples, this idea of the standard deviation, or the smaller standard deviation, we call the standard error. The standard error will use the symbol of either sigma sub x bar, or you'll often see S sub e for standard error. And that's the standard deviation of the sample means. And the way we calculate the standard error, or the standard deviation of the sample means, is we will take the standard deviation of the entire population, and we'll divide by the square root of the sample size. Or if it's a sample, we'll say S for the sample, standard deviation, divided by the square root of the sample size. And that's a key equation that we're going to use quite a bit today. Using this new standard error, we can replace the standard deviation in our distribution of the mean. When we're talking about means, we're going to say that means are normally distributed with the same mean as the whole population. But then we will use the standard error, or S divided by the square root of n, to represent our new standard deviation. Then we can go forward and calculate z-scores and also probabilities in much the same way we did before. Now the z-score is equal to the mean of our sample minus the overall mean divided by the standard error. And that's going to be the key new thing that the central limit theorem gives us, is that new standard error as we calculate our z-values, because we have a sample, not just one value. So let's look at an example where a sample is done. A cell phone company finds that those who go over their data limit go over by an average of 2.2 gigabytes with a standard deviation of 0.4 gigabytes. You conduct a survey of 80 customers. First thing we want to know is we want to know what's the probability the average overage is above 2.3 gigabytes. Or what's the probability that x is greater than 2.3? Actually, x bar is greater than 2.3, that the average is more than 2.3. Well, the first thing we're going to need to do here is we're going to figure out what is the distribution of the mean. The mean should have the same mean as the population, 2.2 gigabytes. But the standard deviation is smaller. We take the 0.4 gigabytes and we have to divide by the square root of the sample size. Divide by the square root of 80. So we have 2.2 comma 0.4 divided by the square root of 80 is about 0.045. That 0.045, that is our new standard error. So when we calculate our z-score, we remember that z is x bar minus mu divided by the standard error. Our x bar we want to be greater than 2.3. So we'll take 2.3, we'll subtract the average of the population divided by our standard error, because we have a sample, not an individual, of 0.045. And when we divide, we get 2.22. So if we think about our normal distribution, the mean of the population is at 2.2. These are x values. We want to be at 2.3 or bigger. So we standardized into z values. And the z value actually turned out to be 2.22. So that's what we're going to look at in our standard normal table. In our standard normal table, we've got 2.2 and another 2. So we see the probability there is 0.4868. But remember, that is always the area between the z value and the mean. We want the area in the tail. So the probability that the mean is greater than 2.3. We know the entire right side is 0.5. Subtract off the middle of 0.4868, and we get 0.0132. There's about a 1 1/3% probability that if I interview 80 customers, I'll get a mean bigger than 2.3. And that's the idea of the central limit theorem. We're shrinking the standard deviation by dividing it by the square root of the sample size. Whenever we have a sample, we need to divide by the square root of the sample size. Let's keep with this example one more. I also want to see if we can find Q1 or the 25th percentile. So same problem with the cell phones, where we've got these x values. The mean x value is 2.2 gigs. We want to find the x value where 25% or 0.25 is in that first tail. Well, the table is going to give us the other half because the table always goes between our percentile or our z-value and the mean. So the table is going to be 0.5 minus a quarter, or 0.5 minus 0.25, which is also 0.25. So we're going to look up the z that corresponds with an area of 0.25. Notice we're talking about an area. We do not know the z-value. So when we go to the table, we're looking for an area of 0.25. We're looking inside the body of the table, and 0.25 happens somewhere in the middle here between 0.67 and 0.68. So we're going to call that 0.675. The z-value is 0.675. But notice it's to the left of 0, to the left of the mean. So it actually has to be a negative 0.675 because it's to the left of 0. It's smaller than 0. We still need to convert that z-value, which has no context, into a x value that does have context. And very similar to how we did it back with the normal distribution, our x bar is going to be equal to the mean plus the z-value times the standard deviation, which in this case is the standard error. So x bar is equal to our mean of 2.2 minus a 0.675, because it's negative, times the standard error, which we calculated the standard error to be 0.045. .045. And 2.2 minus 0.675 times 0.045 gives us a mean of 2.17, putting units on it, gigabytes. The 25th percentile of means of sample of size 80 is going to be 2.17 gigabytes. Now it's time for you to take a look at the homework assignment to try and do some problems using the central limit theorem, where we have this new standard error. The new standard error is triggered because we have a sample, not just one individual data value. See if you can work with a few, and in class we will discuss them further and practice this whole central limit theorem a little bit more. Now that we've talked about this idea that samples adjust the standard deviation to become what the standard error is, we're ready to do some inferential statistics. Inferential statistics take a look at the idea of how can the sample help us make an estimate or a conclusion about the entire population. And as you might guess, a sample and the population will have similar but different statistics or parameters. And so the question we're going to start this discussion off with is, how close is a sample proportion to a population proportion? In other words, if I take a sample of 100 people and ask what number of them or what percent of them eat breakfast in the morning, I'll end up with a percentage of people in my sample who eat breakfast in the morning. That's a sample statistic. And I can use that to try and estimate what percent of the entire population or all people eat breakfast. That is the population parameter. However, the two numbers aren't going to be exactly the same. There will be some type of error involved in that proportion. So that's what we're going to look at today. What is that error and how can we calculate it? First, I want to make sure we really understand this concept of proportion. When we're talking about proportions, what we're really saying is that the underlying distribution is binomial. And if you remember from our probability unit, binomial takes a look at x successes out of n trials. That's what we're looking at. So if we were asking about the breakfast example, we're looking at how many people eat breakfast, the successes, out of how many people total we're interviewing. And then from that success and trial concept, we can calculate the population proportion, or I'm sorry, the sample proportion, which we represent as p hat with the little triangle over the p. We calculate that by taking the successes divided by the trials to get some type of percentage, proportion, or decimal. And it turns out that proportions are normally distributed with a mean that's equal to the proportion and a standard error that's the square root of the proportion times the probability of failure divided by the sample size. And again, that Q hat, Q is failure, the opposite of successes, so it's 1 minus the proportions. This underlying distribution will allow us to estimate where the actual population parameter lies. To do that, we will find what's called a confidence interval. A confidence interval is an interval maybe between 20 and 30%. That's an interval based on the sample statistic where the population parameter is likely to be located. So it's going to be this range of numbers where we are quite confident the actual population parameter lies. And the idea behind it is that our sample statistic is likely not perfect. It's likely off by some error. And so what we'll do to calculate this interval is we'll say, okay, let's take the sample proportion and we'll subtract the error. And then we'll take the sample proportion and add the error. And the population parameter is likely somewhere between those two numbers. So we take our sample statistic and add and subtract the error, and that should give us a range of numbers where the population proportion actually lies. But how big is that error? Well, we don't really know. What we have to do is we have to say we're going to be comfortable with some level of confidence or some level of error that's allowed to occur. And if we're okay with being wrong 5% of the time, we'll make what's called a 95% confidence interval. If we're okay being wrong 10% of the time, we'll make what's called a 90% confidence interval. So the confidence kind of tells us how often we want to be correct and accepts a certain amount of error. Because we can never be 100% confident unless we interview everybody. So we've got this idea of a confidence level. And that's going to be the probability the interval contains the population parameter. We'll have some type of confidence level. Let's say, for example, I want to have a 95% confidence level. That means I want to be right 95% of the time, but I could be wrong. We have this alpha, which is a Greek letter. The Greek letter alpha is the probability we are wrong. And so if we want to be 95% confident, alpha is going to be 1.0 minus the 0.95. Alpha is going to be 0.05, a 5% probability that we are wrong. Visually on the normal curve, what that means is if my sample proportion comes in the middle of the normal curve, we're going to put a range, the proportion minus the error and the proportion plus the error, and we want to be somewhere in the middle. We're claiming the population proportion is somewhere in that range. So in that range, that's my confidence level, the 95%. Which means out in the tails is where I could be wrong if it actually falls out there. Well, if there's 5% in the tails, and there's 2 tails, we could have 2.5%, splitting it in half, in each tail. Our goal is going to be to figure out what that error amount is that we have to add and subtract in order to get 2.5% in each tail. That's what we're doing. So with proportions, to calculate the error, we have this nice formula that the error is equal to what we'll call z sub alpha over 2 times the square root of p hat q hat over n. This is a formula that we should be very comfortable using. P hat, Q hat, and N we should be familiar with because those all come from our sample. We've already talked about those before. This Z sub alpha over 2 value, that is the Z value that gives the correct area in each tail. So for this example up above where I wanted a 95% confidence interval, that would be the Z value that gave me 2.5% in each tail. And we can look that up in the table backwards, or we can consider some common Z sub alpha over 2 values. Because really, most confidence intervals come in one of 3 types. We have confidence levels of either 90%, 95%, or 99%. And the Z sub alpha over 2 that goes with each of them, with the 90% to get 10% in the tails, 5% in each tail, we'll use 1.645. For the 95% confidence interval, like the example up above, we'll use 1.960. And for a 99% confidence interval, it turns out the Z sub alpha over 2 is 2.576. You do not need to memorize these numbers, but you should have them handy as you're doing your assignments and the practices and labs for our class. Okay, I think we're in need of an example so that we can see this work out, so we can see how we find out how big the error is between our sample statistic and population proportion. And once we know the error, how do we find a confidence interval that contains, or likely contains, the actual population parameter? Let's do an example. A survey is done and 95 out of 174 voters support a particular candidate for Senate. And the first thing we're going to do is we are going to construct a 90% confidence interval. For the true proportion of voters who support the candidate. Can this candidate be 90% confident that she or he has a majority of the voter support? Well, first we need to know what is the proportion p hat that we're dealing with. We have to calculate this. The proportion is our number of successes out of the number of trials. 95 out of 174 voters support the candidate. That comes out to a proportion of 0.546, or 54% of the voters in the survey support this candidate. Looks pretty good. Q hat, the probability of failure is always 1 minus the proportion. So in this case, 1 minus 0.546, which comes out to be 0.454. We also need a z sub alpha over 2, or in this case, alpha is the probability of failure, 0.10 over 2, which gives us z of 0.5, because we want 10% in the tails. Oops, not 0.5, 0.05. 5% in each tail. And so we would need to find the z value that puts 5% area in each tail. We can look that up on our big z table, or that is one of the common ones that we have from our chart up above. So we will use z sub 0.05 is equal to 1.645. Those are the three pieces that we will need in order to build our confidence interval. The error between our sample proportion and the population proportion is equal to the z sub alpha over 2 times the square root of p hat q hat over n. Z sub alpha over 2 is 1.645 times the square root of p hat, which is 0.546, times q hat, which is 0.454, divided by n, the sample size of 174. And when you do this on your calculator, for some reason it's really common students forget to multiply by the 1.645. They just do the square root. Make sure you do the whole thing, and you should end up with an error of 0.06, let's round it to 0.062. This is how much my sample might be off at 90% confident. We're 90% confident our sample might be off by about 6%. So we will take the sample proportion and subtract the error to get the lower bound of the worst case scenario for this candidate. And we'll do our proportion plus the error to get our upper bound to get our best case scenario for this candidate. Our proportion was 0.546 minus 0.062, the error, and 0.546 plus 0.062, the error. And when we subtract, we end up with 0.484. And when we add, we end up with 0.608. And this range is where the population parameter or the population proportion likely lies in between. Let's make a better way of saying that, though. Let's look at how we interpret a confidence interval. Interpreting a confidence interval is almost as important as how we calculate it, because our statistics don't mean anything unless we can put it in context of the situation. So what we will say to interpret a confidence interval, and this becomes a nice script for interpreting any confidence interval we do in this class, is we will say we estimate with some percentage, that would be your confidence level, whatever your confidence level is, with some percentage confidence that the true, let's actually say that the true population, whatever we're talking about, we're going to put the parameter in context. So we're talking about the population mean, the population proportion, the population standard deviation, whatever we're talking about, but then we'll put it in context of the situation we're describing, is between blank and blank. And those would be, as you might expect, the low number and the high number. So for our proportion, we're going to interpret the confidence interval from the example above. And you can still see it at the top of your screen there in purple. The confidence interval is 0.484, 0.608. But what that means in context is that we can estimate, notice how I follow the script here. We estimate with, and this one was a 90% confidence interval, so 90% confidence that the true population, and now I'm going to describe the parameter in context. We're doing proportions here. What proportions support this candidate for Senate? That the true population proportion who support the candidate for Senate. Notice that puts it completely in context, so we know what the problem was discussing. Is between, and the low number, let's go ahead and make it a percent, 48.4% and 60.8%. And that's how we will interpret that confidence interval. We're 90% confident the true population proportion who support the candidate for Senate is between 48.4% and 60.8%. So it's not a guarantee this candidate's going to get a majority. You might say it's pretty likely, but we don't know where in between these numbers the actual proportion's going to lie. We just know it's going to be between those numbers, or at least we're 90% confident it's between those numbers. So you should be able to today build a confidence interval using the formulas for proportions that we talked about today. And then just as important, you should be able to interpret that confidence interval using the script we've provided here. So you can go ahead and take a look at a couple of those and try them. We'll look forward to discussing confidence intervals more in class and continuing to work with them in inferential statistics. We'll see you in class. A significant part of statistics is testing a claim to see if we can really believe it's true. So that's going to be our question for the day, is how do we test a claim? And today we're going to specifically focus on a claim for a proportion. The process we're going to talk about, though, does work for all sorts of claims, but specifically today we're going to stay in the context of a proportion. The way we test claims in statistics is what is called hypothesis testing. And the idea behind hypothesis testing is it's this clear process we can do to test if a claim is true. What we'll do is we'll first set up two hypotheses. And they're going to be contradictory hypotheses. Either the first one or the second one is true. The first one we'll call h sub 0. That is what we will call the null hypothesis. And it will always include, it will always use equals. Some variable equals something. And another thing about the null hypothesis is we will always assume the null hypothesis is true until proven otherwise. If the null hypothesis is not true, the other hypothesis is h sub a, which we call the alternate hypothesis. And this is often what we're trying to show to disprove a claim. And this will either use greater than, less than, or not equal to. Kind of the alternative choice. If it's not equal to a number, it must be different than it. And then once we've set up those two hypotheses, we will run a sample or an experiment. And then based on that experiment, we will calculate the probability, the null hypothesis is true based on our sample. This calculation that the null hypothesis is true based on our sample is what we will call the p-value. It's going to be very important to us, the p-value. What is the probability the null hypothesis is true based on our sample? Once we know that probability, we will compare it to the all-important alpha. Alpha, actually no period, we'll just say or the smallest probability that we will still believe the null hypothesis is true. So if our probability, our p-value, is smaller than alpha, that is too small of a probability to still believe the null hypothesis. And so we will have to reject the null hypothesis in favor of the alternative because our p-value was too small. It was smaller than alpha, the smallest probability we still believe the null hypothesis is true. Or the p-value might be bigger than alpha. There is a greater probability that it is actually, the null hypothesis is true, and then we won't reject the null hypothesis. So step 5 is simply either to, make me a little more space. We will either reject the null hypothesis and we do that if the p-value is less than alpha, because the probability was too small to still believe the null hypothesis. Or we will fail to reject the null hypothesis. And that's the case where the p-value is greater than alpha, or it's just too big of a probability to believe that the null hypothesis is false. A great example to kind of show how hypothesis testing works is to consider a trial. In the United States, we assume in a trial that a person is innocent until proven guilty. And it's actually a perfect statistical hypothesis test. Let's say person A is accused of a crime. The null hypothesis that everyone assumes is true until proven otherwise is that person A is innocent. The alternative hypothesis, what we try and prove or find enough evidence, is that the person is guilty. And what we always do is we assume innocent until proven. That proof is the p-value. What is the probability that they're innocent, given there's all this proof that they are guilty? And not just proof that they're guilty, because you never know for sure they're guilty. We just prove they're guilty beyond a reasonable doubt. And that reasonable doubt, that is the alpha. If you go beyond alpha, if p-value gets smaller than alpha, the proof of innocent is so small, we can no longer assume they're innocent. And there's actually two conclusions that we can make. If proven guilty, if the p-value is so small that they're innocent, the probability they're innocent is so small it's beyond a reasonable doubt, we reject the null hypothesis and conclude the defendant is guilty. If not, at least not beyond a reasonable doubt, we will fail to reject the null hypothesis. and conclude, and this is where it gets interesting, and it's very important in statistics, we don't conclude they're innocent. We conclude that they are not guilty. The conclusion focuses on the alternative hypothesis. What's key there is that we never conclude the null hypothesis, h sub 0, is true. We just failed to conclude the alternative. We didn't say they were innocent. We just said there's not enough evidence to say they're guilty. And that's an important conclusion that applies to statistical conclusions as well. We will never conclude the null hypothesis is true. We will always conclude that the alternative hypothesis could not be proven or could be proven. Speaking of conclusions, let's talk about how we want to make our conclusions. Similar to how we interpreted a confidence interval for a proportion, when we make a conclusion, it's really important we make that conclusion in context. But we also are going to focus on the alternative hypothesis, the h sub a. And so a nice script we can follow is we will say there is, or there is not, depending on the context. We will say not if we fail to reject, because we did not get the alternative hypothesis like we wanted. So there is or there is not sufficient evidence to conclude whatever we can conclude. The conclusion, though, is always going to be the alternative, or the alternate hypothesis in context to the problem. Let's do two examples where we can really see what this hypothesis testing thing looks like. Example. First, for doing hypothesis tests specifically with proportions, everything we've done so far actually applies to all hypothesis testing, but specifically with proportions, there's a few formulas we need for proportions. First off, we know that proportions are normally distributed with the proportion acting as the mean and the square root of PQ over N acting as the standard error. But as you calculate these values, different than a confidence interval, because a confidence interval focused on the sample and what we could learn from the sample, we used P and Q from the sample. Here, we're focusing on a null and an alternate hypothesis, so we're going to focus on the claim that the null hypothesis is true. Use the null hypothesis values. And then, to calculate our p-value or our probabilities, we will have z is equal to p hat, the sample proportion, minus p, the hypothesized proportion, divided by the standard error. And remember, the standard error is the square root of PQ over N. So let's try this. Let's say a phone company claims that 43% of smartphone users have an iPhone. But you doubt this claim. So you conduct a survey. Of 83 smartphone users. "44 of them use an iPhone." What can you conclude if alpha equals 0.05? In other words, we're going to believe the claim of 43% until the probability dips below 5% that that claim is actually true. Well, let's set this up. Our null hypothesis has to be that our proportion equals something, and that's the claim that the proportion equals 0.43. For the alternative hypothesis, we can either say the proportion is greater than, less than, or not equal to. There's no direction given in your doubt. When you doubt the 43% is accurate, you're not saying that it's greater or less than. You just doubt that it's accurate. So this is going to actually be not equal to 0.43. And when it's not equal to 0.43, we have what's called a two-tailed test. And what that means is we could reject the null hypothesis if the proportion is bigger or if the proportion is smaller, either direction. Maybe it'd be easier to see if we drew a picture, and we're going to annotate this picture as we go on. Here's the normal curve for the proportion. The claim is that the proportion is 0.43, but we doubt that's true. We think it's either going to be lower, somewhere in the red tail on the left, or higher, somewhere in the red tail on the right. We don't know which side, we just doubt it. It's in both tails, left and right. The distribution, then, of the proportion, just to review, we know that the proportion of our sample will be normally distributed. And again, we're going to use the null hypothesis here. Around the claim of 0.43, with a standard error of 0.43, that's our p, times q, 1 minus 0.43 is 0.57, over my sample size, and here we did a survey of 83 people. So what that really means is our proportion is normally distributed with a mean of 0.43 and a standard error of 0.0543. So, what is our sample proportion? Well, our sample proportion is going to be x divided by n, or the 44 out of 83 people who used the iPhones. That's going to be 0.53. Run out of colors, so we'll go back to blue. Actually, one thing to put in, since we know our proportion is 0.53, on my picture off to the right, I'm going to put 0.53. That is the x value where the red shading starts. We don't know the value on the left. If our proportion had ended up being less, we would have put the number on the left. But because our proportion was more, we put it on the right. Now we're ready to calculate our z-value. And z is our sample proportion minus the hypothesized proportion divided by the standard error. So 0.53, the sample, minus the hypothesized 0.43, divided by the standard error of 0.0543. The z-value there is 1.84. So if we have x's on top, we'll stick z's down below. I should have left a little more space. When it's a z, we assume the mean is 0, and our value on the table is 1.84. So let's go to the table and see what area goes with a z-value of 1.84. On the table, we're looking at 1.84. So if I scroll over, and if I draw my line straight, we see 1.84 corresponds to an area of 0.4671. But remember, with that area of 0.4671, that is the area in white, 0.4671. We are interested in the area in the tail. To get the tail, we have to subtract from 0.5. That'll give us 0.0329. But what's important to know is because this is a two-tailed test, we have to consider the other tail as well is 0.0329 as well. It's symmetrical, which is nice. So when we want to calculate the p-value, the p-value is the total shaded area. Because this is a two-tailed test, we have to add them together. The 0.0329 plus 0.0329. That gives us a p-value of 0.0658. And remember that p-value is the probability our null hypothesis is true based on our survey. In other words, based on our survey, there is a, change it to a percentage, 6.58% chance the proportion of iPhone users is actually 43%, what the null hypothesis claims. Now, at first glance, you might say that's not a very large percent. But remember, we did say up at the top here that alpha is 0.05. And that means we will continue to believe the null hypothesis is true as long as the probability does not dip below 5%. So if the p-value is 6%, that's not below the 5% threshold, we say that still is not quite enough evidence to kick out the null hypothesis. So our decision is we will fail to reject the null hypothesis, because there's just not quite enough evidence. It was close, but not quite enough evidence to reject the null hypothesis. The reason for that, really clearly stated, is the p-value, the probability the null hypothesis is true, is greater than that alpha, that minimum threshold. Putting the numbers in there, the p-value is 0.0658. That is greater than the alpha of 0.05. So we failed to reject, and we're ready to make our conclusion. Following our script, then, we will say that there is not, because we failed to reject, we'll say not sufficient evidence to conclude. And the conclusion must be in context of the alternative hypothesis. So we're going to state the alternative hypothesis, that the proportion's not 43%. Of course, we must put it in context. So to conclude, the proportion of iPhone users is different than 43%. Now, one thing you might notice is there's a couple of p's going on in here in problems like these, and it's very important we keep them all straight. We have a p-value. That's just the probability the null hypothesis is true. We have a p in the null hypothesis. That is the claim for the population proportion. And we also have a p hat. That is the sample proportion. Be very careful not to get the three p's mixed up. Quite often we'll see students compare the wrong p to alpha, and they'll make the wrong conclusion as a result. Make sure you compare the p-value to alpha to make a conclusion about your p based on your p hat. Sounds confusing, but practice a few to make sure you get them straight. Just to kind of make this interesting, and this isn't always required, but it often is with a hypothesis test, is let's make a 95% confidence interval for the true proportion based on our sample. So based on our sample p hat, our sample we said was 53%, which means q hat, the opposite of that is going to be 1 minus that, or 47%, 0.47. And if we're doing a 95% confidence interval, we should know the z sub alpha over 2, or z sub 0.05 over 2, or z sub 0.025, is equal to 1.96. And we found out in our previous lesson that the error is equal to that z value of 1.96 times the square root of pq over n. But with the confidence interval, notice I will use the sample data. This is different than the hypothesis test where we use the hypothesis. With the confidence interval, we use the sample data of 0.53 times 0.47 divided by the sample size, which was 83. And that will give me an error of 0.107. So my confidence interval then is the proportion 0.53 minus the error of 0.107, and the sample proportion of 0.53 plus the error of 0.107, giving me a confidence interval for the true population proportion to be between 0.423 and 0.637. Or in context, we're saying that we are 95% confident the true population proportion of iPhone users, always put it in context, is between 42.3% and 63.7%. And what you notice is with that confidence interval, our null hypothesis said what we were assuming to be true, the null hypothesis said the proportion was equal to 0.43. Notice that 43% is within that confidence interval. That's why we cannot reject it, because it still is a valid possibility for the true population proportion of iPhone users. I want to do one more example. I know this video is running a little bit longer than normal, but it's really important that we're comfortable with these hypothesis testing. So, it has been claimed that 58.4% of web users prefer Chrome. However, you believe the number is lower. So you're going to test it. You sample 152 web users. And 74 of them use Chrome. With alpha equal to 0.01 this time, we want to be very confident. We're going to go all the way down to a 1% error. What can you conclude? Well, like before, let's start with our hypotheses. The null hypothesis is that the proportion equals what they claim it equals. The claim is that it equals 0.584. The alternative hypothesis is based on what you're trying to show. And this time, we're going to try and show that the actual number is lower, that the proportion is less than 0.584, which means this time we really have a one-tail test, or better said, a left-tailed test. Meaning we're going to reject the null hypothesis if we end up far out into the left tail. Drawing a picture, the hypothesized mean is at 0.584. We're going to reject if it's less than, significantly to the left, or in that left tail. So we have our distribution. We know that the proportion is normally distributed at 0.584 with a standard error of, using the null hypothesis, 0.584 times q, which is 416, sorry, divided by the sample size of 152, which means it's normally distributed at 0.584, comma 0.0400 when we round. If that's the distribution, then we're going to compare it to the proportion, or the p-hat, that we get from our sample. Our sample said 74 out of 152 use Chrome. 74 out of 152 is 0.487. That's the value off to the left. It's less than 0.487, where the shading starts. Is that far enough away that we can make a conclusion that it's actually less than? Well, to do that, we will go to our z-value, which is equal to our sample proportion of 0.487 minus the hypothesized proportion of 0.584 divided by the standard error of 0.0400. Our z-value is negative 2.43. So we've got our x's on our picture. Putting those all into z's, the mean is 0, and the z-value of negative 2.43 is where the shading starts. Let's go to our z-table. And I got to scroll down a bit to see 2.43. So 2.43. Looks like this time we're going to have a z-value of 0.49. I'm sorry, an area of 0.4925. But that's the area in between of 0.4925. We need the area in the tail, which is just 0.5 minus that, or 0.0075. This time we don't need to worry about the other side because it is a one-tailed test. So my p-value is just that shaded area, the 0.0075, which means based on our survey, there is a 0.75% chance the null hypothesis is true, or the proportion of Chrome users, or people who prefer Chrome, probably would have been a better way to say that, is 58.4%. That is really, really small p-value. In fact, what's really important is when we compare that p-value to our alpha of 0.01, it is actually less than that alpha of 0.01, which means that's too much evidence to the contrary. So we will make a decision to reject the null hypothesis. And the reason for that decision is because the p-value, the probability it's true, is less than the alpha, or specifically 0.0075 is less than the 0.01 minimum threshold. So our conclusion? If we reject the null hypothesis, we will say that there is sufficient evidence to conclude. And then we will state the alternative hypothesis in context, focusing on being less than the 0.584. To conclude, the proportion of web users who prefer Chrome is less than 58.4%. One last little thing as we wrap up our conversation on hypothesis testing is when all is said and done, we make a conclusion based on a p-value. What's the probability that the null hypothesis is true? Do we reject it? Do we fail to reject it? But when all is said and done, at the end of the day in statistics, we could be wrong. And we really have no way of knowing if we're right or wrong. We can be fairly confident, 95% or 99% confidence, but we could be wrong. And there's two types of errors in statistics that we always try and minimize. We call them type 1 and type 2 errors. A type 1 error is when we reject the null hypothesis when it is true. We should not have rejected it, but we did. The probability of that happening is actually the alpha that we're using in the problem. The other type of error is what's called a type 2 error. And that's where we fail to reject the null hypothesis when we should have, when it is false. And the probability is not as evident for that. We call that probability beta. It comes up in more advanced statistics classes. We're not going to spend a lot of time on that. But you should be aware at this point of what a type 1 and type 2 error is in context. So we did two examples today. The first example was about iPhones. And we failed to reject the null hypothesis. We could have committed a type 2 error, where we conclude not reject, or failed to reject, when we should have. Or to put it in context, and this is probably a better way to say it, or we believe the proportion of iPhone users is 43% because we failed to reject it, but we should have, when it is not. It is not actually 43%. We should have rejected. That's a type 2 error. The second example, because we did reject, could have been a type 1 error, where we conclude reject when we should not have. Or, to put that in context, we currently, after running that sample, we believe the proportion who prefer Chrome is less than 58.4%. Because that's what we concluded. But it's not. That would be a type 1 error, where it's actually either equal to or possibly greater than 58.4%, and we made the wrong conclusion. Those errors hopefully don't happen often to us, but there's always a chance that they could happen, because with hypothesis testing, we're never sure of anything. We could be wrong. And that's what the type 1 and type 2 errors tell us, is what does it mean if we're wrong? So we covered a lot of stuff in this video today. We introduced the concept of what a hypothesis test is and how hypothesis test works. And then we did several hypothesis test examples in the context of proportions. And then really briefly at the end, we talked about we could be wrong, the type 1 and type 2 error. So take a look at the assignment if you want to try a few of these. A little bit of a longer video, but some of the next few are going to be much shorter to make up for it. So we'll see you in class. Now that we've taken a look at how hypothesis testing works, specifically in the context of one proportion, we can extend it to hypothesis testing in many different situations. And one of those situations involves having two proportions, or two groups, and trying to decide, are the two groups the same, or are the two groups different? So our question for the day is, how do we test a claim about two proportions? We're going to have two groups, and we want to know, are these two groups the same? Is one group bigger? Is one group smaller? What can we conclude about these two proportions? And the idea of the hypothesis test is identical to the idea that we did with one proportion. The only difference is we have a few different equations needed to find the test statistic. First thing we need to know is what we're going to call the pooled proportion. The pooled proportion is what the proportion would be if the groups weren't separate. So if we weren't comparing men and women, but we were just looking at people, how many successes are there out of the total group? The pooled proportion we represent with P sub c. The pooled proportion is equal to the sum of the successes from the first group and the sum of the successes from the second group, divided by the number in the first group plus the number in the second group. And as a tip, if you do this on your calculator, you will probably need to put parentheses around the numerator and denominator to make sure that division happens in the correct order, because a proportion should always be between 0 and 1. If your proportion's not between 0 and 1, check the order of operations. So this is our first important formula, finding the pooled proportion in order to test the two proportions, if there was no separation of the groups. The second formula you need to know is the distribution for two proportions. When we compare two proportions, we don't just compare them. What we actually do is we take the first proportion of our sample and subtract the second proportion of the sample. We're actually looking at the distribution of the difference between the proportions. And they are normally distributed, as you might expect. And if they are the same, we should have a difference of 0. The standard error formula is a little bit more involved, but not difficult. It's the pooled proportion times 1 minus the pooled proportion, which might be the pooled Q, times 1 over the first sample size plus 1 over the second sample size. And so that is the second key thing we need, specifically because it is going to help us find the standard error. That big square root is the standard error that we need to calculate the test statistic. With the normal distribution, the test statistic is z. And the test statistic here is going to be the difference in the proportions, p hat a minus p hat b, divided by the standard error. So that's the third new equation we need. Other than that, everything is identical to what we've seen before. So we should be able to jump right in to an example where we will compare two proportions. Let's say a restaurant wants to know if teens are more likely to order dessert than adults. Knowing this information can help them plan their future marketing campaign, so they contact a sample of 84 adults. $33 order dessert. They contact a sample of 91 teens. 46 order dessert. Can they conclude teens are more likely to order dessert if our alpha level equals 0.10? Notice this example is different than when we had one single mean. When we had one single mean, there was a global claim that said the proportion is equal to such and such a percent. Here we don't have any such global claim. Here we're doing a sample of two separate groups, and then we're going through and comparing, are these two separate groups different, or are they the same? So setting up our null hypothesis, the null hypothesis is always going to have equality. So the null hypothesis is that the proportion of the teens who order dessert is equal to the proportion of adults who order dessert. Notice I use a subscript on each of the p's so I know which one is which, T for teens and A for adults. That way when I set up my alternative hypothesis, we want to know, are the teens more likely to order dessert? They want to know if the proportion of teens is greater than the proportion of the adults. What we have actually is a right-tailed test because we are going to reject in the right tail. Drawing our little picture. The mean, the assumed difference, the hypothesized difference is that there is zero difference between them. The order of my hypothesis tells me the order of the subtraction. We always subtract left to right. So what we're really doing is the proportion of teens minus the proportion of the adults. We're claiming the teens are bigger than the adults. So we're taking a big number minus a small number. It should give us a positive number and something in that right tail. That's what we're going to attempt to find. Let's calculate some of the pieces that we're going to need in order to solve this. First, the proportion of teens. There are 46 out of 91 teens that order dessert. That's going to be 0.505. The proportion of adults who order dessert, that's going to be 33 out of 84, or 0.393. And then for our pooled proportion, if there was only one group, not two separate groups, and we just interviewed people, the number of successes would have been 46 plus 33. Over the number of trials would be 91 plus 84. Making sure I use parentheses so I don't get in trouble with order of operations. The pooled proportion is 0.451. We can use that information. Let's not scroll too far. Keep that hypothesis on there. We can use that information to find the distribution. We know the difference in the proportion between the teens and the adults is normally distributed with a mean of 0 and a standard error equal to that big square root. The pooled proportion of 0.451 times 1 minus the 0.451 times 1 over the first sample size of 91 plus 1 over the second sample size of 84, or normally distributed with a mean of 0 and a standard error. If if you put that in your calculator, of 0.0752. Now that we know the standard error and the distribution, we can calculate the z-value, the test statistic. Let's label it test statistic. The difference in the proportions, we're going to do the same order as the hypothesis. So we have to do the teens minus the adults. 0.505 minus 0.393 over the standard error of 0.0752. Now, just so I can label it on my picture, let's do the subtraction in the numerator. 0.505 minus 0.393. The actual difference is 0.112 divided by the standard error of 0.0752. So on my picture, the actual difference is 0.112. And when we divide by 0.0752, we get a z-value of 1.49. So if we've got x's in the top row, z's in the bottom row, z's also have a mean of 0, but now the z-value is 1.49. That 1.49 is what we want to look up in the table to find our p-value. Looking at our table then, we have 1.49, so 1.49. That's going to give us an area of 0.4319. So our area of 0.4319, but the p-value is the area in the tail. So we subtract from 0.5 to get 0.0681. So our p-value is 0.0681, which means the probability, or given our sample, I should say, given our sample, the probability the proportion of teens and adults who order dessert is the same is 6.81%. Probability they both order dessert at the same rate is 6.81%. That's what the p-value means. We said we wanted our alpha to be 0.10, which means we will believe the null hypothesis. We will believe the proportions are equal as long as the probability is bigger than 10%. We got a probability of 6%, so our decision is to reject the null hypothesis. And the reason for that decision is our p-value is less than our alpha. There's a 6.81% chance, or let's not do it as a percent, a 0.0681 p-value, which is less than the alpha of 0.10. So we reject the null hypothesis. And we're ready to make our big conclusion. The script for the conclusion remains exactly the same. Because we rejected the null hypothesis, got the alternative we were looking for, we will say there is sufficient evidence to conclude. And then we will go back and state the alternate hypothesis in context, that teens are greater than adults. The proportion of teens who order dessert is greater than the proportion of adults who order dessert. The conclusion is in context. It focuses on the alternative hypothesis. You should feel like what we just did was very, very similar to the hypothesis testing for a single mean. The only difference that we had to do was we had to find this pooled proportion and a new standard error to calculate our test statistic. But the process of the hypothesis test remains the same regardless of what we're testing. So take a look at practicing some of these. We're going to do some of this in class. We'll look forward to seeing you then. Just as we have done inferential statistics with proportions, we can do many of the same things with means. In fact, we more often are working with means than proportions. So let's answer the question first. How do we find a confidence interval for a mean? Very similar in idea to find a confidence interval for a proportion, but there's one key difference with the means is normally when we do a sample and we have a mean of the sample, we do not know the standard deviation of the population. We only know the standard deviation of the sample, which means the normal distribution will be a little bit too tight or a little bit too small to calculate a reliable confidence interval because we're only estimating the standard deviation of the population with the standard deviation of the sample. So if we have no standard deviation, of the population, we can no longer use the normal distribution. We need a different distribution. And the distribution we will use is called the student's t-distribution. Or often you'll hear it just called the t-distribution. The student's t-distribution is very similar to the normal distribution, but it allows for greater flexibility as we will use the sample standard deviation to estimate the population standard deviation. And that's never perfect. It's probably close, but it's never perfect. And that's why we need that extra flexibility that the student t-distribution gives us, is it allows us to still make a confidence interval with a little bit extra flexibility. And it turns out that, and it makes sense as well, the larger the sample size, the less flexibility is needed. And that makes sense, as if we interview more and more people getting closer and closer to the population, our estimate for the standard deviation is probably going to be more and more accurate. And the more accurate we are, the less flexibility we need. It turns out that we have to adjust the student t-distribution then based on the sample size. And we call that estimation the degrees of freedom. The degrees of freedom is often abbreviated df for degrees of freedom. And it's very easily calculated as n minus 1. The degrees of freedom is n minus 1, one less than the sample size. And it turns out that if the sample size is greater than 30, the student t is almost identical to the normal distribution. And so when we have a sample size bigger than 30, we end up using normal values because they're so close together. But if the sample size is less than or equal to 30, then we will use the student t table for finding critical values. This table shows us the amount of area that we're going to get in a single tail of the t-distribution. You'll notice the shape looks very similar, but our degrees of freedom are going to determine the critical values that we need to calculate. So what we'll do is we'll first find out the degrees of freedom of our problem. Maybe we've got 11 degrees of freedom. Then we'll figure out how much area we want in one tail. Maybe we want 1% in one tail. The table would then give us the critical value that we can use to calculate a confidence interval. One more thing you'll notice is the very last row of the table is labeled z, because that's when we pass a sample size of 30 or 30 degrees of freedom. And at that point, the t-distribution starts to look like the normal distribution. And you should recognize several of the numbers in this row as the critical values we used with proportions. Those are the z values that give us the area we want in each tail. So once we're past 30 degrees of freedom, we'll just use those normal values. Well, now that we're kind of familiar with this idea of the student t-distribution that we have to use if we don't know the population standard deviation, let's talk about how we can use that to make a confidence interval for means. First off, the distribution for the mean, if we don't know the standard deviation, we'll just say is t with a subscript that is the degrees of freedom. And remember, the degrees of freedom is equal to 1 less than the sample size. So that's the distribution we're working with, the t-distribution. So we need to calculate an error that exists between the population and the sample mean. That error, actually we'll do a colon, that error is equal to our t sub alpha over 2, very similar to our z sub alpha over 2, but this time we'll use the t table and the correct number of degrees of freedom, times the standard deviation of the sample divided by the square root of the sample size. And once we know the error, we can find the confidence interval. And very similar to proportions, with the confidence interval, we will subtract and add the error to our statistic. So we'll take our x bar and we'll subtract the error to get our low value, and our x bar and we'll add the error to get our high value. And that's the confidence interval using the error we just calculated. These three pieces will work together to get us our confidence interval. So let's try an example. You are interested in the average cost of a smartphone. So you take a sample of 16 smartphones and find a mean cost of $531 with a standard deviation of $83. We are going to, number one, construct a 90% confidence interval. A couple things we need to know to conduct this 90% confidence interval. First, our alpha, the amount of area in both tails, if it's a 90% confidence interval, is going to be 0.10. So the alpha over 2, looking at just one tail, is half of that, or 0.05. For our t distribution, we need to know the number of degrees of freedom. The degrees of freedom is always 1 less than the sample size. So we've got 16 smartphones minus 1. We have 15 degrees of freedom. And so now we're ready to calculate our t value. That has 0.05 in the tail and 15 degrees of freedom. Going down our degrees of freedom on the table, we want 15 degrees of freedom. And we want 0.05 area in that tail. So we go down and across, and we find a t value of 1.753. 1.753. Now we're ready to calculate the error. The error is that t value, 1.753, times the standard deviation of my sample size, which was $83, divided by the square root of my sample size, which is 16. And putting that on my calculator, we get an error of $36.37. So if that's the maximum error between my sample mean and the population mean, we just have to subtract and add it to my sample mean. The $531 minus the error of $36.37, and the $531 plus the error of $36.37 gives me a 90% confidence interval of $494.63. up to $567.37. And very similar to how we constructed a confidence interval with proportions and then interpreted it, we will also interpret the confidence interval for the means following almost the exact same script. We estimate with 90% confidence the true population, and then state the parameter in context, mean smartphone cost is between $494.63 and $567.37. So as we can see, constructing a confidence interval with a mean is very similar to how we constructed a confidence interval with a proportion. We've got a different distribution, a slightly different formula for the error, but the exact same idea. So you should be able to try a few of these, and we'll talk about confidence intervals a little bit more in class. Now that we've gotten comfortable with working with the t-distribution and making a confidence interval for a mean, we're ready to do a hypothesis test for a mean. So the question we're going to answer is, how do we conduct a hypothesis test for a mean? And the process of a hypothesis test is always the same, whether we're talking about one proportion or two proportions, or in this case, one mean. The only difference is we have a few different formulas for the mean to help us calculate that important test statistic that will help create the p-value. First off, for the mean, the distribution, because we don't know the population standard deviation, the distribution of the mean is a t-distribution with a subscript for the degrees of freedom, one less than the sample size. The way the standard error is calculated, the standard error is equal to the standard deviation of the sample divided by the square root of n. And then we'll use that standard error to calculate our test statistic. And our test statistic is going to be t equal to the difference between the mean of the sample and the hypothesized mean divided by the standard error. So these are the three pieces that will help us find the p-value to conduct our hypothesis test. Now, because the t-distribution has a slightly different number based on the degrees of freedom, we need a slightly better way than just looking up a value on a table to calculate the p-value and our t's. The way we're going to do that is we're going to use our calculator. First, we have to set up the test. And the way we set up the test is you're going to hit the Stat button. Then you will scroll over to Tests. Then you will scroll down to the t-test. Once you set it up, you have to enter the stats from your study. Now, the calculator has an option of entering the data or entering the stats. We're going to enter the stats. So if needed, select stats. So the calculator knows you're going to actually enter in the stats. And the stats you're going to enter in, first it'll ask for mu sub 0. That is the null hypothesis. It's also going to ask you for x bar, which is the sample mean. It's also going to ask you for what they call SX, which is the sample standard deviation. Then it'll ask you for N, which is the sample size. We know that one. And finally, it'll ask for mu, which is the symbol in the alternate hypothesis. Whether that's less than, greater than, or a not equal to. I'll show you how this process looks on the calculator, but it really helps to have an example. So let's do that. Let's build an example. It is claimed the average page in a novel has 275 words per page. To test this claim, you sample 24 pages of a novel. And you find the average page has 260 words. With a standard deviation of 34 words. Do you believe the claim is true if alpha equals 0.05? Well, we start off every hypothesis test with a null hypothesis. Here we're talking about a population mean, and the claim is that the mean is 275 words per page. For the alternative hypothesis, we're not really saying it's less than or greater than. You just want to know, is the claim true? So what we say is mu is not equal to 275. And because we have that not equal, we're really dealing with a two-tailed test. Where we've got our normal distribution. The hypothesized mean of 275 is in the middle, but it actually turned out to be 260, which is less than it. But because this is a two-tailed test, we're going to shade both sides. Those are our x values. We're going to calculate t values off of the distribution. The mean is distributed as a t distribution because we don't know the standard deviation of the population. But we do know the degrees of freedom is 1 less than the sample size. So the degrees of freedom is 23. Let's go to our calculator then to calculate the t value and the p value. Again, that keystroke that we're going to do is first you're going to hit the stat button, which is right next to the arrow. Then we'll scroll over to test. Then we'll scroll down to the t-test. We are going to input the actual statistics, not the individual data values. So we'll highlight statistics. Mu sub 0 is the null hypothesis at 275. X bar is the sample mean. Our sample was 260. Sx is the standard deviation of the sample, which was 34. And n, the sample size, was 24. We're going to make sure we highlight the alternate hypothesis symbol, not equal to, and scroll down to calculate. When we do, you'll see the calculator gives us several things, but what we're interested in most is t and p. T, the test statistic, is negative 2.16, and p, the probability the null hypothesis is true, given our sample, is 0.0413. So let's record that. Our test statistic is t equals negative 2.16. We can add that to our picture to the left of 0. And the p-value is 0.0413. And what that p-value means then, that's the probability the null hypothesis is true. So based on our sample, the probability the average page in a novel having 275 words, that probability is 4.13%. And remember, we said alpha was 5%. 5% is the minimum probability where we will still believe the null hypothesis is true. 4% is less than that, so we can no longer believe the null hypothesis is true. So we will make a decision to reject the null hypothesis. And the reason for that decision is that the p-value is less than the alpha. The p-value is 0.0413, which is less than the alpha of 0.05. That is too little probability. There is overwhelming evidence to reject the null hypothesis. And so we make our conclusion. Following our script, we say that there is sufficient evidence to conclude. And then we state the alternative hypothesis in context. The alternative hypothesis was just not equal to or different than. So there is sufficient evidence to conclude that average number of words per page in a novel is not, or maybe we should say is different, than 475 words. Let's actually take this one step further and build a confidence interval for where we believe the actual mean number of words lies. Let's build a confidence interval. And let's just do a 95% confidence interval. Now we know the distribution that we're dealing with. We know the degrees of freedom off of that are 1 less than the sample size. The degrees of freedom we said was 23 because the sample size is 24 pages. So our degrees of freedom is 23. Alpha, the percent of chance that we're going to be wrong, is 0.05, the opposite of the 95%. So alpha over 2 is 0.025. So we're looking for a t sub 0.025 that has 23 degrees of freedom in our table. Looking at our table then, we want 23 degrees of freedom. We want 0.025 in a tail. And so that tells us that the critical value we're using this time is 2.069. So t sub 0.025 is 2.069. We're ready to calculate the error that might exist between our sample mean and the actual population mean. Remember, the error is t sub 0.025 times the standard deviation divided by the square root of the sample size. So 2.069 times the standard deviation. We said the standard deviation was 34 words, divided by the square root of the sample size, which was 24. We end up with an error of about 14.4 words. So for our confidence interval, we will subtract and add that error to the mean we got in our sample. Our sample mean was 260. We'll subtract the 14.4 to get a low number. We'll add the 14.4 to get a high number. And so our confidence interval is 245.6 through 274.4. And you notice the hypothesized mean of 275 is outside of that confidence interval, which is related to why we ended up rejecting the null hypothesis. Let's go ahead and interpret it. We can estimate with 95% confidence the population, and we're talking about a mean, and put it in context, number of words per page in a novel is between 245.6 words and 274.4 words. And now we have our confidence interval. So hypothesis testing with a mean, it should feel very similar to hypothesis testing with a proportion because the process of a hypothesis test is identical regardless of what we're studying. The means are nice because we can use the calculator to make things a little bit shorter and quicker for us, but the philosophy behind the hypothesis test is still exactly the same. So try and take a look at a few of those. We'll look forward to trying a few of these in class and answer any questions that you might have. We'll see you then. The next type of hypothesis test we're going to turn our attention to is a hypothesis test for two means, as we attempt to answer the question, how do we compare two means? And just as is the case with all the other different hypothesis tests, the process is exactly the same. The only difference is we have some formulas to help us set up our test statistic. First, the distribution for comparing two means. When we're comparing two means, we want to know if two separate groups have the same average. Is there a difference between the two groups, or is one group higher or lower than the other group? And when we're interested in comparing them, what we're really comparing is the difference, or the mean of the first group minus the mean of the second group. And because we don't know those population standard deviations, it's going to be a t-distribution with a subscript that represents the degrees of freedom. Now, the degrees of freedom is an ugly formula. If you really want to know what it is, you can look it up in your book. It is in the section in your book preceding the practice assignments that we're doing for today. It's ugly. We are going to cheat, and we will use a calculator. We'll also use a calculator to find the t-statistic, but just so that we have it, the standard error for two means is the square root of the first standard deviation squared divided by the first sample size plus the second standard deviation squared divided by the second sample size. And then we use that standard error to calculate our test statistic, t, which is the difference in the means, a and b, divided by the standard error. But as was the case with the t-distribution with one mean, it will be also the case with the t-distribution with two means that we will use the calculator to do the hard calculations for us. The setup is identical. First, you will hit the Stat button. Then you will scroll over to Tests. And then you will scroll down, but this time you're going to scroll down to select the two sample t-test. Once you're in the two sample t-test, you will enter all the stats we have from our problem. And again, if the calculator is expecting you to enter the data, we're not going to enter the data, so you might need to highlight stats if needed. When you get in there, the first thing it's going to ask you is for x bar 1. That is the first sample mean. Then it will ask you for sx1. That is the first sample standard deviation. And it'll ask you for n1, which is the first sample size. So we enter in all the information about the first group that we're going to compare to the second group, which, as you might expect, you'll see x bar 2, sx2, and n2 is for the second sample that we will compare it with. Then it will give us a mu, which is the alternate hypothesis symbol. We need to tell the calculator, is this a one-tailed test or a two-tailed test, and which direction it is. And finally, the last thing the calculator will ask us for is if we have pooled data, and for our purposes, the answer is always going to be no. We are not pooling the data. And I'll show you what this looks like on the calculator again, but again, it's going to be easiest to see it if we have an example to work with. So for our example, you want to know if there is a difference in GPA of online students and face-to-face students. So to determine this, you survey 32 online students who have an average GPA of 3.45. With a standard deviation of 0.7. You also interview 41 face-to-face students who have an average GPA of 3.67 with a standard deviation of 0.4. If alpha equals 0.10, can you conclude the groups are different? We're comparing the average between the two groups, not just a claim and testing against the claimed GPA. We just want to know, is there a difference between these two groups? We have two means that we're comparing. Well, the mean of the online students is hypothesized then to be the same as the mean of the face-to-face students. Again, I'm using subscripts to make it really clear which group I'm talking about. The null hypothesis, no difference. They are equal. The alternative hypothesis is going to be either one is greater or they're not equal to each other. This example didn't give me any inkling of a direction. They didn't say face-to-face are higher or GPA or online students have a lower GPA or anything like that. So we are just looking to see if the online students are not equal to the face-to-face students, which means we have a two-tailed test. In other words, we have our t-distribution with our hypothesized difference. We hypothesize that the difference between the GPAs is 0, and we'll reject on either tail. Whether it's higher or lower, we will reject on either tail. Well, the actual difference, let's add that to our picture. The actual difference in GPAs, and we have to subtract in the same order of the hypothesis. So the online GPA has to come first. The online GPA was 3.45. And we subtract the face-to-face GPA of 3.67, and we end up with 0.22. to negative 0.22. So negative 0.22 is the x value we're looking for. We need to figure out what the t values are. Well, our distribution the difference between online students and face-to-face students is a t-distribution, but we don't really know the degrees of freedom because it's got that ugly formula, so we're going to go to our calculator. Again, on the calculator, the way we get to the test is we'll go to Stat. It's right next to the arrows. We'll scroll over to Test, and we'll scroll down to the 2-sample t-test. Make sure Stats is highlighted because that's what we have. Our first group, the online students, we said the online students have an average GPA of 3.45 with a standard deviation of 0.7. And we said that there are 32 of them. The second group, the face-to-face students, have an average GPA of 3.67 and a standard deviation of 0.4, and there were 41 of them. We select an alternate hypothesis of not equals. Pooled is going to be no for our purposes. And when we hit calculate, you'll see the calculator gives us the 3 key pieces of information we need. The degrees of freedom to finish out the distribution. Notice it's an ugly decimal. That's very common with 2 samples. And a t-value and a p-value. Let's copy that information over. So the distribution had 46.5 degrees of freedom. The t-value that came off the calculator was negative 1.59. So negative 1.59 to the left of 0. And a p-value equal to 0.1193. What does that p-value of 0.1193 mean? Well, remember, the p-value is the probability the null hypothesis is true given our survey. So based on our survey, the probability the average GPA is the same for online and face-to-face students is 11.93%. And we compare that p-value to the alpha, which is the smallest probability where we would still believe the null hypothesis is true. We have a greater probability, so we're going to go ahead and say our decision, because the probability, the p-value is bigger than alpha, we will fail to reject. And the reason for that is the p-value is greater than alpha. There's more evidence for the null hypothesis. The p-value is 0.1193, alpha is only 0.10. And so for our conclusion, in context, because we failed to reject, we say there is not sufficient evidence to conclude, and then we will state the alternate hypothesis in context, that there is a difference between the means. There is a difference between the mean GPA of online and face-to-face students. Again, we should start to feel really familiar and comfortable with this process of going through a hypothesis test. It's exactly the same regardless of if we're testing 1 or 2, means or proportions. The process is exactly the same. The only tweak that's different each time is actually calculating the distribution and the test statistic. But we should be very good at the process of setting up and conducting the hypothesis test by now. So you can take a look at those on the assignment. We'll work out with them a little bit more in class, and we'll look forward to seeing you then. Another hypothesis test we can do is hypothesis testing with what are called matched pairs. Matched pairs are where we have before and after data, and we are looking to see, are things the same, or was there some type of improvement? Or maybe we'll pair together couples and see if there's a difference between, the husband's score and the wife's score. Or maybe we'll pair together twins to see if there's any difference between the twins. Or maybe we'll compare your left hand to your right hand. But the data is paired together, and we're looking to see if there's any type of difference. That is matched pairs. And so the question we're going to ask is, how do we hypothesize test for improvement? Or maybe it'd be better to say a difference. Has there been any change? And this is that idea of matched pairs. All the data comes in pairs, and the pairs are matched together. Usually we have that before or after score. And the way matched pairs work is we're going to do a t-test for one mean, just like we did a t-test for one mean before. The only difference is we will first find the difference for each pair. And then we'll use those differences as our one variable to figure out whether or not there is a positive, negative, or no difference between the before-after data. So with that in mind, we've got some equations that we need to know to run this test. The distribution, it's very similar to the t-test distribution because it is a t-test. The only difference is we're going to put a little subscript of d on the x-bar to represent the average distance. Is a t-distribution with a subscript representing the degrees of freedom, where the degrees of freedom is simply the sample size minus 1. And then we can calculate the standard error. And the standard error is simply the standard deviation of the differences divided by the square root of the sample size. And we can use that standard error to find our test statistic, which, very similar to the test statistic for a single mean, is t is equal to the difference between the average difference and the hypothesized difference divided by the standard error. And the hypothesized difference is usually 0. We usually assume there's no difference between before and after scores, and we're looking to see, is there a difference, or is it positive or greater than 0, or is it negative or less than 0? Now, like before with the t-test, though, we're going to save all that work with using our calculator to do a lot of the manual crunching of the data for us. So first thing we're going to have to do on our calculator is we're going to have to tell the calculator all of our data. So here's how you enter the data into your calculator. You're going to start by hitting the Stat button. And then you will select Edit to edit a list. And the edit feature will already be highlighted when you hit Stat. So you just really have to hit Enter. And then in L1, you're going to enter the before data, or the first set of data. And then in L2, you will enter the after data, or the second set of data. And then for L3, what you're going to do is you're going to scroll up and highlight L3 and do L2 minus L1, and the calculator will automatically subtract and find all the differences and fill list 3 with the differences. Now the way we get that is you'll hit the second button, and you'll hit the number 2, which will give you L2, minus the second button, and then you'll hit the 1, which will give you the L1. And now in L3, you will have a list of all of the differences between the before and after. A positive difference means it got bigger. A negative difference will mean it got smaller. Then you're ready to actually run the t-test. So you can hit Stat, scroll over to Tests, and then scroll down to t-test. And even though there's 2 sets of data before and after, we're actually just working with the differences. So it's just one t-test. Don't do the 2-sample t-test. It's a single sample t-test. That single sample is the difference between the before and after, checking to see if the numbers went up or down. So when you're running the t-test, you have to enter in some information. First thing you want to do is you want to highlight data, because you have entered the data into the calculator. We don't have the summary statistics. We actually entered the data this time. And that is different than our last t-test. Then you'll see mu sub 0. That is the hypothesized difference. Which is usually 0. We usually hypothesize that there's no difference, or that the difference equals 0. Then it'll ask for the list. The list you want to be L3, where you have all those differences entered. And the way we select L3 is you hit the second, and then the number 3 will give that third list. And finally, we'll enter in mu, which is the alternate hypothesis symbol. Are we looking for it to be smaller after the treatment, bigger after the treatment, or just not equal to 0 after the treatment? And as before, this is a lot easier to see with an example. So let's do an example where we check these matched pairs for some type of improvement. A football coach wants to know if a strength class can help improve his players' bench press weight. The before and after data is below. So we're going to have players. We'll just mark the players with letters to protect their identity, A, B, C, and D. And we'll have weights for before the class and after the class. So before the class, A benched 205. After, A benched 295. That looks pretty good. Before the class, B benched 241. After, B benched 252. Not as dramatic, but still an increase. C benched 338 before the class and 330 after the class. C went down a bit. And D benched 368 and afterwards benched 360. So the question is, if alpha equals 0.05, can the coach conclude the class was helpful? We're going to run a hypothesis test of matched pairs to see if there's a significant difference. First, the null hypothesis is that the average difference is equal to 0. There's no difference. The alternative hypothesis is that the average difference is going to be positive or greater than 0 because the coach wants it to be helpful. He wants the difference to be positive. He wants it to be higher after than before. Which means we have a one-tail test, or better said, a right-tail test. If we were to draw a picture of this, the hypothesized difference is 0. Somewhere over to the right, we hope to see improvement. And we hope that right tail shows there was enough improvement out of the class. Well, our distribution is that the average difference is a t-distribution, and the degrees of freedom is 1 less than the sample size. There are 4 players. 1 less than that is 3. It's very small degrees of freedom. It's going to take quite a difference in order to say there's a difference. So from here, let's go to our calculator and see if it can help us find the differences. To enter our information into the calculator, we're going to hit the Stat button right next to the arrows. Edit is already highlighted. If I already had numbers in my list, let's say there were numbers already in here that I didn't want. If you scroll up and highlight the list and hit the Clear button and then Enter, it'll clear out the list, so there's nothing left in the list. The first list is for the before data, so we'll enter in our data 205, 241, 338, and 368. The second list is our after data. Make sure they're entered in the same order, 295, 252, and 330, and 360. Then list 3 is where we're going to put our differences. So if we scroll up to highlight list 3, and then we're going to say take list 2 and subtract list 1. Hit second, and then the number 2, That'll grab list 2 minus second, and then the number 1. And now I see list 3 is equal to 2 minus 1. When I hit enter, I will see all the differences. And that's the data we're going to use in our single mean t-test. To run the t-test, we'll hit Stat, scroll over to Test, scroll down to the t-test, and this time we've actually entered the data into the calculator. So we'll scroll over and highlight the data, enter. The hypothesized mean is 0. For the list, our data is in list 3. That's where the differences are. So we'll hit second and the number 3 to give us list 3. Leave the frequency alone. For the alternate hypothesis, we want to show that the mean is greater than 0. So we need to select the greater than alternate hypothesis. And then we're ready to actually calculate. When we do that, we get our t-value of 0.91 and a p-value of 0.2149. We're also told that the average difference is 21.25. So we can add that to our picture. The average difference is 21.25. But when we convert that to a t-value, the t-value was only 0.91. So the test statistic is that t equals 0.91, which gives us a p-value, an area for that tail of 0.2149. What that p-value means is, given our sample, the probability, the strength class, made no difference in bench press weight, because that's the null hypothesis, is 21.49%. There's a 21.5% chance that the class had no effect on bench press weight. And if we look at our alpha of 0.05, we see that is much bigger than the 0.05 alpha. Alpha is the minimum probability where we still believe the null hypothesis is true. We are well beyond that probability, much higher, so our decision is to fail to reject the null hypothesis. And the reason for that decision is the p-value, the probability that the null hypothesis is true, is greater than alpha, which is our decision break. With numbers, the 0.2149 is greater than the 0.05. And so for our final conclusion, we will state that there is not sufficient evidence. And then we state the alternative hypothesis in context. To conclude, the strength class increased bench press weights. And so what you see is with the matched pair hypothesis test, it really is exactly the same as a single mean hypothesis test with the t-distribution. The only difference is here we will focus exclusively on the differences. So first we have to calculate that after minus before relationship to see how much things have improved or decreased after the treatment. So that's how we do a hypothesis test for matched pairs. Take a look at a few of these on the assignment, and we will see you in class to continue to work on matched pairs a little more. Quite often we read a claim that a certain population is distributed in a certain way. Maybe we say that 20% fall in one category, 40% fall in another category, and 30% fall in another category. The question we're going to take a look at today is how good that fit actually is to data we might collect. So the official question here, how do we test if data fits a claimed distribution? And as we do this hypothesis test, we have to run into a new distribution that tests how well data fits a claimed distribution. And the new distribution is what we call the chi-squared distribution. And we use the Greek letter chi with a little squared on it. Looks like an X with tails on the ends. And this chi-squared distribution, a few characteristics of it. It is a non-symmetrical distribution. And it is skewed right. So unlike the normal and the t-distribution, which is perfectly symmetrical, the chi-squared is skewed right. In fact, the shape itself varies based on the degrees of freedom. There is a different shape based on the degrees of freedom. And another unique thing about the chi-squared is that it is always greater than 0. With the t-distribution and the normal distribution, we found it symmetrical around 0. We had positive values and negative values, representing if we were left or right of the mean. The chi-squared doesn't do that. The chi-squared actually starts at 0, and depending on the degrees of freedom, if there's only 1 degree of freedom, the graph looks something like this. But if we increase the degrees of freedom to maybe 3, it's going to look something like this, with a little hump skewed to the right. And the more we increase the degrees of freedom, that hump is going to move slightly over. So this red line might represent 10 degrees of freedom. And so you see the shape varies quite dramatically based on the number of degrees of freedom we have. So let's look at how we can use the chi-squared distribution to test a claimed distribution. What we're going to do is the goodness of fit test. Or we've got some claim that a certain percent fall in various categories. Is that claim accurate? Does the data fit that distribution well? Is it a good distribution? The test statistic we will use is chi-squared is equal to the sum of the observed frequency minus the expected frequency squared divided by the expected frequency. So we've got some new variables. O is the observed frequency. And E is the expected frequency. And this chi-squared value we're going to calculate by hand. It's not too bad, but it is one we should know how to do. Now, with chi-squared, we have to know the degrees of freedom. The degrees of freedom with the goodness of fit is 1 less than the number of categories. And then for our null hypothesis and alternative hypothesis, with the goodness of fit test, we usually state it in a sentence rather than symbolically, like we did with the means in the t-distribution or the normal distribution. So in words, the null hypothesis is that the data fits the distribution. The alternate hypothesis is that it's not equal to the distribution, or that the data does not fit the distribution. And what's interesting about the chi-squared, because it starts at 0 and is skewed right, that alternate hypothesis is always going to be a right-tailed test. In fact, with chi-squared, almost always we're working with a right-tailed test. There's only one context, which we'll talk about in another video, where we could have a two-tailed test or a left-tailed test. But in general, chi-squared is a right-tailed test. Now, we can use our calculator to help us find the area that's in that right tail. So let's take a look at how the calculator can do that. What we'll do on the calculator is we will find the area from the test statistic all the way out to infinity. How much area is in that right tail? The problem is our calculators can't do infinity. So we're going to put a number in that's pretty darn close to infinity. We're going to use 10 to the 99th power to represent infinity, because there's going to be very little area that's past 10 to the 99th power. That's a 1 with 99 zeros after it, a 100-digit number. That's pretty darn close to infinity. So the calculator keystrokes we want to do is, first you'll hit the second button. Then you'll select the distribution function, which is really the vars button. And then above it, with the second feature, you're getting distribution. Then you can scroll down to the chi-squared CDF. Once you've selected the chi-squared CDF, what you'll do is you'll enter the test statistic to represent the minimum value we're finding the area of. Then you'll do a comma. Then you will do the infinity, which is 10 raised to the 99th power. Then you will do a comma, and then you'll type in the degrees of freedom. We'll see this process work out when we do our example now. Let's say a researcher wants to verify a claim about her community. She wants to verify the claim about her community that 40% of the residents speak Spanish in the home. %, speak Russian. 45% speak English. And 5% speak other languages. So the researcher does a survey. In a survey of 200 community members, '71 speak Spanish. 23 speak Russian. 102 speak English. And 4 speak another language. If alpha equals 0.05, can the researcher conclude the claimed distribution is accurate? We're going to go through the same process of a hypothesis test that we've gone through before. We've just got a different test statistic, but everything's exactly the same from there. Our null hypothesis, we said, is that the language, put it in context, but that the claim is accurate, that the language spoken in the home matches the distribution of the claim. The alternative hypothesis is that it does not match the claim, that the language spoken in the home does not match the claim, or the distribution of the claim. I should say distribution because that's important. And we said with the chi-squared, we are almost always dealing with a right-tailed test. We end up more in the right tail, the more different we are from the distribution. The distribution itself is a chi-squared distribution, and we'll do a little subscript for the number of degrees of freedom. We've got Spanish, Russian, English, and other. 4 languages. The degrees of freedom is always 1 less than the number of categories. So we have 3 degrees of freedom. And now we're ready to calculate the test statistic. And this is where we're going to do our real work. we've got Spanish, Russian, English, and other. The claimed proportion, can't get it all on one page here, but we've got 40% with Spanish, 10% with Russian. So Spanish is 0.4, Russian's 0.1, English 45%, 0.45, others 5%, 0.05. The expected value we've done a survey of 200 community members. So of those 200, we should expect 40% to speak Spanish. So we can calculate 40% or 0.4 times 200, and that gives us, we would expect 80 people in our survey to speak Spanish. For the Russian, we'd expect it to be 10%. 10% of the 200, 0.10 times 200 is 20. For the English, 0.45 times 200 is 90. And for the other, 0.05 times 200 is 10. So we use those percentages and the total sample size to calculate what we expect to happen. But something different happened in our observed probabilities. What we observed is 71 spoke Spanish. This is from our survey. We observed 23 Russians. We observed 102 English. And we observed 4 other languages. So now what we can do is we can use that chi-squared statistic is the observed minus the expected squared divided by the expected. Similar to how we did the standard deviation by hand back in chapter 1, we're going to just make a different column so that we can sum those observed minus expected squareds over expected. So first, observed minus expected. Observed minus expected. The observed comes first. So 71 minus 80 is negative 9. 23 minus 20 is negative 3. 102 minus 90 is 12. Oops, I'm sorry. 23 minus 20 is a positive 3. And 4 minus 10 is negative 6. Then we square those values. The observed minus expected squared. 9 squared is 81. 3 squared is 9. 12 squared is 144. And negative 6 squared is 36. Now we take the observed minus the expected squared, and we divide by the expected value. The expected value column is that second column here. So 81 divided by 80 is 1.0125. 9 divided by 20 is 0.45. 144 divided by 90 is 1.6. And 36 divided by 10 is 3.6. Now we're ready to actually find that sum of the observed minus expected squared divided by the expected by adding up that last column. 1.0125 plus 0.45 plus 1.6 plus 3.6 gives us 6.6625. That is our chi-squared test statistic. Now that we have our test statistic, we are ready to calculate a p-value. And we're going to do that p-value by doing the chi-squared CDF. We're going to go from a low value of 6.6625 to a high value of infinity, which we use 10 to the 99th power for infinity. And we said we had 3 degrees of freedom. So on our calculator, to get the chi-squared distribution, we're going to hit second, and then the vars button, which gives us distribution. And we'll scroll down. We want the chi-squared CDF. It has to be the CDF. Make sure you don't do the PDF. We're never going to use that one. The CDF, the lower limit is 6.6625. The upper limit is infinity, which we'll use 10 to the 99th power. And the degrees of freedom is 3. And when I hit paste, you see it types those numbers in for me. If you don't have the newest model of the TI-84, you might just have to enter in these numbers with commas separating them. Get the same thing, though. We end up with 0.0835. 0.0835. And what that p-value tells us is the probability that null hypothesis is true given our data. Based on the survey, there is an 8.35% chance the proportion of people who speak various languages matches the claimed distribution. %8 chance that it matches the claimed distribution, but we said that alpha is 0.05. In other words, we will believe the claimed distribution all the way down to 5%. We only have an 8%, or we still have an 8%, so we're still going to believe that null hypothesis. Our decision is to fail to reject the null hypothesis. And the reason for that decision is because our p-value is bigger than alpha. There's enough evidence to still believe the null hypothesis. Specifically, the p-value was 0.0835, which is bigger than alpha, which was 0.05. So we can make a conclusion in context, focusing on the alternative hypothesis. We say that there is not sufficient evidence to conclude the distribution of languages spoken in the home is different than the claimed distribution. Not enough evidence to say it's different, so we'll have to be stuck believing that distribution is true. That's the goodness of fit tests. The hypothesis test process still exactly identical. We just have a new distribution of chi-squared. We have to do a little bit of arithmetic to calculate that chi-squared value, but it's not too bad. So go ahead and take a look at a few if you want to practice some. We'll talk about it more in class. We will see you then. Another use for the chi-squared distribution is testing to see if two variables are dependent or independent of each other. So the question for today is, how do we test if two variables are dependent or independent. And to do this, we will test for independence. What we'll do to test for independence is we will collect frequency data and organize in rows and columns. For example, we might compare gender to, we'll just do male, female, to whether or not you played sports in high school, yes or no. And this will generate a table where we'll enter in how many yeses, how many nos for each gender. We'll probably also have a column for totals and a row for totals. And then off this contingency table, we will see if playing sports is dependent or independent on gender. Once we have our frequency information, we also need to calculate the expected frequencies. And often I'll make a second table to do this of expected frequencies. And the way we calculate the expected frequency is we will take the row total times the column total divided by the total of the entire survey. And we'll have to do that for every single cell. So first row, first column, first row, second column, second column, second row. Find all the entries for their expected frequencies. And then we can calculate the test statistic from here. Often I'll organize this in a third table, because our chi-squared is going to be equal to the observed value minus the expected value squared divided by the expected values, and then we take the sum of all of those. So we've got two equations that are going to be helpful to test for independence. You should know how to calculate the expected values, and then from that calculated the chi-squared. Now, as we're testing for independence, we need to know the degrees of freedom. The degrees of freedom is equal to a product with independence. It's the product of the number of rows minus 1 times the number of columns minus 1. Also with independence, similar to when we did goodness of fit, the null hypothesis and the alternative hypothesis are generally in words, not in symbols. So the null hypothesis is generally going to be that the variables are independent. And then the alternate hypothesis is that they're not independent or that they are dependent. And then similar to the goodness of fit test, that dependence is always a right-tailed test. So let's try an example and see if we can test for independence. An example. A restaurant wants to know if breakfast preference is dependent on gender. So the following data is collected. And they're going to compare male to female. And some are going to prefer French toast. Some will prefer pancakes. Some prefer waffles. And some prefer omelets. And then we'll have a total row and a total column. We find 47 males prefer French toast, 35 prefer pancakes, 28 prefer waffles, and 53 prefer omelets. If we add all of those together, we'll get a total of 163 males were surveyed. For the females, 65 prefer French toast, 59 prefer pancakes, 55 prefer waffles, 60 prefer omelets. We interviewed a total of 239 females. And if we total the individual breakfast choices, we've got 112 who prefer French toast, 94 who prefer pancakes, 83 who prefer waffles, and 113 who prefer omelets. There's a total of 402 individuals in this survey. The question is, if alpha equals 0.05, can the restaurant conclude that breakfast preference is dependent on gender? Well, let's set up our hypothesis test. First, we have our null hypothesis, which states that breakfast preference is independent of gender. Breakfast preference does not change based on if you're male or female. The alternative hypothesis is that there is some type of dependence, that breakfast preference is dependent of gender, or on gender. As usual with the chi-squared, we have a right-tailed test. And our degrees of freedom to help us calculate the actual distribution is going to be the number of rows. We've got 2 rows. Don't count the total. 2 rows minus 1 times the column. Don't count the total again. 1, 2, 3, 4 columns minus 1, which gives us 1 times 3, or 3 degrees of freedom. Our distribution for our chi-squared statistic is a chi-squared with 3 degrees of freedom. Then let's see if we can calculate our test statistic. To calculate the test statistic, we first need to make another table of our expected values. So for our expected values, we'll do the same table, male and female. And for French toast, give it a little more space here. The way we calculate the expected value for our males with French toast is we will take the row of males and the column of French toast, those totals. So the row of males had a total of 163. The column had a total of 112. That's how we get the French toast male cell for expected. 163 times 112, and then we'll divide by the total. So we have 163 times the 112 divided by the total number of people, which was 402. The expected value for French toast is 45.41. Now we'll go over to pancakes. Pancakes is in the second column, first row. So in this case, what we'll see is we want the pancakes for the males. That's in the first row, second column. So those are the numbers we're going to multiply. 163 times 94 and divide by the 402. The row times the column. So we have 163 times 94 divided by the total of 402. We end up with 38.11 is the expected value for pancakes. Next is waffles. With the waffles, we want the third column in the first row. So we're going to multiply 163 times 82 and divide by the total. So we have 163 times the 83. Is it 83? Yeah. Divided by the total of 402. And that's going to give us 33.65 for our expected value. Finally, we've got the omelets. Similarly with the omelets, the total for the omelet row for the males was 163. The total number of omelets was 113. And then we divide by the 402 to get 45.82. We'll do the same thing with the females. This time the female row total was 239. So we're going to do 239 times the French toast total of 112 divided by the 402. The expected females who prefer French toast should be 66.59. With the pancakes, 239 times the column total of 94 divided by the total of 402, 55.89. With the waffles, the row total of 239 times the column total of 83 divided by the total of 402. The expected value is 49.35. And finally, with the omelets, the row total is 239. The column total 113 divided by the total of 402. The expected number of omelets for females is 67.18. So we've got this second table that demonstrates for us all of the expected values based on the row totals and the column totals. Next, I'll make another table that does the observed minus the expected squared divided by the expected. For our males, females. First with the French toast. Our first cell, and I've got to do a lot of scrolling here. Hopefully you can see it all on one screen. 47 is what we observed. 45, actually I'll go ahead and highlight it to emphasize what I'm looking at here. Highlighted in yellow here, our first cell had an observed value of 47, an expected value of 45.41. So plugging that into our formula, the observed value of 47 minus the expected value of 45.41 squared divided by the expected value of 45.41, that equals 0.06. Then we'll do the pancake preference. You'll see pancakes, the observed value is 35. The expected value is 38.11. So we plug it into our formula. 35 minus 38.11 squared divided by the expected value of 38.11, that gives us 0.25. Waffles. Same thing. We'll come up here. We observed 28 waffles. We expected 33.65. So we plug that into our formula. 28 minus 33.65 squared divided by the expected value of 33.65, we get 0.95. And we'll keep going with all of our remaining cells. For the omelets, we observed 53. We expected 45.82 squared divided by the expected 45.82. That equals 1.13. Doing the female row, the observed French toast was 65 minus the expected 66.59 squared divided by the expected 66.59 equals 0.04. With the pancakes, the observed value of 59 minus 55.89 squared divided by the 55.89, that equals 0.17. For the waffles, the observed value was 55 minus the expected value of 49.35 squared divided by 49.35 equals 0.65. And finally, the observed value for the omelets was 60 minus 67.18 squared divided by 67.18. That's going to give us 0.77. So we're going to get really good at that observed minus expected squared formula. And the reason we need to do that is our chi-squared test statistic is going to equal the sum of those observed minus expected squared divided by the expecteds. We're going to actually add all 8 of these numbers that we just found together. And when we add all those numbers together, you should get 4.02. That is our test statistic. So it's a little cumbersome and tedious to calculate because you've got to go through cell by cell, first we calculate the expected values by taking the row total times the column total divided by the total. Then you need to find that observed minus expected squared divided by expected. Plugging those values in, calculating them out, and then finally we add them together to get our final chi-squared value. And now we're ready to go on with our hypothesis test. Everything should flow pretty quick from here. We need to calculate a p-value, or the probability the null hypothesis is true. To do that, we'll do the chi-squared on the calculator CDF. The minimum value of 4.02, all the way to a maximum value of infinity, 10 to the 99. And we said there are 3 degrees of freedom. So let's do that. We'll hit second. The distribution, or vars button. We'll scroll down to select chi-squared CDF. The lower value we want is 4.02. The upper value is infinity. 3 degrees of freedom. Again, if you don't have the newer software, you just have to separate them by commas. And when we hit enter, we find a probability of 0.2593. 0.2593. Which means there is a 25.93, actually let's say based on our survey. Based on our survey, there is a 25.93% chance that breakfast preference is independent of gender. And we said we would believe the null hypothesis that they are actually independent as long as that probability does not go below alpha of 5%. 25% is well above that. And so we will make a decision to fail to reject the null hypothesis. And the reason for that decision is the p-value is greater than alpha, or 0.2593. That's too much evidence, overwhelming past the 0.05. We must still believe the null hypothesis is true. So we make a conclusion. Our conclusion is that there is not, always in context in the alternative hypothesis, there is not sufficient evidence to conclude breakfast preference is dependent on gender. And that is how we do a chi-squared test for independence. It takes a little bit of time to calculate the test statistic running through those calculations, but it's not too difficult. It just takes the time to run it out. So go ahead and take a look at trying a few of these. Off the homework, we'll do a few of these more in class as we look at it a bit further. We'll see you then. Today we're going to take a look at another use of the chi-squared distribution, and that is testing a claim about a single variance. Our question's going to be, how do we test a claim about a variance? And when we're testing a variance, a single variance, we have a test statistic, which is a chi-squared statistic. The formula with a variance for chi-squared is the sample size minus 1 times the sample variance divided by the divided by the population variance. And we need to be very careful or be very aware of what we have in the problem. We use sigma and s to represent the standard deviation. But when those pieces are squared, and we either have sigma squared and s squared, those represent what we call the variance. And so the formula says s squared and sigma squared. Those values represent the variance if it's already been squared. If it hasn't been squared, we would have sigma and s, the standard deviations, which need to be squared in order to find the test statistic. So we need to be very careful. Do we have s or s squared? Do we have sigma or sigma squared, and not get those backwards? Also, with chi-squared, we need to know the number of degrees of freedom we have. The degrees of freedom are always 1 less than the sample size with the chi-squared. And something that's unique about testing a variance is that it can be either left, right, or two-tailed test. And this is very unique because normally with the chi-squared, we're dealing with a right-tailed test. But in the context of the variance, it's the only time we're allowed to have either a left-tailed test or a two-tailed test, which doesn't happen as often. So the best way to really attack this is to run through an example. So let's say a customer wants to know how the cost of a list of school supplies varies from store to store. A teacher claims the standard deviation is only $15. So to test this, the customer surveys 43 stores and finds a mean of $84 and a standard deviation of $12. Test if the standard deviation is less than the teacher's claim of $15. If alpha equals 0.05. So we've got a claim about the standard deviation. The claim is that the standard deviation is $15. But notice that's the standard deviation, not the variance. The variance is the standard deviation squared. So when we set up our null hypothesis will state that the variance, or sigma squared, is equal to the standard deviation squared, or 15 squared, which is 225. Notice again, we had to square the standard deviation to get the variance. The alternate hypothesis, we believe that the variance is actually less than 15 squared, or less than 225. Because we're interested in less than, we actually have a left-tailed test. So let's draw a little picture of our left-tailed test. Chi-squared is skewed right. And we're interested in being in the left tail. Now, in the survey, the standard deviation ended up being 12 compared to the actual mean of 15. Is that enough to reject the null hypothesis? Well, first we need to know the degrees of freedom. The sample size, minus 1. 43 minus 1, we've got 42 degrees of freedom. And then we'll also calculate the test statistic. The test statistic is chi-squared is equal to n minus 1, 42 minus 1, times s squared. S, I'll go ahead and actually write the formula here one more time so we can see it. N minus 1 times s squared divided by sigma squared. S is the standard deviation of the sample. So for my sample, the customer did a survey and found a standard deviation of 12. That is my sample standard deviation, 12 squared to get the variance, divided by sigma, the claimed distribution of the population. The claimed standard deviation is 15. So we'll divide by 15 squared. And when I do this on my calculator, oops, sorry, the sample size was 43. 43 minus 1 times 12 squared divided by 15 squared, we get a test statistic of 26.88. Now that we have a test statistic, we're ready to find the p-value, or the probability my null hypothesis is true. The probability the standard deviation is actually 15. It's a chi-squared CDF. Normally with chi-squared, we go from smallest to largest. Here, the smallest value on the chi-squared is going to be 0 to the largest value of 26.88, comma, our degrees of freedom, we said was 42. And let's see what the calculator gives us for that value. To get the chi-squared distribution, we'll hit second, vars, so we get the distribution. We'll scroll down to chi-squared CDF, going from 0 to 26.88. Our degrees of freedom are 42, and we'll hit paste. If you have the older version of the software, you just enter those numbers in separated by commas, like you see on the screen here. And when we hit enter, we find a probability of 0.0337. 0.0337. That p-value tells us that based on our sample, the probability that the null hypothesis is true, that the standard deviation of the cost of school supplies being 15 is 3.37%. There's a 3% chance that that null hypothesis is true. Well, if that's the case, we're ready to make a decision. The decision point is always compared to the alpha. And we said alpha was going to be 0.05. 5% probability we'll still believe the null hypothesis. We only have a 3% probability, so we can no longer believe the null hypothesis. So we will reject the null hypothesis. And the reason for that decision is that the p-value is less than the alpha value, or that 0.0337 is less than the 0.05. And so our conclusion, which focuses on the alternative hypothesis in context, we can say that there is sufficient evidence to conclude the standard deviation of school supplies cost is less than $15. And that's all there is to testing a single variance. It's actually the easiest chi-squared problem to solve because it's very straightforward. We don't have to find all those expected values that we do in other chi-squared tests. So we test a single variance with our new chi-squared test statistic. And then we run it through the same process of a hypothesis test that we've been seeing for several weeks now. We should be very good at setting up these hypothesis tests. So you can go ahead and take a look at a few of these on your homework assignment. We'll look at this more in detail in class, and we will see you then. Now that we've taken a look at how a hypothesis test can be conducted for a claim about a single variance, we can extend this to the next level and look at a hypothesis test on a claim of two variances. And so the question we're going to answer is, how do we compare two variances? And similar to one variance, we have to be careful if we're talking about standard deviation or variance, because the standard deviation is the square root of the variance. But different than the single variance is we need to introduce a new distribution that models a comparison of two variances. And this new distribution is what we will call the F distribution. The F distribution, because this distribution is used as a fraction when comparing two variances. Similar to the chi-squared distribution, the F distribution is not symmetrical. In fact, it is also skewed right. Also, similar to the chi-squared, is its shape is different based, different shape, based on degrees of freedom. But what's really unique about the F distribution is it's a fraction of two variances. In other words, we're going to have a ratio, or let's just go ahead and call it a fraction, or a ratio, with two sets of degrees of freedom. We say the numerator has degrees of freedom for the numerator is equal to the first sample size minus 1. And the denominator is going to be the degrees of freedom of the denominator is equal to the second sample size minus 1. And what's interesting is as the degrees of freedom get larger for both the denominator and the numerator, the curve becomes more normal. One last thing to talk about the F distribution is similar to the chi-squared. The F is always positive, or always greater than, I guess it could be equal to 0. So that's kind of a brief introduction of the F distribution. We're going to use our calculator to do most of the calculations with the F distribution. What we're interested in is, can we set up and carry out a hypothesis test on 2 variances? The test statistic for 2 variances is simply the fraction, the first variance, divided by the second variance, or the standard deviation squared divided by the standard deviation squared. If both variances are equal, if we have equal variances, that tells us that F is going to equal to 1. We're dividing everything by itself. If we have different variances, F is closer to 0 if the second variance is larger, or infinity if the first variance is larger. We'll use our calculator actually to do most of the work for the F statistic. And so just really briefly how to do that. First, you're going to hit the Stat button. And then you can scroll over to Tests. Then you can scroll down to 2samp F test. And that's where we can access the 2sample F test for the comparing of our variances. Then to actually enter in our data, you want to make sure that stats is highlighted. And then you can enter the standard deviation. Notice I did not say the variance. Even though we're comparing variances with the F test, the calculator wants us to enter in the standard deviation, which is the square root of the variance. So we can enter the standard deviation and our other data. Other than that, the hypothesis test is going to work exactly like all the other hypothesis tests we've seen before. So let's try an example and see if we can do a test of 2 variances. Quality control is interested in the variance of two machines making widgets. The first make 32 widgets. With a variance in the radius. Apparently there's a circle on these widgets. Of 4.1 millimeters. The second makes 37 widgets with a variance in the radius of 3.7 millimeters. At the alpha equals 0.05 level, can quality control conclude the first machine has a higher variance? We'll start by setting up our null and alternative hypothesis, like always. The null hypothesis always has equity, so we're assuming with our null hypothesis that the variance of the first machine is equal to the variance of the second machine. The alternative hypothesis is that the variance of the first machine is greater, because we want the first machine to be higher than the variance of the second machine. For our degrees of freedom, the degrees of freedom of the numerator, we always do our division in order as listed in the hypothesis test. So we're going to do the variance, the variance of the first machine divided by the variance of the second machine. Same order as they're in the hypothesis test. So the first machine is our numerator. The first machine made 32 widgets, meaning the degrees of freedom of the numerator are 31. The degrees of freedom in the denominator being the second machine, which made 37 widgets, one less would be 36 for the degrees of freedom. So our distribution is that we have an F statistic that is distributed as an F with 31 and 36 degrees of freedom. And we can calculate our test statistic by just dividing those variances. Notice we're given the variances. The variance is 4.1 and the variance is 3.7. They've already been squared. So the first variance is 4.1. divided by the second variance of 3.7. That gives us 1.1081. So if we were to draw a picture of this situation, the F distribution skewed right, we have a test statistic right at 1.0181. We want to be greater, so we go for the right tail. How much area is in that right tail? Well, this is where we're going to go to our calculator to find our p-value. First, we're going to hit Stat, scroll over to Test, and then we're going to scroll down for the 2 sample F test. Oh, there it is. 2-sample f-test. I'm going to enter in the statistics. And it wants my first standard deviation, not the variance. The calculator's asking for the standard deviation, which is the square root of the variance. Fortunately, I can just type in the square root with the second, and then the square root key is above the square, diagonal from the 7. And my first variance was 4.1. So if the variance is 4.1, the standard deviation is the square root of 4.1. And when I hit enter, it's going to calculate that value for me. The first sample size had 32 widgets in it. The second machine had a variance of 3.7. So we'll take the square root of 3.7 to get the standard deviation of 1.92. And the second machine made 37 widgets. For our alternate hypothesis, we said that the first is greater than the second, so we'll select greater than. And go down and hit calculate. Notice it gives us the exact same f statistic that we found, 1.1081. But what we're really interested in is it gives us a p-value of 0.309. 3809. So let me scroll a bit, give me a little more space to work. We have a p-value of 0.3809. Remember, the p-value is the probability the null hypothesis is true. So we will say the probability, or based on our sample, the probability both machines have the same variance, that's the null hypothesis, that they're equal, is 38.09%. And the alpha tells us the probability required to disprove that null hypothesis. We have to drop below 5%. We're well above the 5%, so we're ready to make a decision, which is to fail to reject the null hypothesis. And the reason for that decision is that the p-value is greater than alpha. There's too much evidence in support of the null hypothesis. Specifically with numbers, 0.3809 is greater than 0.05. And so for our final conclusion, which is always written in the context of the alternative hypothesis, I'll leave the alternative on there, is that there is insufficient, or there is not sufficient evidence to conclude the first machine has a higher variance than the second machine. And that is how we can compare two variances. So we have a new distribution, the F distribution, which is a fraction of the variances. But the idea is still the same as our hypothesis test we've been doing. We've got our null and alternative hypothesis. The test statistic gives us an area, a p-value that we compare to alpha and make a conclusion whether or not we have sufficient evidence to believe the alternative hypothesis. Take a look at a few of these on your own if you'd like. We'll talk about comparing two variances more in class, and I'll look forward to seeing you then. Quite often in statistics, we're concerned with comparing the mean from more than just two groups. In the past, we compared two groups with the t-test. But here, when we compare more than two groups, we need a different statistical test. And that's what we're going to look at today. How do we compare the means of more than two groups? This actually also works with two groups, but the t-test is easier. The t-test turns out to be a special case of this thing that is called the ANOVA. But the t-test is easier for two groups, so we do the t-test. But when there's more than two groups, we use this test called the ANOVA. ANOVA is actually an acronym. It stands for Analysis of Variance. And the idea behind the ANOVA is we compare the variance between the groups to the variance within the groups. And when we divide them, we end up with an F statistic. And so we can compare using the F ratio, just like we did with two variances. So a couple differences with the ANOVA: the hypothesis test. For the hypothesis, the null hypothesis is always the same, that the first mean is equal to the second mean, which is equal to the third mean, which is equal to all the other means until you get to the very last mean. Basically, all the means are the same. And the alternative hypothesis is that at least one mean is different. We don't know which mean, but just one mean is different than the rest. Possibly all three are different from each other. And we use the F test to compare which hypothesis we'll end up going with. What we're doing is we are looking for a difference, but not where the difference is. Turns out that once we decide that there actually is a difference between one of the means, we have to do some follow-up statistical tests, which are beyond the scope of this course, to identify specifically where that difference is. We might have an idea where it is, but to get the exact difference, we need follow-up tests that we're not going to cover in this course. So for today, all we're looking at is, are they all the same, or is there a difference somewhere? We're not going to spend our time in this course with the complex calculations of the ANOVA. We're just going to look at actually carrying it out and having our calculator do the complex calculations. How we're going to do this is we're going to put each group in its own list. And the way we do that is we'll hit the Stat button, and then we'll select Edit to edit our list. And in list 1, we'll put the first group data. List 2, we'll put the second group data. List 3, the third group data, until we get all of our groups. And once all of our groups are actually listed in there, we will run the test. And we'll do that with the Stat button. We will scroll over to Tests. And then we will scroll down to the ANOVA. Now, the ANOVA will not give us prompts on what information to enter in like a lot of the other statistical tests did. So what we need to do is we're going to enter the lists separated by commas. And the way we get the list is we'll hit second, and then select the list number. And we'll see how that all works out with our example. Let's go ahead and move to our example and see if we can compare this time, this context, we're going to compare 3 groups and see if they have the same mean or different means. A university is comparing traditional students, transfer students, and non-traditional students. By comparing GPA in the junior year. Here are their results. The traditional students had GPAs of 3.2, 3.4, 3.7, 4.0. The transfer students had GPAs of 3.1, 2.7, 2.9, 3.2, and 4.0. And the non-traditional students had GPAs of 3.4, 2.2, 2.7, and 2.8. We want to know if all 3 groups can be considered to have the same GPA or different GPAs. If alpha equals 0.10, can the university conclude there is a difference in the groups? Let's scroll up and give ourselves a little room and start our hypothesis test. The null hypothesis is that the mean of the traditional students is equal to the mean of the transfer students, which is equal to the mean of the non-traditional students, that they all have the same mean. The alternate hypothesis is that at least, possibly more, one group have a different GPA. Let's go ahead and run this test on our calculator and see what happens. First thing we need to do on the calculator is enter our data into stats, and we'll select edit. If there's extra stuff in this list, you can highlight and hit clear enter, and that'll delete the list, or clear the list. Clear enter. Clear enter. And so in list 1, I'm going to put the GPAs 3.2, 3.4, 3.7, and 4.0. List 2 is my second group, 3.1, 2.7, 2.9, 3.2, and 4.0. The non-traditional group, 3.4, 2.2, 2.7, and 2.8. Now let's go ahead and run the ANOVA. We'll hit Stat, and this time going over to Test, and all the way down to the bottom, or hitting up gets us straight to the bottom, you'll see ANOVA. For the ANOVA, we enter in our list. We had the 3 list, so second, 1 for the first list, comma, second, 2 for the second list, comma, second, 3. And we'd keep going based on how many lists we have. We only had 3 lists. And when we hit enter, we get all sorts of information. We've got our F statistic of 3.07. We've got our p-value of 0.09. Under factor, you'll see we've got degrees of freedom equals 2. And under error, we've got degrees of freedom equals 10. The other numbers we're not going to concern ourselves with today. But those degrees of freedom represent the numerator and the denominator. So the factor is the numerator 2. The error is the denominator 10. They are in order, which is nice. So when we say our distribution, we'll say F is distributed as an F statistic with 2 and 10 degrees of freedom. And we just found out that F equals 3.07. And more specifically, our p-value, that's the important one, was 0.0912. I'm going to also go ahead and draw a picture of what's happening. There's my F distribution, my test statistic at 3.07, and we shade that tail, which we now know has an area of 0.0912. Now, speaking of the p-value, what that p-value means is based on our sample, the probability all three groups of students have the same mean GPA in the junior year is 9.12%. We've got a 9% chance that all three groups have the exact same probability. The p-value is the probability the null hypothesis is true, which means we are ready to make a decision. The decision is based on the alpha. We said alpha is 0.10. We're going to believe the null hypothesis is true until there's less than 10% chance it actually is true. We have a 9% chance that it's true, so that passes our threshold, so we will reject the null hypothesis. And the reason for that decision is that the p-value is less than the alpha, or the 0.0912 is less than the 0.10 we said was our decision breakpoint. So our conclusion? In context of the alternative hypothesis is that there is sufficient evidence, because we rejected, to conclude the mean GPA of traditional, transfer, and non-traditional students in the junior year is not the same. Again, I'll notice this test doesn't tell us which group is different from the rest, or possibly all three groups are different from each other. It just tells us that they're not all the same. So that's the ANOVA. It's another use of the F distribution. There's actually several types of ANOVA. This is the most basic that we're going to look at in this course, and you can see more ANOVAs in more advanced statistics courses. But for now, we're comparing, do multiple groups have the same mean? We plug it into our calculator, we get an F statistic and a p-value, and we should be able to conclude, do they all have the same mean? Or is there a difference somewhere in the group? Try a few of these on the homework. We'll talk about it more in class, and we will see you then. This video is going to look at the important concept of finding a relationship between variables with what we call correlation and regression. So that's where our question stems from. Our question is, how do we test for a relationship between variables? And the first thing we're going to start with is just getting a visual of how the two variables are related using what is called a scatter plot. A scatter plot is basically just a graph of all of our data. So it's best illustrated with an example. Let's say a researcher collects a sample of the number of pages a person reads based on their age. So we've got, let's call the first column their age, and the second column the pages that they read. So we've got a 14-year-old who read 40 pages. There's a 21-year-old who read 45 pages. They asked a 33-year-old who read 92 pages. They asked a 45-year-old who read 167 pages. And they asked a 63-year-old who read 171 pages. The idea of a scatter plot is if we call the first column the independent variable x, and the thing that we think changes based on the independent variable, or the dependent variable y, we should be able to graph these to get a visual of how they relate to each other. Let's go up by tens on the x-axis. 10, 20, 30, 40, 50, 60, 70 years. And on the y-axis, we'll go up by 30s. 30, 60, 90, 120, 150, 180. And so we'll make a point for each one of these, and this is going to be what becomes our scatter plot. So at 14 years old, we'll go up to 40 pages, which is right about where that blue dot is. Then we've got a 21-year-old who goes 45 pages, so maybe a little bit higher. Then there's a 33-year-old who's going to go up to 92 pages. A 45-year-old who will go up to 167 pages. And a 63-year-old who will go up to 171 pages. And so we kind of can see a relationship here. But before we get into that, let's make sure our scatter plot is complete, because a good scatter plot will have titles and labels. So the bottom represents the age. Going up represents the pages. And we might say pages read by age for the title. And what we can see is the dots aren't exactly in a straight line, but they do kind of trend upwards. It seems that as age goes up, the number of pages goes up. And so we've got this relationship starting to establish visually. Now, our calculators can also make these scatter plots. So I want to show you how to make this exact same scatter plot on the calculator. So first, I'll write out the instructions, then we'll go ahead and do it. First, we have to enter the data. And the way we enter the data is you'll start by hitting the Stat button, and then you'll select Edit. And then you can put x in list 1 and y in list 2. Once you've entered the data, you're ready to make the graph. And the way we make the graph is first you'll have to hit the second button, and then you'll have to hit the y equals button, because above y equals, the second feature is stat plot. It's for graphing statistics. And you're going to go into the first stat plot and make sure it is on. Make sure you select the scatter plot, which is going to be the dots. And then you want to select what list you want, L1 and L2. Once you're done with setting up the stat plot, you'll hit the zoom button. And you'll select zoom stat, which will center you right on the statistics. So let's look at doing that on our calculator. First, we have to enter in our data. To do that, we'll start by hitting the Stat button, selecting Edit. And there's already stuff in these lists. To clear it out, I'll highlight the list name and hit Clear Enter, and that clears out the list. Clear Enter. And then I'll put in L1 my x's. My x's were 14, 21, 33, 45, and 63. And then L2, I'll put my y's, 40, 45, 92, 167, and 171. Now that I've entered in the data, to set up the graph, we'll hit second and the stat plot button, which is the y equals button. Option number 1, we're going to make our scatter plot. First, you want to make sure you've turned it on by selecting on. There's lots of graphs. You want to make sure the dotted one, which stands for the scatter plot, is selected. And then L1 and L2 are my list. We're ready to see it. We'll hit the zoom button. And near the bottom, maybe not the bottom, there it is. Number 9 on my calculator is zoom stat. What that does is that centers my graph around my statistics. And you see we end up with much the same graph we had before. The two dots next to each other, a dot, a high dot, and then another dot over to the side. And so now we've got our scatter plot on our calculator. But sometimes we're interested in more than just the dots. What we might be interested in is, can we draw a line that kind of models through the center of the data a best fit close to the dots? That is what we call our regression equation. So let's take a look at the regression equation, also known as the line of best fit, also known as the least squares line. Basically, a line that models those dots as close as possible. Well, since it's a line, we know the equation of the line is going to be y equals some y-intercept plus the slope times x. And in linear regression, we call that y equals a plus bx. A little different than algebra, where you probably learned y equals mx plus b. Similar setup, but now we use a for the y-intercept and b for the slope. The equations for a and b are quite complex, so we're going to have the calculator do our work for us to calculate the equation. And the way the calculator can do that is we actually run what's called the linear regression t-test. So we'll hit stat. We'll scroll over to tests. And we'll scroll down to the lin reg t-test. We can also graph it on our scatter plot graph by hitting the y equals button and then typing in the equation. So let's do that for our age versus pages example. So pulling back up my calculator, we're going to hit the Stat button, scroll over to Test, and near the bottom, you will see len reg t test. Make sure you do len reg t test, not any of the other len reg stuff. Len reg t test. And hit Enter. L1 and L2 are x and y. We're going to always select the not equals to button for our len reg t test. And then if we hit Calculate, it gives us a lot of information. We're going to come back to some of this information in just a minute. But specifically what we're interested in right now, if I scroll down, we see A is negative 5.523, and B is 3.083. I'm going to go ahead and round those to 2 decimal digits. So A is equal to negative 5.52, and B is equal to 3.08. Which means if I put that into my equation, y equals A, which is negative 5.52, plus B, 3.08 times x. This equation models as close as possible my scatter plot. If I hit y equals, I can type that in. Negative 5.52 plus 3.08x. The x button's right next to the Stat button. And when I hit the Graph button, what I'll see is I have a line that goes right through the middle of my dots. Seems to model that quite well. We have a line of best fit. The nice part about the line of best fit is I can use it to estimate values I don't have. Let's estimate the number of pages read by a 30-year-old. If we go back to the original data, we don't have 30 in here. But age is my x value. So if I plug in the age for x, we should be able to get a good estimate for what that 30-year-old is reading. So y equals negative 5.52 plus 3.08x. X is the age, my 30-year-old. And when I put that into my calculator, I end up with 86.88 pages. So round that maybe to 87 pages, we would expect this 30-year-old to read. One important thing to note about using the regression equation to estimate points is it only works within the domain of the problem. It only works between the high and low values. We can't estimate values outside of that range. So for example, this would be bad. Could we figure out a 3-year-old? Well, mathematically, it would make sense if 3 is the age. We'll just plug 3 in for the x, and we get negative 5.52 plus 3.08 times our 3-year-old. And that's going to equal to 3.72. So do we conclude that a 3-year-old is reading 3.72 pages? Probably not. There's not a lot of 3-year-olds that can read anything. Maybe their name. The problem is the 3-year-old is outside of our data. Our data had a low of 14 and a high of 63. we're only going to estimate values between those numbers. If we go outside of the data, the model can very easily break down. And so we want to be careful not to take the model further than it's designed to go. All right, I want to look at one more thing with regression and correlation, and that's what we call the correlation coefficient. And this is where the hypothesis test comes in, though we won't do it nearly as formally as we have in other contexts. The idea of the correlation coefficient is I have this red line on my graph that goes kind of through the blue dots, but not perfect. Well, how good of a model is that line of best fit? Is it close? Is it far off? What can we know from that line? This is what the correlation coefficient measures. And we have a special variable r that we use for the correlation coefficient. And it tells us two things about the graph. It tells us the strength and direction. First, r is between -1 and +1. We say if r equals 0, that tells us that there is no relation. No relation between the x and the y. The dots are completely random. And our line of best fit just has to go straight through the middle, but that doesn't even model it well. There's no relationship. Everything's random. If r equals +1, what that means is we have a perfect positive relation. Positive means we're going uphill. So now we're going to have these dots going uphill, and the line goes right through all the dots, uphill perfectly. That would make r equal to 1. Similarly, r equals to -1 means we have a perfect negative relation. Or we're going downhill. So now there's a bunch of dots going downhill, and the line goes right through the middle of all the dots going downhill. Now, there's no such thing as perfect data, so r very rarely is 0, 1, or -1. Usually it's somewhere in between. R might be -0.78, or r might be +0.23. And the closer it is to 0, the less relationship we have, and the closer to 1, the more likely we have a relationship. And the way we determine if there's a relationship is we do a t-test. It's called the lin-reg t-test, linear regression t-test, which gives a p-value that tells if the relationship between the two variables is significant. A p-value less than alpha of 0.05 will mean that we have a significant relationship. But r works hand in hand with this p-value because r tells the strength of the relationship. R could be positive or negative, but what we'll say is if it's between 0 and 0.1999999, the strength is considered to be very weak. There might be a relationship because the p-value tells us it's significant, but it's very weak, below 0.1999999. From 0.2 to 0.3999999, we say it's just a weak relationship. 0.4 to 0.59999 is a moderate relationship. But we like to see r bigger than 0.6. 0.6 to 0.7999 means we have a strong relationship. And on occasion, we end up between 0.8 and 1.0, which would be a very strong relationship. In addition to r telling us the strength of the relationship, and p telling us whether or not the relationship is significant, there's a third variable that we look at in analyzing correlation and regression, and that is r squared, which we get by squaring the r value. R squared tells the amount of variance. Actually, not variance, we'll say variation. In the dependent variable. That is explained by the independent variable. How much of the changes in that dependent variable are explained by changes in the independent variable versus other factors? This whole concept of the correlation coefficient is probably best seen by going back to our example. So let's go back to our age versus pages example. We can run the ln reg t-test on our calculator to find these important values, the t-value, the r, the p-value, and the r squared. So going back to our calculator, let's run it one more time. I'll hit stat over to test, and I'm going to do the ln reg t-test. My numbers are all already in there. So when I hit calculate, we see our test statistic, the t, is 5.09. We see that gives us a p-value of 0.0146. And if I scroll down, we will see an r value. R is 0.9466. And r squared is 0.896. Let me transfer all those values over here, and we'll talk about what they mean. So we had a t-value of 5.09 when we round it, which resulted in a p-value of 0.0147. Also, there was an r, our correlation coefficient, of 0.947. And r squared, it says, was 0.896. With linear regression, the null hypothesis is always that the relationship, which we represent with the Greek letter rho, looks like a p, equals 0. That means there's no relationship. The alternative is that rho is not equal to 0, or that there is a relationship. And we can see in our case, we're going to make a decision, because the p-value is less than 0.05, to reject the null. and make a conclusion that there is significant evidence to conclude the alternative hypothesis, which says there is a relationship. There is a relationship between age and pages read. But we can expand on that conclusion a bit and say, because r is equal to 0.947, which if we scroll up in our notes, we see that puts us in the very strong category between 0.8 and 1.0. We can say the relationship is very strong. We can even go one step further and say because r squared equals 0.896, we can claim that 89.6% of the variation in the dependent variable, or in pages read, is explained by the independent variable, or by age. And so you see, we don't end up with the traditional hypothesis test going through all the same exact steps we have before, but the pieces are still there, that we decided based on our p-value that there is a significant relationship. Based on our r, we can determine how strong the relationship is. And based on our r squared, we can say what percent of the variation is explained by the independent variable. So that's what we're looking at today, determining is there a relationship. If there is a relationship, what that relationship is based on the equation y equals a plus bx, and also drawing the scatter plot so we can get a visual to see that relationship. We'll look forward to seeing you in class so we can look at these scatter plots, linear regression, and correlation a bit further.